the back and forth. So I always tell people the best slides, and it's kind of too late. People don't have their slides ready yet, but the best slides are the ones that the audience says, could you go back to this slide? I want to talk about this slide. So when you talk to the slide, that's actually appropriate. So bring everyone up to speed. It's up to you to hopefully keep things going. Sometimes you'll see a discussion going back and forth, around and around and around. You say, okay, let's move on. It's okay for you guys to tell the presenters to say, hey, we don't have much time. Move to the next topic, and here we go. Perfect. Can you make sure shared notes? Select the shared notes. I gotta go through every one. I don't want the chat. Okay, so we have a matrix chat. When by default you see a matrix chat, the chat will. I see a chat here. So by the way this works. They're hooked to the screens. They hooked to BBB. That's why I had no control over what's up here. They're hooked to BBB. The laptop up here is just a laptop for you to use. If a person wants to use their own lap, perfectly fine. Let them log into BBB. Hopefully beforehand, I'm going to try to start emailing people, and maybe I'll even email the speakers a reminder. If you want to use your laptop, if it's easier to do a demo, a screen share, whatever you want to do, and you want to use your laptop, you have to log in. You could come up and use your laptop. The one thing is, how many people here have logged into BBB? Okay, great. Everyone knows it. When you log into BBB, you see that microphone and the headset. And you pick microphone to talk if you want to participate, the headset if you want to hear. When you're in the room, you close that window. You don't pick either. That way, when you look here, let's see if you can see here. It's off. You can't see. Here. I don't know if I'll come over there on that side. But see this little circle? It's blank. This is my laptop. That's my laptop. It's blank circle. That means, oops. That means I tripped over the camera. No, that means that I didn't log in. That's exactly every laptop that's used in the room. Don't log in. If you log in, you're going to have a feedback. You don't want any feedback loop. The laptop is there for display only, no sound. If someone wants to use it, perfectly fine. They can stream. There's, like I said, the little share icon with the presenter, share it. So help them out. We'll have a shepherd. One of the program committees should be hopefully in every room to help out if there's an issue. Just keep things moving along. And most important thing at the end, you may exit so if you have that little square, you have as much power to BBB as we do. And, the whole Spider-Man thing, with great power comes great responsibility. And when you click on the 3 dots to exit, there's going to be leave meeting, and below, and this is the important part, there's a big red kick everyone off. It shuts down the session completely. AV has to reset if you do that. It basically kills the recording. Your share notes are lost.
And all presentations.
Yeah, and all presentations are you have to upload all the presentations again. Don't hit that button. We will hit it at the end of the day. Oh, the shared notes. This is why I'm asking people to have shared notes. People could log in and could go and please encourage people to take notes. So past years I like to have write-ups. Sometimes we don't get people to do write-ups. It's hard, but at least a blog. I want you guys at the end to have a blog on your microconference to advertise it. Think of it this way. I like to say that Linux Plumbers is the most technical productive conference there is, period. Why? Because of the microconferences. The microconferences get work done. I want to advertise that. I want people to know. I want next year that people know what a microconference is. I don't have to keep having these trainings to tell people this is how you need to run your microconference. I want people to understand. I come here, I'm going to show people a problem, I'm going to get my work done, and then you know what makes me so excited? It's when I see a patch go to the mailing list that says, from our discussion at Plumbers from last year, this is the change that's going into Linux. That is the goal of microconferences. So that's about it. Anyone have questions?
Which is the button you don't push?
It's big in red.
Can you get a demo of it?
They would be upset at me. Actually, I'm wondering if they could see the screen. I'm going to have you guys do this, maybe. Or wait, have you do this real? I'm going to just show the menu. Click on the 3 buttons up there. Obviously, don't show it. Click on the 3 buttons up there. I want to show you what What not to do.
It's pretty obvious what not
Yeah.
to do.
What does this
What
button
not
do,
to do.
Steve?
Yes. You click there, that one.
Yeah, don't even hover on it.
Before, it used to be the same color. It's a leave meeting, exit meeting. So finally, people kept hitting exit, like it was nightmare. So we finally figured out, thank for Mike Rappaport, who figured out how to change the color and change the thing. We figured that's pretty much, saying, kick everyone off is a good way of telling everyone, don't touch this, because that's exactly what it does.
No. There may be reasons I want to
What?
Leave meeting and kick everyone off is so close to each other.
Well, that's another. We haven't figured out how to change it. This is all open source software, but it's kind of kludgy and very, very, believe it, this is not easy. It's improved tremendously over the years, believe it or not. But it still has a lot more to go. Yes, they should be separate. But any other questions?
Yeah, how do we handle interaction with the on-site audience?
Oh, very good point. So online audience, see the windows here up there? What you do is you tell people who are online, if they want to talk or if they want to say anything, tell them to turn on their camera. They will pop up just like that. And when you see someone pop up, you can turn on and say, oh, then they'll see it on here like, oh, someone popped up. Encourage them to, when they want to have a question, you could raise a hand, but the raised hand pops up and may or may not, the presenter might see it. If they're shy, they could do raise their hand, but pop up the window, encourage people who are remote. If you want to interact, turn on your thing. They turn on their mic, have to log in with the mic. They have to have their sound on, obviously, and for interactions. But yeah, that's a very, very good point. Again, try to talk to people, maybe up front. Ask if any of your runners want to do live streaming, or someone just asked me, I need to share a tab. I have some web browsing thing I want to show. I said you could do that. If you click on the shared, it'll say pick Chrome tab. They could do it on this laptop. They could use their own. Like I said, this laptop, I could unplug. It's not hooked to anything. And I could go through and, oh, now that I have the slides open, I forgot to, so here's this, and then you do the harassment. And by the way, when you're on break, go to the break one. And when you're all done and you're finished, go back to the break. And then we can switch back to, we'll probably put it back to sponsors. But this will let people that come in, because the join button will always be there. People could join early. But, if someone joins and, they see a thing like what's going on, if you put on we're on break, it kind of lets the people that are remote know, okay, the thing's on a break and we'll come back when we're ready.
Steve,
Yes?
this year do we have the catch boxes with the camera following?
Yes, okay, here's another thing. Thank you. Good question here. We have the catch box. I'm sure there's here. Yep. Now, so when I walk over here, well, yeah, I can throw it. Good catch. It's not on yet.
Not a question, more of a comment.
That's what usually happens. By the way, also I come over here, and one thing is if the person is, and you'll notice it follows the camera, and if you're not talking, nope.
No, it didn't. It's not following.
Uh-oh. Is the camera set to follow? Hello? Oops. Oh, is it following now or no? It's not following.
You are going
What?
too fast following.
Oh, maybe. Oh, is it there now? Is that the one in the back? Yeah. It's following me now?
Yeah, now it is.
Okay. Oh. Yes. Maybe because I just go too fast. So the one thing is, if you're done talking or whatever, and someone's just sitting there like this, we've been told that the remote people get seasick. So put it down or something to keep it from moving. Yeah, any other questions? Yes.
Could you explain once again how to connect another computer without the mic and the headset?
Oh, so when you log in, you get that mic and headset thing. There's a little X at the top. Click that. It just closes the window. Yeah, it'll pop up. Just close it.
Oh, okay, thanks.
Yeah, that's all you have to do. So when you log in, tell people who could use your laptop, close the microphone. Don't select either one.
Okay, thanks.
And if you do, you can always go and hit exit audio. If you do it by accident. Any other questions? In that case, thank you very much and enjoy the conference.
Thank you.
You have
related question. Is this us on Matrix?
EBPF, I guess,
Can
probably.
we rename to BPF and networking? Because this
Oh.
is going to be the networking day.
Oh wait, there should be a networking then. I thought you guys separated. There should be EBF and networking. So this is a James Bonhamley one. Yeah, ask, ping him right there. Say, hey, can we do it? 'Cause he's the one that runs the Matrix servers.
All right, thanks.
Stephen,
Yes.
can I get admin for the 6 microconf tomorrow?
What's
Still
that?
round circle.
Oh, okay, so,
If not, I'll probably find someone else who's one of the runners who's actually got it.
okay, no, but, okay, sorry, Cameron, yes,
I can send you an email.
yeah, send me an email, because it's Mike Rappaport that will, he's in charge.
Oh, okay, I can
Or
speak
just,
on Mike.
just, tell Mike, could you make him, because he's the one in
Yeah,
charge
sure,
of.
if he's doing it, yeah.
Yep, thanks. Yep.
I hope that at least one will take, but there's no bugs.
Every year I forget everything.
Which track for you? Well, what day is it? Today? It's now. Oh, it's on this one. I'm going to be in the SkinX. I'm monitoring. I'm one of the monitors, so I'll be in SkinX. I'll be in SkinX. Monitoring. Of course, I'll be monitoring that.
That one will be interesting.
Right here, the Rust MC here is
Every day.
room 1-31-1. Yeah, so here. And you're the tool chain.
Today my brain decided, let's
room 180, 185, 1.8.
presentation at 5 o'clock and so on.
I'll be where SkinX is, but yeah, but no, this should be.
I want to sleep, but I want to think about this.
Yeah.
¿Dónde está tu?
1 point something.
Which one you wait? Which?
Me, that one, the next one.
You want to get your computer?
Oh, yes, I probably should.
I can't
Do you let everyone know I have it?
Yeah, it collides with Rust, which is a shame, but it does not collide with the bit
This time it's coming.
which is finally. So I will have Alexei and the others coming today while the VP of this coming.
Mike is one of the.
51.
Oh, the Cuccinelli for Rust, I found it super cool in it's super nice. The Cuccinelli is so nice. We don't deserve it.
What is your adventure of duty? What phase? Things. It's a huge change.
Okay, have to go to upload presentations.
I keep discovering new tricky complications all over the place. And then I talk to someone who says, I haven't understood this yet. You understand what I do. Yeah, it's quite complex.
No, pues
But I do have seen working code at PRP right now. It's getting there. There's the same kind of thing with this energy efficient internet. It's like a whole rabbit hole. Everything is broken and that's the thing with that is it was supported with Open and all of it. And yeah,
no se supo.
I will tell it today. So you keep working on POE and what happens are the oh,
Console, sí.
PODL. Yeah. Currently not really forks. So there's my customers happy, so okay. Nothing important for now. And there's no, we have not seen any advanced controller for now. Or maybe.
Sí, pues tomó
Anyway,
nota. No, pues me dice, no sabes qué es. Y entonces me preguntó y yo le dije, pues
so how does
rápido,
it
digo,
work
hombre,
in terms of hardware for the
hace
POE?
falta
You
más
have
la
like
implementación del
something that is in between the fire and the
Eso de que solo haya una es
Because the injection.
porque ya pasó con GNT. Es que ya
Oh
pasó
yeah,
con
okay.
GNT durante
That Not now.
No, pero ya le dije, no,
Potentially
ayer,
it could
y
be.
luego Peter preguntó un poco a eso, me dice, ¿es un problema en Power? Y le digo, bueno, básicamente sí, claro, es que es un lenguaje difícil de implementar.
There are
Claro, preguntó.
some extra
Entonces, mira,
protocols which
ahora lo que
can
igual puede ser es que joder,
POD,
yo al final estoy llegando a la conclusión de que, porque yo no quiero hacer las
kind
cosas
of
más difíciles, pero yo sigo pensando
single
que
where
tiene que implementarse más rápido, porque yo tengo mis dudas de que sea posible.
I have seen that
El problema que tiene
GI
es que
propose
no hay
to
un
use
core del lenguaje.
some
Y ese es un problema súper serio, porque para implementar, no hay un core del lenguaje. Tú puedes implementar un C++ primitivo, pequeñico, en 3 meses. ¿Vale? Y a partir de ahí, sí, pero es un subset que funciona. El problema que tienen esta gente es que el core, toda la librería utiliza stable features de esos. Es que es absurdo. Bueno, ya, pero lo que quiero decir es que complica las cosas.
Phoenix.
Y entonces, lo que yo estoy pensando funciona.
They make this kind of switches and requested one of them just to look up how this works. Well, they make some security or FPGA things and nothing but exists CL, IC or some chip. I spent here days pricing diagnostics, talking with people about diagnostics. It's really important. It's cool. We need diagnostics.
I saw your series on that and the mail.
Who's ready to pay for this? I was like, yeah,
That's
it's
the
cool.
big question.
Yeah.
But it would be really nice to have that.
Yeah,
It
that-
does better diagnostics out of place. That's true. Yeah, how many hours spent diagnosing and just implementing a few stuff to poke at the right register to get the counter to get
Yeah, exactly. And the worst thing is that actually counters are often wrong. I mean, don't show real counters. They are not really good tested and sometimes useless. We're trying to, I asked to implement level 1 and level 2 tests in LibGrid for one of our customers, and my colleague who is working on this said that he can do already things, but there was some kind of problems. If you start testing, then you will find problems not only on device in the test, but also on the host and things.
No, I haven't tested yet. I don't even know what that does. It's like you put the nick in self-test code. I've seen the code in the drivers, like some of them could define loopback, for example, to some tests. But is this defined somewhere what you should do during the self-test, or is it specific?
Not really. Looks like every driver just did something. No, not every. Some drivers implement something.
But they do whatever they want.
Yeah, and then I decided to take self-test, which was implemented for STMac, a space, and moved it to the Netcore.
Oh,
So these self-tests, which are inside of the Netcore, they actually should work with every interface
okay.
for additional work.
That's interesting.
But there are some problems which I still didn't solve. One of it is, well, it's using a file loopback to make a loop. But this loopback works only if the link is already working. And there's still missing code which should force the link in some first state if the link is not there.
That's a good idea.
And in this case it will work as well. And currently it's not supporting all those loopback levels.
Yeah, this will be a discussion this time.
Yeah, but it should be actually really, really easy to do because everything what you need to do is just to make a loop to walk, to repeat the same set of tests for all loops.
Yeah. That would be a very nice first step. Like you can easily identify where things are misconfigured.
Probably there's no need to make all loop tests, but just make the first one, and if it fails, then try to identify issues. There will be on the way sometimes switches, yeah, same problem. But this, I don't know, can we already address CPU port of the switch from the network, NetDev? I don't think so.
You can. CPU ports you can. The ones that you will not be able to access are when you have chain switches, the ports that are used to chain the switches of the array. These ones, they are nowhere.
Okay.
Not handled anywhere. At least from what I understand, because I think you can access the CPU side. I need to check. But I had seen it very about. Yeah, we need to check.
Because this year I already had some issue with NXP switch. This is JA105, 05. They have an issue with RGMI interface on the CPU side. I mean, it's really horrible. There's we implement some kind of output detection over there for the clock skew, and it is not always working correctly, and sometimes it just needs more time. So there's its first packages with the script, or sometimes it will need a lot more time, or it will never be.
So you need some kind of training to get this interface is like 90% of the errors of customers that they can talk to modify this are using HTML.
Yeah,
Did you get the timings right?
exactly.
What timings? Okay. This is wow.
Yeah, in all cases, in most cases, it's just easy work. You just define the right RGMI, identify mode, and so on, and that's work. But in this case, it isn't working because there's some kind of funny
I've never seen some such things like they would try to auto-detect the skews. Yeah, so you need to do a bit of training before. But the PSGMI, I think, does the same thing from what I understand. You need a bit of training when you need to, before you can actually send it out.
Yeah.
So in the link establishment, there is like I think they put a switch in loopback mode and they train the link until you can successfully send
Oh.
it, and then they get the user.
Okay. Interesting. Yeah. Can be implemented, yeah. But we decided to switch to RMI. And it's worked. Well, it was not important enough for the customer to invest more time and money. They just said like, oh, the other version of this switch chip do not support HMI at all. No, they support, but do not support clock skew configuration. So it should be either on the SOC side or on the board. And this customer said, it's insane. We are on 2000 and page of far.
I agree, but it's crazy that we still have to do this kind of thing.
And then after we have seen what happens.
Hello.
Hey.
Hi, Lukasz.
Oh.
I met you by the emails.
Yeah, exactly. I have seen your mail for
This is very strange when you see the people. That is the only news with the emails.
reality, not so scary.
No, I mean, normally people are friendly and programmers are even more so. You know, it's like each other in a bit. You don't know 100%.
Yeah, mail communication is not always good enough.
Yeah. Events for programmers in the process is much more better to make the ideas or push your patches.
Yeah. Previously, if I was getting mails from Russell King, I was just like exploding.
Have you seen him?
No,
Did you see my talk at the dev
maybe.
I talked about multi-file stuff. And so before the talk, it was Jamal coordinating staff came to see me and said, this was a virtual stuff like that. And he says, Andrew is going to join you at the end of the talk to answer the questions audio. So he says, Andrew also invited this weird English guy. You know him? Russell something. What? Russell is going to join the
Oh no.
But he was very nice actually.
I mean, my experience process is about discuss on the network. This 2 weeks to propose solution, and then Russell came and said, okay, sorry for jump late, and the list of the changes. My impression is this from the Russell.
He is always right though.
Maybe not all of them, 90, like 90,
I know.
But the same with the you know, and show up some confidence.
My problem with Russell earlier was like interpreting his emails emotionally.
Yeah.
And it was like I made one mistake one day and took a look to the mails at my vacation. And it was bad choice. It was like, oh, why I did it.
My approach is that just listen, and then say my rationale or what customers wants, and then I do what the community wants. If this is open on the open list, and just in the discussion with the customer. If you want to have it upstream, then there is the way to commit best practice.
Hey, it's fair.
This is best for your kind of mental health.
Yeah.
In this case, it was actually a merge window and things were broken. So, why didn't I review this before? So he was included in CC. I don't know why he didn't include it.
Golden starts with the reply looks like a spam. And then it's going to the header. And after that there is a discussion. Yeah, I told you that 2 weeks ago.
Probably was changing part of those things is yeah, it is social as well, but I mean, well, my work was let's say you need to sell things to the customer, not always the customer just push you, but you need to say like, well, you need this and okay, let's implement this, and so sometimes things look easy enough that like to account it for probably maybe some days, not weeks, and then send patches and then some of maintainers will come and say, hey, let's make things even better and implement like generic statistics for Python.
He's called like, do you job, not do hands. I have a wish list. You want to just change things, then you want 50 hours more. And you guys will pay for that.
You can't pay for 50 hours installation.
That's very fine.
I was already seeing the discussions of this is going to take a while.
Why? It's just it's
simple. Look like
One change that I was hearing, and it's broken by design for that. Give you the solution. I started part of the job and give this person like this. According to them, yes.
got yes, customers implement the master state configuration. And I was like, well, actually it is 1 hour work.
it makes sense to do that. So
It will, I will need to touch core code and we will need to touch device tree things and it will probably be a discussion and so
it went pretty okay.
Yeah.
Besides the naming, display, master, the rest was
For me, all of this word taboo thing inside the kernel is like absolute horror because I was learning linguistic and historical critical things before, and the thing is, words meaning change all the time. It is not just like, oh, we define it or we redefine it and that's it. No, it will be in 10 years a different meaning. Like, I don't know, words like Führer, German, well, it's actually a leader, but now it's a bad word because yeah, it was used for Hitler and so on. And there's a lot of many different things. Like, it's really good to see if you take like some language book, like 100-year-old and from now, you know, there's a book which makes all the words, and you have old version of Duden and you have new version of Duden, like 100-year difference, and start to compare like meaning of words, and you will see how much difference it is. And if you start this like refactoring kernel every time you think the words are have bad meaning or no, use these words for bad things, and what now? Or like, I
But now the specs are adjusted. Is that the right day? Well, the stuff you can do the actual location of the specs.
for example, I'm Ukrainian, and now I'm offended by letter Z. Because Russians use Z like symbol for the war. So who decided that letter Z is now a bad one?
Test 1, 2.
Your name keeps coming up on the message. Do you know the YAML description?
Yeah, I know. But
Okay. I'll try to show you. Everything is broken, let's go home.
Not on my side, it came from me, but
All right. So welcome everybody to the networking track at LPC. Our first talk is by Oleksiy about energy efficient Ethernet, if I remember correctly. There we go. Is it full screen? Is this big enough? I think, yeah, everybody can see the slides, or should we make it full screen? I think it's preferred to keep the notes open. Everybody's good? All right. So if anyone has any questions, I mean, it's up to the speaker whether you want to take the questions during the talk or at the end, but also you can post the questions in the chat and I will then read them out if you're too shy. All right, without further ado, Oleksiy.
Yeah. So if you have some questions within the talk, just raise a hand, maybe I'll be able to schedule it. Okay. Need to show if it's working. Yeah, it's working. Yeah, I'm Oleksiy Rempel, and I'm working with Linux kernel team in Pingatronics, and well, most of my topics last months are related to networking, so this probably not really actual anymore. Yeah. So I decided to preach about energy efficient Ethernet is broken. Every time I talk about this with anyone, they say, oh, I disabled it immediately because it's not working and everything is not good enough. So I'm trying to fix at least things for me that it works for my customers, and it is like a really deep rabbit hole like there's no end to fixing things. So is it even worth to work on this or not? In my case, it was a medical device which actually consumed not too much power, and I measured that inside of this medical device, enabling energy-efficient Ethernet will like save 0.2 watts per port, and so if you just count it per link, it will be two times more. And if you have like switches and a lot of this kind of infrastructure, it will count a bit more. So maybe it is worth to make it work and fix it at one time. And for medical devices, they are not always enabled, but stay in standby mode and still need to be activated over network. And it is actually cool if this device in the standby mode actually be able to consume less than 1 watt power in this mode. And to make it possible, then you need to enable energy efficient Ethernet to actually reduce power consumption, because there are no packets transferred in this mode, and link is mostly silent. So actually it's good to have it. So I updated this slide set. I was talking about this already previous here. There was more work to do. Now it's a bit less. In current kernel, there's already some patches included, which are rework of the PHY core framework to handle most of advertisement for EE. To make EE work, we have different levels which should be done. First of all is auto-negotiation advertisements, so that first one side advertise like I support this kind of speed link modes, and to these link modes we have EE modes which should be used if we advertise them, and the other side advertise them, and we use exactly this link speed with which should overlap with EE advertised link mode, something like this. And before the PHY core work, most of drivers was using own logic, and it was not really good, because sometimes this logic was applied like on the system start and not on the actually link advertisement part. So the EE actually failed or was never enabled, or enabled but not used, or used, enforced, and broke configuration for other people. So there was different kind of broken variants. To fix this, you will need to use oscilloscope, but you don't need to have any kind of heavy-duty, expensive oscilloscopes. Just I don't know, in the budget level of €1,000. It is enough to measure the link, and you'll see if this mode is activated or not. I will show you some pictures how this can be done. So the target of my talk is hope to inspire you to take a look if maybe your devices are kind of affected, because there are different hardware variants, and I'm not able to fix it all or test it all. So hopefully you can reuse this knowledge. I tried to analyze the current state of drivers which support or potentially support EE, and included kernel version which should probably be okay. But after I did this list, I noted that probably they're still broken. So please recheck it again if it's really working. So my point was, by analyzing this drivers, that driver is actually activate this configuration, the energy efficient configuration, on the link up or link adjust state. And the green ones, they are doing this. The FEC, the free-scale FEC, was a bit complicated case because it was broken on different stages. Now it is adjusting this low power configuration on the link up, but there's still timer configuration issues. I will talk about this a bit later. So it is probably still broken. There's a bit more drivers, and yeah, this the microchip still seems to be broken, and Samsung. It was interesting driver because it seems to implement all of what other hardware is doing in hardware. This driver seems to implement some kind of software-based low power management in runtime. I mean, in really per package time. So this should be investigated, but I can't do it because I don't have this hardware. So how is it expected to work nowadays? With current changes in the PHY core, if the Mac driver is attaching the PHY, it should call PHY support AE function to advertise the PHY framework that this Mac is able to work with this. So the PHY framework will be able to decide and say, okay, we can advertise now the energy efficient modes. Otherwise, if this function is not called now, then the PHY framework will not advertise it, and this is good. So it's better not advertising it if it's not working anyway. Then, after the link is established, the PHY framework will set the variable enable tx LPI. LPI is for low power idle to the true. So the Mac driver should use this variable to decide if, well, it should not just decide, it just should enable low power idle support. And yeah, well, this should be done in link up or adjust link function. Typical issues, like I said, that some drivers do not call the adjustment or enablement for low power idle on the link up. So it is somehow affected by ETH tool configuration, that after link was configured, and ETH tool was able to enable it somehow or disable it. Exactly, yeah. One of problems which currently not handled at all are the timers. There are different kind of timers inside of this standard which affecting different levels. Some of them are affecting Mac driver, some of them are related to the PHY driver. And this one which are related to the Mac driver, they do not recalculate the frequency which is supplied to the Mac to the actual time. So they just hope it will work, and the actual time which will go out of this device will not apply to expected result. And in some cases, it will really break actual standards, so the link will fail. And some drivers just do not call PHY support AE, which will tell the PHY framework to not enable AE at all. Now a bit about timers. First of all, we need to understand how the standard is working. We have here different parts. This, the red one, is actual data transfer. So we are transferring some frame. And the idle. this idle is not low power idle. So after transfer, we just keeping clocking things over RGMI or MI or interfaces, and it is still active on all levels. Like Mac is clocking, Phi is still up, and on the link on the cable, you'll see a lot of modulation and so on. As soon as low power idle will be active, we'll have first a transition. This is the transition part. So the first one is a sleep. So we announce that we are about to switch from idle to low power idle. And there's a timing which should be kept correctly to make this transition correct, correct. After this, on the cable, you will see complete idle. There will be nothing, just 0. And it's good, so we switched. Power is off. And in this case, usually the Mac is able to disable clocking. There is some special signaling on RGMI side that is signaling that we are in low power idle mode. And there is a silent, the Phi is able to go in a deeper power state, and there's a silence on the cable. And in scheduled time period, we have these refresh spikes. They are green. And with these refresh spikes have defined time, and it's better not to change this timing. So in most cases, if it's broken, then it's broken on the Phi side, and you probably need to contact the Phi vendor to fix it somehow, or to provide proper values for the Phi to make them work correctly. And after this, we have a very important part is the wake time. The wake goes from the Mac. If the Mac has a new frame to transfer, it will start idle signaling on RGMI interface. And this idle signal, or idle operation code, this is very important to give the time to wake up for the Phi and to let wake up the remote Phi in the remote Mac. If this time is not kept correctly, you will see frame corruptions. And sometimes if you see like, oh, A is broken because I have some kind of frame corruptions, this is probably exactly this timer, which is not configured correctly. And in case of the FEC, free-scale FEC driver, this timer is configurable and it is not configured correctly. So most probably it is broken now. Yeah.
In what order of magnitude are these times? Are we talking about? Thanks. So what order of magnitude are these times? Are we talking about microseconds, tens of microseconds, or milliseconds, or?
Yeah, this is microseconds.
Okay.
Yeah.
Thanks.
I tried to assign all of these timers to different components. So we have 5 timers. This is TS, TQ, and TR. All of these timers, sleep, quiet, and refresh. These timers are related to Phi. So if they are broken somehow, then probably you'll be able to measure this with the scope. But most probably you should contact a chip vendor. And in this case, if they are broken, then the changes and adjustments should go to the Phi driver. Then we have Mac-related timers. There's transmit timer and wake timer. The wake timer is this one. And the transmit timer, which is configurable by the H tools, is this one. It's not really defined in the standard. It's like an optimization. For example, after frame is transmitted, we tell the Mac how long should it stay in not low power idle to not reduce the speed too much. So if we'll immediately change after each frame to low power idle, then we probably have some speed regression, like from gigabit to, I don't know, 800 Mbit or something like this. And to avoid this kind of speed regression, we need this TX timer, which will keep some time the link in high power mode. And I added here some extra information. Here, if TX timer is not configured correctly, then you'll have speed regression. And if vec timer is not configured correctly, you'll have frame corruptions. Yeah, this is the same information. How to see it on the RGMI side. So the picture before, it was the cable side. The RGMI side, or there are different MII variants, whatever you are using, they will signal the low power idle in some special way. There's defined opcodes. You'll be able to find this in some of IEEE slides. This is not always directly available. Here's the case for RGMI. It is very easy to see if you attach your scope to TX control line. This one. If you see this button, it is low power idle. So you're able to use like not too much of scope lines, one to TX control line and other to actual cable to see what is happening. And if you measure this, you'll find some interesting issues, like I found in for some months on IMX8MP. There's a very popular evaluation board which is with Realtek PHY, and everything is fine. But as soon as I started testing it, I found that this PHY is actually in energy efficient PHY mode. It is not using MAC to provide energy efficient Ethernet at all. And whatever MAC is doing and what kind of configuration is using don't reflect anything on this configuration. So any changes in timers and so on will not change anything in this case. And this is one of problems because in case of this PHY, it is actually was not publicly documented as this mode is supported. And it was really nasty because if you use this board with PTP, exactly, yeah. Precision time protocol, you'll see like really heavy jitter and things which you not should have for precision time protocol. And it is possible to switch this PHY in actually MAC mode, so the MAC is regulating PHY and telling that we are using now the low power idle or not. But this is not publicly documented, and you need to get an NDA to switch these modes, and I failed in this case. In case some of you has NDA assigned with Realtek, just please, maybe you can get it, this information, fix this PHY. And what is interesting about this PHY, if you switch it in 10 megabit mode, well, this PHY has integrated buffer, well, to be able to support this PHY-based energy efficient mode. And this power buffer is so huge that it will introduce delay of like 900 microseconds. Yeah, exactly. 900 microseconds. It's like, poof. But it's only in 10 Mbit mode. So a bit tips for hacking. Yeah, just not so high power budget scope. 2 channels is usually enough. Actually, you should use a differential probe. It is safe. I recommend it. Don't do this except you are knowing what you're doing. And don't do this if you have power over Ethernet attached. Otherwise, probably your scope will blow out. Well, with this kind of setup, I just walked around of my missing differential probes, which are usually expensive. In this case, you'll be able to measure differential signal. I use this kind of boards. Our company producing this. If you need this, contact me or directly Linux Automation GmbH, or there is a link. It's just nice for hacking everything Ethernet related. If you see, well, to make measurements and get expected results, you should disable automatic crossover detection, which will make sure that you'll see transmit and receive side separately in case of 10 and 100 Mbit. In case not, you'll be always like mixed, you'll get always mixed results, like transmit on one side, receive on the other side, and by other link change, it will be other way around. The problem is that sometimes drivers are broken and do not configure this correctly, so the drivers should be fixed as well. And in this case, on this picture, you are seeing auto-negation pulses. And in this case, auto crossover is enabled, so you'll see auto-neg pulses like switching between different cables. If it's working correctly, you'll see this picture. There's no jumping between auto-neg pulses on different cables. Other part of investigation, what is going wrong with energy efficient Ethernet, is to use ETH tool just to show what is announced on your side, what is received from other side, an auto-negation level. And as soon as you see that energy efficient Ethernet is actually active and working, you will see this kind of picture. So these are actual refresh pulses, and everything other is the silent part of the picture. And if there is no auto-negation is active or actual frame is transferred, then you will see a lot of modulated signal. So just one more comparison. One is EE is active, other is EE is not active. And in case of 10 megabit configuration, 100 Mbit configuration, you is able to use partial energy efficient configuration, like one side is in low power idle, like this one. So this one is low power idle active, and other one is low power idle is not active. Yeah. And if you see a frame transferred, then you'll see something like this. Low power idle active, frame not active. And here in this case, it is very important to measure actual time and compare it with ETH tool TX timer configuration. This one. If these are numbers which are correctly configured and clocks are correctly calculated, then you'll get proper numbers. in case of gigabit, then in gigabit case, there are no transfer and receive lines, and all 4 twisted cables, you have part of modulated signal, so you will not be able to differentiate between one side receiving, other side receiving, so you should keep other side silent to be able to debug everything what you need. Yeah. I hope it was fast enough. Do you have questions?
Hello.
Hi.
We have also for us, EE is a constant source of problems. Our customers plug all different devices into Fritzbox. We make the Fritzbox. And for us, it's sometimes difficult to tell whether it's the customer's device that does it wrong, or if we do it wrong, or if the vendor chip or driver does it wrong. We have PHYs and Macs from all the vendors you mentioned. And yeah, do you have a strategy or a recommendation how we approach this? How to find out basically if we are on the good side and it must be the customer's device, or maybe there's some confirmation test or test a good other side that we can test against, or something like that?
There are some counters integrated to PHYs which count failed attempts to wake the link. Maybe this can be used, but currently I don't have enough experience to remotely diagnose this kind of problems. Currently only local experience. So I don't have any practical advice right now. But we can discuss this, I don't know, maybe after session.
So did you document your findings somewhere that people can find and perhaps input their findings into the same?
Currently there's only this presentation which is linked on the LPC event site, and some discussions on the net dev mailing list with Andrew and
So you'd mentioned for the TX wake up that there has to be some coordination with the remote PHY and the remote Mac to avoid frame corruption. What sort of resolution in terms of time sync do you need for that? Is it? I'm assuming there's a PTP or PTM component that you need to run to sync, or is it you just hope the clocks run at the same?
For the wake time, there is no need to for synchronization between sides, but there is definition in the IEEE standard what kind times are actually expected, and if systems are outside of these times, then things will break.
So did you mean more of like if the remote side gets a pulse, then it has to respond within a certain time?
Yes.
Oh, okay. Thank you.
But these times are different, and currently kernel has no idea about these timings. So potentially, as next part which should be done inside of the PHY framework is to list all of these timings. They are different between link speeds, and use them as standard for Mac drivers.
So basically apply offsets to known vendors having variants. Thank you.
All right, I think this is all the time we have for the questions. So thank you very much. Yep. I have a little gift for you from LPC.
Oh, thanks.
Thank you very much. All right. Give people 2 minutes to shuffle out and in. All right, next talk is by Maxim about representing front-facing ports. Good luck.
Okay. I can start? Okay. So, welcome to this talk. I am going to continue talking about PHY topics and low-level aspects of the link. I am Maxime, so I work at Bootlin, and what we do is embedded systems development. So on my side, I've been working on embedded devices for a good chunk of the past 7 years, and focusing on the network aspects of it. What I'm going to talk about is how do we deal with devices that has network interfaces, but when you look at the physical device, there are more than one front-facing port that is attached to that net device. So before I dive into it, just a small refresher for everyone. On typical embedded systems, you have something that looks more or less like that. You have a system on a chip. Within that SoC, you have a Mac controller, and that Mac controller is going to be connected usually to a PHY, and that PHY connected to a front-facing port. So the need for the PHY is to do some kind of translation of the pretty generic protocol that is output by the Mac and the medium-specific protocol that needs to be sent on the actual link. So the actual physical protocol depends on whether you are using fiber, you are using typical copper Ethernet or single pair Ethernet or BNC or whatever. There are tons and tons of different protocols that you can use. And this picture here, it's a good representation of 90% of the systems, and what I want to talk about is the rest of that. So the PHY, for example, is not always there. Sometimes there is no PHY at all on the link. The Mac is directly connected to the front-facing port because the PHY is either within the Mac, or we use SFP, for example, which uses a serialized link that can be directly output by the Mac. Sometimes the PHY is not handled by the kernel itself. It's driven by a firmware running on the NIC. Sometimes there is no port at all. We are using backplane Ethernet. It's hard to make assumptions about the fact that this is going to be the de facto design for a network interface on an embedded system. So what I want to talk about is this kind of situation. So you have a Mac, something on the hardware is going to actually split that single output from the Mac into two front-facing ports. So the cloud here is where the magic happens. This is what cloud computing looks like on embedded systems. So we have several examples of devices supported upstream that have this kind of layout. The two main reasons for that is either to give the final user a choice on the connector. For example, having both an SFP cage and an RG45 connector. We have devices upstream like the Macchiato bin that has that design, but there are also switches that have this kind of design. Say an 8-port switch that has actually 12 front-facing ports for our SFP cages that are shared with other ports of the switch. And the other reason to use that is to achieve some kind of redundancy on the link. So it's a bit different than bonding or any kind of other technology that does redundancy. Here we have redundancy of the link at the layer 1. So we basically, when we are going to use only one link at a time, of course, there is no other way. This is not a switch, the cloud here. We can only use one single port at any given time. And if the link goes down on the port we are using, we can try to see if there is link on the other one. And again, there are devices out there that have this kind of thing implemented. So we are going to focus on the connector part, the port here. So we know actually a lot and not that much about that port here in the kernel. So what I mean is that we know very well when the link is established, what we can do on that link. For example, when you are connected to your link partner, you can know very precisely if you can do 10 megabits per second, 100, 1 gig, 10 gigs, in half duplex, in full duplex, do you have flow control available to you or not? All of that is very well known when the link is established, but you don't know actually that much about the physical connector and the limitations that are imposed to the link because of the physical port. An example would be, for example, if your PHY is connected to your RG45 port with only 2 pairs of wires instead of 4, then you will be limited to 100 megabits per second. You cannot do 1 gig in that configuration. So the PHY device and the PHY subsystem give us some clues about that. We have a field that is the PHY def port, which tells us if we are using twisted pair or fiber or BNC. Very, very generic information. And we have kind of a list of the different supported ports in terms of fiber, twisted pair, but very broad terms that we can use. And as I said, we have also the EASTool case settings that give us precise information about the link when it is established. When you use SFP, we have also the advantage that the SFP module can tell us what they can do, if they are fiber or if they are copper. There are some quirks with that, but we can derive a lot about what we can do based on whatever the SFP module reports to us. Yeah, we know that information when we have link right now. So what I would try to come up with is an internal representation in the kernel of the physical connector. One thing I don't know how to do well is naming stuff. I'm really bad at naming. The name I have came up with so far is PHY port, but I don't really like it. Port in the networking world means a lot of things already. We talk about switch port, interfaces, and so on. So maybe MDI would be a more appropriate term. MDI is what the standard uses to refer what comes out of the PHY towards the outside world. So maybe that would be an appropriate name. And within that object, we will have a set of dedicated callback operations that will allow us to know whatever we can do on a physical connector. So the goal is to keep that very transparent. Most of the devices that are out there, they just have one single front-facing port for each interface. So the information we would report would just be whatever the PHY reports or the MAC reports. But on multi-port systems, we will have different information reported for each port. But yeah, again, the goal is to make that very transparent. So we know quite a lot of things right now. How do we know, as of today, what we can do on a physical interface? So if we look at an embedded system, for example, with a PHY and a MAC and one single port, how do we know what we can do on that port? Well, the first clue is the PHY we are using. The PHY device might only know how to do one single thing. For example, if it's a base T1 PHY for single pair Ethernet, there is a good chance that that PHY knows only one protocol, base T1S, base T1L, and so on. So we have no choice but to use these protocols on that link. But on some other cases, we can use devices or NICs that can be configured in a different variety of ways. So for example, a PHY that can do typical copper Ethernet, or that can be connected to an SFP cage alternatively. And the way you would select that is based on usually hardware straps. So on the PCB, with the way the PHY is integrated, there are some straps that are going to connect some paths to ground or to VCC in order to auto-configure the PHY in a given mode and basically hard-code that. Sometimes the straps are wrong and they report things that are not correct, or they were not integrated correctly in the PCB, or they are glitchy. So how do we do in that case? And in other cases, and this is more for NICs that are fully self-contained, like PCI NICs and so on, this kind of information would be in some kind of an EEPROM or reported by a firmware running on the NIC, telling you, okay, this particular instance of that NIC has 2 SFP ports, or it has just one RG45 connector. And the final information is looking at device tree. In device tree, we have a few clues about the actual physical medium we are using, but it's not ideal, I would say. In the case of PHYs that can do either fiber or copper, we have some cases where this information needs to be set in device tree because the straps are incorrect. And what we start to see is a tendency towards having vendor-specific properties that are being used. For example, we have a fiber mode property that is used by TI PHYs and also on micro PHYs, different properties from different vendors, but they do exactly the same thing. We have the operation mode for TI PHYs. So all of that is just configuring the PHY in a way that will make it output the right protocol on its MDI bus. So if we come up with a way to also better represent the front-facing ports in device tree, this will also help us build that set of capabilities that each front-facing port can export to the world. And one thing we are clearly lacking right now is information about the absence of a port. So let me show you an example. And this is like a real-life example. We have a device that has this exact configuration. The first representation at the very top is how do you represent in device tree PHY, simple PHY device. So you have a node in device tree that represents your PHY device, and then you have some pointers, some p handles in your Mac node that points to that PHY. So the first case is a PHY with a copper connector. The second case is a PHY that has an SFP after it, because the PHY in that case is used as a media converter. So it converts whatever the Mac outputs into something that you can feed into an SFP cage. And in that case, the device tree is a bit different. You have a p handle that contains a reference to the SFP cage. And the third case is a device that has a PHY which exports both an RJ45 port and an SFP connector. And as you can see in device tree, you have absolutely no difference between that case and the second one. You don't know if there is an RJ45 connector or not. You have to guess it or infer its presence. So how do we know about this information here? So far we don't, and it's a happy accident that all of the devices that we have that use the PHYs that have this kind of capabilities have both port wires, but we should try to come up with a new way to represent that to avoid the ambiguities. So that's the second point of my talk. The first one is about that port internal representation. Are we missing stuff? Do we actually need that representation or not? The second point is about device tree. So this is a work in progress example of what it could look like. So the main idea is inside your PHY node, you would have an MDI node that would list all of the ports. And among the information you would set is the kind of technologies each port would be able to support. In the first case, it's going to be base T Ethernet at 10, 100, and 1,000 megabits per second. The number of lanes that are wired, so in terms of the differential pairs that go between the PHY and the actual connector. And another nice thing, and maybe this is something we could discuss with people that do a bit of PoE, is we could use that to better represent devices that are power over Ethernet providers. Like when you are using PoE on a device as a PoE provider, you typically use a dedicated controller that will inject the power, and this controller is going to sit between the PHY and the connector. So we could consider using that node in device tree to actually attach the information about the fact that a PoE controller is going to inject power on that port specifically. And in this example, there is also an SFP cage attached to the same PHY. So no binding was accepted or submitted yet. This is still work in progress, so feel free to comment if you have some ideas on that. And the last part that I want to talk about in that whole problem is how do we deal with switching between the ports at runtime. So say you have one interface, 2 ports, we can only use one at a time. How do we deal with that? So here I have removed the magic cloud, and I show you some actual physical configuration that exists on products. So we have on the far right side the use case I've been mentioning you, one single PHY that drives 2 ports. On the middle there is another use case that we have, which is a device that has 1 Mac and 2 PHYs connected to the same Mac. So this is something I have been working on in the past months, and the support for that is starting to be accepted upstream. It's not totally there yet, but we are getting there. And if you look at the difference between these 2 cases, or even these 3 cases, the third one is same with 2 PHYs, but one is within the SoC and the other one is external. What the user will actually care about is not really the internal topology of the link, the internal hardware integration, but the fact that he has 1 interface and 2 front-facing ports. So we need to give the user some way to control all of that. Like, I want to use that one, or I want to use that one. But maybe we can go a bit further than that and say, I want to prefer the port number 1 over the port number 2, because the port number 1 is the one that I'm going to want to use most of the time, and the second one is a backup. Or go even further than that and say, if I am able to detect the link on both ports at the same side, still use one for data transfer, but do the negotiation on the other one, maybe what I want to do is use the one that has negotiated the fastest speed and automatically switch the port to the one that has the fastest speed. So doing that is possible, but the thing is we have some limitations depending on how the hardware is done on how we can perform link detection on the ports that are not currently used. So I've listed basically 3 main cases that I have encountered. The first case is the best case scenario. When you are using one port physically, you can still perform link detection on the other one, no matter what. You can negotiate the link speed and so on. Of course, you cannot send and receive data on it. Both ports are exclusive, but you can detect link on that one. So you could consider switching the ports with the one that has the highest speed. The second case is when you are using one port, you cannot do anything on the other one, not perform link detection and so on. And the third case is a bit worse than that, is even when there is no link on any port, you can only detect the link on one port at a time. So you do a round robin to detect the link. So you check for 2 seconds if there is link on port number 1, then you stop, and then you check for 2 seconds if there is link on port number 2, and then you stop, and you do a round robin like that to do the link detection. And when we do the port switching, we also have to consider the case where the 2 ports are connected to the same switch. So we need to send some kind of data to the switch to make it update its internal forwarding database through a gratuitous IRP. And when we start looking at that, it starts to look a little bit more like bonding. This is another question, open question, like would it be possible to integrate that with the bonding subsystem or not? It's similar but different, like we have only one net device here in that case. So all of that are the open questions. So the user space API I have so far is not yet submitted, but it will come shortly after that talk. Is based on ETH2 Netlink, so it's very specific to Ethernet, and it's just a way to list the front-facing ports and set a few attributes on them to force one port to be used, or set one as preferred, or disable one port entirely. So it's a very basic API, and it's also open for discussion if you have ideas on that. So that was my main, the main goal of that talk, to present what I've been working on so far, if you have ideas. The code so far, I have prototype code for pretty much everything I have presented. I will send parts of it as an RFC after the talk, but yeah, I have started to like troubleshoot most of the issues, but only with my limited set of boards available and use cases in mind. So if you have other things that you have considered when looking at that, let me know. Some next thing that we will do in terms of upstreaming is also the support for the file isolation. You know that that use case where we have 2 files connected to the same Mac. We have to make sure that one is not going to interfere with another. So this has been this has been submitted, but it's not yet upstream. But yeah, the next step is going to submit the whole thing that I've been presenting to you. All right, so I think that's it for me. Now I will take some questions. I think we have time for some.
So have you considered any options or other ways to do the device tree binding on systems that don't have device tree?
That's a good question. Yep. Do you have such a use case on some hardware?
After seeing what you've been showing with 2 different or 2 different connectivity things with like an RJ45 with a redundant SFP, it definitely gets some ideas floating for options that might be interesting for our use cases. So having some kind of kernel interface that would be more of like in an x86 land would be compelling.
So something along the lines of ACPI? Or
yeah, like an ACPI-based thing, but yeah, how would that be described would be kind of interesting to dig into the details.
I guess the main attributes would be very similar, but then I am not versed that much into ACPI myself, so if any help would be welcome.
Okay, yeah, no, I'll be watching for it because I'm very interested now. Okay, thanks.
Other questions?
Hello. Yeah. Just an answer partially to your comment. I have a USB Ethernet adapter with two interfaces. I mean, with two integrated files, so it's will not be possible to address it with ICPI anyway. So it's maybe will be detected by chip ID or by vendor ID, and you'll need some extra code to describe it, or I have no idea how to solve it.
Another thing is that we already have like tons of devices out there with already that setup. So the device tree would only be to clarify some things, but you can also have the option of registering the ports without device tree at all. If, for example, the PHY or the NIC or the Mac can already know everything there is to know about these ports, you can also instantiate these objects and register them.
You want to register them as a separate interface, or you want to create the software nodes or whatever that thing is?
Good question.
I have a basic question. So you showed the example where there's one PHY and two ports.
Yep.
That kind of gets tricky about like what attributes are really about the port and what attributes belong to the PHY, right? Like, do you have any ideas on that?
Yeah, well, that's the whole complexity of it. So what we get for information right now, if nothing is connected, the PHY will report everything it can do in its entirety, like an aggregation of what both ports can do. And so the complexity would be to, in the PHY drivers that support that, split that out between the two ports and say this one can only do base T, and this one can only do base X or base R, but then when you plug an SFP module, this is going to change depending on what the SFP is going to do. So this is where most of the complexity will lie here.
Yeah. Okay. Any other questions? All right. Thank you. Let me give you the chocolates. Thank you very much. Hi.
Shall we have some break? Or?
No, the break is after your talk. Just give everybody a minute to make the noise. There's a thingy here if you want to walk around. You want this?
It might be helpful, but select the timer to keep track.
Oh, okay. I think this is... Oh, it does. Nice.
This is the... which I discovered when Steven was presenting the whole system. I think I'll just...
click here?
I'll just use the mouse here, or maybe this can be helpful.
I don't think this works.
Excuse me?
What? Oh, okay, go ahead. Thanks. I don't know if this doesn't seem to work, but you can play around with it.
I will do. I think that I will manage to. No, it's okay. It's okay. I mean,
No, I mean, you can start, right? It's, oh no, 5 more minutes. Okay.
2 more minutes. I can start earlier.
All right, let's start. Next topic is by Łukasz about HSR. There's a lot of patches floating around the mailing list about HSR, so we are looking forward to learning more.
Thank you. Good morning, everyone. My name is Łukasz Majewski. I'm going to present some information regarding Linux kernel high availability seamless redundancy driver. Okay, so this presentation would be divided to 3 main parts. I will start with brief introduction into the standard. I will present what are the internals, what is the operational idea behind it. Then I will spend some time to present the current status of the Linux kernel driver development and say a few words about the possible improvements. And the last part would be to present some testing strategies which can be used with that particular driver. So a few words about me. I'm an embedded software engineer employed as contractor at Denk Software Engineering. If you would have any questions regarding this presentation, please reach me with the email from this slide. I'm very open source oriented developer, involved in some projects. Most notable are networking in Zephyr. This is the T1S and DSA subsystems. I'm a long-time U-boot developer with some experience in the DFU and the USB stack. With Linux, recently I'm doing the networking, some DSA and the HSR itself. And with the glibc, I help with the year 2038 bug fixing for 32-bit systems. So this is the short introduction. Let's start with the glossary. The HSR, high availability, seamless redundancy, is built from nodes. We have DA and H, which is doubly attached node for HSR, and SAN, which is the singly attached node. The SANs are representing networks which are not HSR supporting. I will call them standard Ethernet. And if you want to connect the DA and H with SAN, then we need red boxes. Those are special devices which allow the communication with two sides of that networks. And the red box is the abbreviation for redundancy box. Last but not least, there is very similar in principle and properties protocol to HSR. It is the PRP, Parallel Redundancy Protocol. So what is the rough idea behind the HSR driver itself? We have nodes on the network, and the network topology is ring. Each node has two Ethernet ports, and now those two Ethernet ports, they form single SAH port. In principle, when we want to send data from the node, for example here, the frame is passed to the data is passed to the SHR driver, and then the frame is duplicated. So we send exactly two copies to the network, one on the one Ethernet port and the second one to the second Ethernet port. In that way, we have two copies flowing in the network, and then the destination node, for example here, is receiving either two copies, and then it decides if one shall be discarded, or because of some failure, for example, node is broken or the connection is broken, it only receives one copy. And this is enough. The networking still is working. As I depicted on the picture, we have the red box node, which allows us to connect between the standard Ethernet, like SANs, to the ring with the HSR nodes connected. Last but not least, the node which is sending the frame, the duplicated frame, is responsible to remove them when it detects that the frame has made the whole circle. This prevents looping indefinitely the frame in the network. Okay, so how this is done in the level of frame? We have the SAR tag inserted. It has 6 bytes. First 2 bytes are the ether type. In our case, this is the 0x89-F. Then we have the path ID, which specifies the direction in which the frame was sent. We also have the frame size, because we can have different HSR frames. For example, we have supervisory frames, we have supervisory frames from red boxes, we have normal data frames. So this is different for each case. And last but not least, we have the sequence number. And this is crucial because sequence number in conjunction with source address allow us to assess if we already received the copy of the frame, and the copy which we receive afterwards can be dropped. Now I'm going to present some facts regarding the SAR protocol. Protocol. It is standardized by the International Electrotechnical Committee. The newest standard is from 2016. This protocol is very similar to PRP in principle and in properties, because the PRP basically has the star topology. This is the redundancy network. So we have two networks in parallel. Whereas for the HSR, we have the ring topology. As I mentioned, we have two Ethernet ports, on top of which we build the HSR network device. Frames are duplicated. That is the reason why we receive at least one copy. And also, as I showed previously, those frames are not compatible with standard Ethernet frames. And this is the motivation for red box devices. As we have the duplication of frames, of links, there is no single point of failure. So even when the node is broken or the connection is broken, then we receive the data anyway. And this is the most important property of the protocol, because we have first zero switch over time. So we don't need extra time to reconfigure the network because of the failure, which is the case in, for example, RSTP. And also we don't lose any packets. So the data is flowing anyway. And this makes it suitable for mission critical, safety critical, hard real-time use cases. And it's used mostly with the industry/transportation or heavy industry or avionics. So this is the use case for this particular driver. It is possible to offload some of the operation to hardware. For example, the duplication of frames can be done in the hardware device itself. And this driver is off-the-shelf driver, because one example, the most notable, is the KSZ9477 from Microchip. It was Micrel previously, which can be used for such use case. The KSZ is the switch circuit, well known to be the switch circuit. And also it is possible, according to the standard, to monitor the health of the network itself. Because in 2-second interval, by default, because this can be adjusted, the supervisor frame is sent, which will allow us to know which node is still reachable, if there is connection failure with the connection, etc. So what are the features of currently implemented driver? This driver supports the HSR version 0 and 1, as well as PRP. And this is done in pure software. So this can be done in pure software. This is one case. Also, the red box support has been added recently. One thing to note is to have the pretty recent IP Road 2 program. 6.10 already has the support to set up the red box with the IP command. The HSR driver can closely cooperate with DSA driver, which has the hooks or callbacks for setting up the HSR protocol support in the switch port. Also, the red box is filtering some traffic which is not supposed to be received by the other side of the network. For example, the HSR traffic shall not be delivered to the normal Ethernet port when not needed, and in opposite direction. This helps with improving the performance. And as I say, there is offloading support. The KSZ9477, it has hardware support for duplication of the frames, and also to send one frame to two HSR-aware ports. So this is done in hardware. Moreover, it has some hardware support for removing duplicated frames, but this is according to the manufacturer not working 100% in all the cases. There are some cases in which the frame can be not dropped, so we need the software fallback anyway, but this provides substantial improvement in performance anyway. There is another chip used, XRS700X, which despite of having the features from the above one, it also can in hardware insert and remove HSR tags. And the flags which are presented here, those flags are accessible from Ethernet tool, ETH tool, and can be assessed if are supported or manipulated. Also, it is possible to inspect the node table status via the driver, so one can see what are the nodes on the network available. There is some ongoing development. There were two patches developed by Sebastian Andrzej-Siewior recently. One of them replaced the plain ++ operator with the sequence number increasing with the atomic operation, and also optimization for spin lock usage was done. I also saw some patches from TI. This is the AM64 SoC, and it provides the hardware support with the IC SSG IP block. But for doing that, you need the firmware from TI anyway. But to note that the hardware offloading is also possible on this architecture. Now I'd like to delve into the testing because I think this is quite crucial for this driver. First approach is to use the hardware. Of course, this is very welcome for the customers because you can test it with the real hardware, how it works, or how it will work during the deployments, etc. In my case, I was using the KSZ9477 development boards. I was able to set up the connection with and without hardware support, offloading support for the HSR driver. So it was possible to use only software emulated HSR, and then to use the hardware offloaded use case. Also, there was the tiered port to model the red box case to communicate with the standard network, standard Ethernet network. For the configuration, important parts are here that you need two slave Ethernet ports to form one HSR higher level network device. Also, you specify the portion of the MAC address for the supervisor frame and the version of the protocol. And for the red box, there is the tiered parameter, the interlink, which is the port to which the standard network devices can be connected. So this is the configuration. And when I had that all connected, I did some measurements, maybe to be sure how good it works. So I was using the NAT TCP program. In my use case, it was 100 megabits per second, the maximum speed for the transmission. So with hardware offloading enabled, I was pretty close to that value. But when I only use the software, then the performance dropped, I think, considerably, and it was possible to see the difference in the operation. Now the second case, I think even more interesting. This is the case with using the QEMU, and this particular diagram is from the already available in the Linux kernel 3 HSR_redbox file. What we can see is that we can model the small HSR ring. This SHR ring is connected to the switch, to bridge, and we have some standard network devices connected to the bridge. So the topology is pretty, maybe not very complex, but it reflects the normal use case, for example, for the HSR driver. What is important here is that one can use this approach when there is no hardware, because very often the hardware is available during the development and then it is sent to the customer, sent back to the customer. And in this case, with using the network namespaces and traffic control program, one can simulate very sophisticated networks and use cases. For example, drop patches. For example, introduce some jitter. Reduce the speed of the link. Even insert some wrong values to the packet itself. So this can be all modeled with the QEMU. And as it is in one box in the host PC, you can easily connect Wireshark, T-Shark, check what is the status of the network. To even make it even better to access, to test the HSR driver, I will now present how one can set up this test environment. I have uploaded with this link my configuration file to my GitHub, so they are freely available. Those are two configuration files. One is to build the build itself, and it has some extra tools like bash, etc. enabled. The second step, after we build the build, we compile the kernel, and the configuration files is also uploaded. It has support for virtual Ethernet, HSR, network namespaces. This configuration is in sync with the NetNext from last Friday, I think. So we build the kernel and copy it to the build directory structure. Last step is to, of course, start the QEMU, but we need to mount with the SSHFS the directory with the test itself. So this is under tools, testing, self-testness, and HSR. And then we can freely run the SSH redbox and SSH ping. So it is very easy to assess if the tool is working correctly or if the driver is working correctly with that approach. Okay, so what are the future enhancements? First of all, the node table is available to the debugFS, and we discussed this on the mailing list that this is not the best approach. So other way needs to be devised. Also, that is the reason why the proxy node tables from redboxes are not accessed yet. For my internal usage, I have some patches to use the debugFS as well, but I think that maybe the IP02 might be extended, or maybe sysfs can be used for such to deliver such information. Also, my impression is that the HSR forward do function is going pretty convoluted recently. According to the standard, the patch ID shall be set when we use the redbox device. This is not yet done, so this is the open topic. Also, there is the maybe it would be good to separate the PRP and HSR specific code, because for now we have the HSR underscore file names which start with the prefix of HSR underscore, and this is a bit misleading for somebody who doesn't have the experience with that driver itself. Somebody reached me via private email with the question if I'm planning to add the redbox support for PRP, and unfortunately not, because this was the PRP itself was out of the spec for my project. And also I think that at some point we would need to provide the support for VLAN and P2P in the HSR ring. My personal impression is that the P2P demand will be sooner than the VLAN. Also, it would be good to model the quad box operation with the test scripts, because I did not do that, but this is interesting to check if the two combined red boxes can form the quad box. And also the driver itself is orphan. It is developed ad hoc, in ad hoc manner, when developers have some work related to this particular driver. So this also could be improved. Okay, to sum up. As I say, the SHR driver is actively developed. Patches are flowing, maybe not very high volume, but from time to time there are fixes, there are some enhancements. It is also possible to use the hardware offloading. Maybe good starting point and good reference is the KSZ9477, because it shows the way to add the support for chip which might be used in that case. My impression is that there is some rising interest in the industry to have the open source PRP and HSR driver available. And also the QEMU-based test setup is really sophisticated, might be really sophisticated, and is a very good tool for validation and to prevent regressions. So those were my points of the presentation. Now it's time for the questions. Thank you.
How the duplication is actually working? Is it based on some kind of frame ID or just arrival time?
The duplication is that when you use the offloading, then you have the hardware itself is just copy the binary data. So in the case of the hardware, the KSZ, for example, it just copy binary data, and even the path ID is not correct according to the standard, because you have the path ID of 0 and then it sends it. So this is like one way. The second way is that in the driver itself, it just copy binary data when you have the interface before you send it to the...
I mean deduplication.
Deduplication, yeah. Okay, sorry. So the deduplication is that you use the destination address, the source address with the sequence number. So we have in buffer the number of received frames, and when you see that, okay, I have already received that from that source address with that sequence number frame, then when you receive another copy, then you knew, okay, this is already served, and you toss it away.
Are there some kind of maximal timings between arrival time to deduplicate it correctly?
I think there is specified by the standard, but I would need to delve into the... For sure there is like the information stored in the node, which receives the data. You have the list and some cache with the frames available. So it just has the information what was received, and then by using the destination, the source address and sequence number, you just remove it.
And one more question. How PTP is expected to work there?
I saw some presentation from Cisco that you need to hack the way that you receive the frames because you have the duplication, so you don't know which one is the correct one. And you would need to delve into the received frame and then make the adjustments. This is done already with the Cisco, but they advertise this, but I was not thinking yet how this can be moved to our driver.
Because if I imagine it correctly, the path of the frame inside of the ring has some unexpected latencies inside of the switches, and as far as I know, cassette switches do support transparent clock, but only if DSI is disabled. If CPU tagging is disabled, then transparent clock will work, and if not, then...
I don't know. I mean, my impression is that for now, the demand was to have the HSR from the Linux kernel with hardware offloading and pretty good performance. And that was the case here. But if the PTP will show up, I think yes, because for the transportation or any real time support, it will be required anyway. But I don't know how it can be yet done. We just move step by step with some basic, how to say, steps to follow, right?
Hi. There is a specification for PTP and HSR, and I've been working on it for like 2 years ago twice, and it got cancelled twice. You need to patch Linux PTP like big time to support transparent clock and dual clock and whatnot. And I have no idea how to get it done in the kernel. You need the Linux way you have the sequence number is that the highest one wins. That's why you have to send in one by one and shoot the last packet left, and they got not to get reordered. Either way, you need to send packets from userland which get duplicated on both links, and you need to have one-to-one connection on both sides of their Ethernet link to get one-to-one connection for the clock.
Okay.
I'm not as far as doing code. I have the specification, I think, this year. And then it got cancelled again because the more nodes you get, the slower it gets, and then people say, no, it's not worth it.
Okay. So this is the open question if there is the...
Right. So this is what you need to keep in mind if you ever try to implement it.
Okay, so the performance drop is...
well, the performance drop is because you need to... say you have 20 nodes, right? Then you have to copy the packet, and it gets slower and slower with each node. So each one I know that are using this in production have FPGA with cut-through. So what you get in Linux is all set. Okay. And you don't worry about anything else. TI, with what you presented, I'm not aware of anything recent. I know they have heavily patched kernel and userland, including Linux BTP, with their hardware. And for something Linux kernel is what they offer. I haven't seen anything recent.
I think that were patches from a few days ago, like at least from the September.
Ah, okay. That's news to me, because back then when I tried to do it, I was like, hey, what's doing TI? Maybe we can copy it. And this was, no, it's heavily dependent on what they did on their firmware side.
Okay. So at best, what we have in Linux now, we have the some off-the-shelf device with the limited offloading. And at least in my case, we are happy that the performance was high enough to have the 100 megabits transport speed achieved. So this is the current status of the driver. What would be the next? Then I cannot say what would be the next demands. Okay?
Maybe the first question, can you do it selectively? Like can you say, for example, I don't know, this destination address or something like we do HSR, and for another we don't do it? So, I mean, for example, to have, like you could say, okay, the application traffic uses HSR, and for the time synchronization we don't use it because we have another setup, something like this?
I think this would not be welcome, because when you set the, we divide the network to have the HSR, very often this is to communicate with some very important parts of the system, and then the parts which are not so critical, then just use the other networks, that's how to say. And when we start to mix it, then I believe this will not work well at some point. I just say about the PTP because I was curious about the Cisco is advertising it, that maybe somebody from the management of some companies will read it and then demand, hey, they did it, so do it in the open source. My impression is that this is for reliable systems. So when we start mixing frames which have the SHA tag and they don't have the SHA tag, then we would see some issues.
Okay.
And one impression from using the KSZ9477 was that when the chip was not correctly configured, when there was no separation, when all the frames were mixed, then it was not working correctly. There were some subtle bugs. So also the way the hardware is configured is important in this case. This is why I mentioned the DSA configuration hooks and etc.
Mm-hmm. Okay, I see. Another question. So I've seen in the tag there is a 4-bit path ID. So
yes.
Are there more complex topologies than just a pure ring where you would only need 1 bit?
For the HSR, this is the just 1 bit is used, and
okay.
For the PRP, more bits are used.
Okay, I see. So they use basically the same
tag
structure.
In principle, PRP is very similar to
okay, I see.
HSR. They're just different clauses in the standard.
Okay. And the last question, how would you operate it properly, such a network? So what I mean, for example, when I ping, just send a ping between two devices, and one one part of the ring is, for example, broken, you would not see it.
You would not notice that because you just use the HSR higher level, how to say, network devices. So we just configure the routing to use that one, and you don't see the network ports which are from which you build the SHR device. So you just see the HSR 0, for example, and then you just send the data and you will not notice that something went broken. But where you can notice that something went broken is the node table, which allows you to, where is the, you have the node table which will have the information about the network status itself. Okay. And so we have the node table which will say that, okay, node table from this node will say that, okay, there is a path to this port, the path to this port, and you will see the status and healthness of the system itself.
So, okay, and I can get that via ETH tool or whatever.
Excuse me?
So from user space, how can I
the node table. You can use the node table to see what is the status and healthness of the driver itself. When you send pings, you would not see that the duplication. Of course, if you disable debugs, but you normally will not notice that.
Okay, so I just from user space access the node table, and then I will see. Okay, yeah, this part of the ring is probably broken.
That it was because with the 2 seconds interval, you have the update of the frames. The supervisor frames are sent with 2 seconds interval. So when you unplug the cable or do something like that, you will notice that something will be.
But only after 2 seconds. Or
yeah.
Okay.
But you shouldn't notice that when the network is properly configured and you have two paths to travel.
Mm-hmm. Okay. Thank you.
Node table is actually a table, but what is actual user space tool for this?
No, this is exported via the debugFS. So it's like a file that you can cat and see.
But I hope there is a plan to use IP route or something Netlink interface.
That was the discussion, because my first approach was to just use the same API, to use the same file, for example. This is exported as file. So we cut it and you see what is the status. And for red boxes, it was also required to see the IP address, the MAC addresses for the nodes which are connected to the standard Ethernet. And I was planning to use the same way to do that. But then on the list it was replied that the debugFS is for debugging. This is not used for like production. And when this is done in that way, that you use debugFS, then you force somebody, or there is a temptation from the how to say, industry to use it as a fixed API.
Good.
And maybe the IPO tool can be extended, or I think Andrew Loon also proposed maybe some other program, like we have the program for managing the database for the switches can be done in that way. So this is the open question. Maybe sysfs, but I don't know if can be used for this one.
Diagnostic fan, so I like to make diagnostics which works in embedded devices and automatically without interaction of the human. And I just trying to imagine how to diagnose this kind of issues as fast as possible, that there is a regression in the ring. And in this case, I can imagine that the kernel need always watching what is the state of the neighbor table, or whatever table name is it. And if there is a changes, then push some kind of broadcast notification over Netlink to the user space that, oh, there are changes.
As I say, on the very beginning, the demand, the requirement was to have the full speed HSR with the ring support, red boxes with the 100 mega bits per second. And that was the basic requirement. And for the daily use or for testing, it was enough to add the code which was out of the tree. But for have it done properly, then maybe a bit more discussion is required, because at some point people will start using that, and maybe they already did it.
All right, thank you very much.
Thank you.
Here's a little speaker gift.
Which one is Maxim? This one?
Maxim.
I just wanted to say, in general, I was told like the catchbox, it doesn't like it if you're too close to the camera itself. So you can keep, I mean, this should still be borderline fine, but like the further away you can keep it, the better. That's yeah, it's just confused in general, but just like as a rule of thumb. I mean, this should be fine. Yeah, because it's not one either way right now.
We can experiment. I was trying to keep an eye on the third one, right? The one on the right is the one.
Yeah, exactly.
I'm gonna try. Yeah.
Internally, I don't know if it will work better if it's not also mic, because like it was just like.
I will try to switch to the mic.
If it doesn't work, it doesn't work.
Yeah.
But yeah, I just want to.
Hey Quentin, you changed your hairstyle. Good, how are you? one fast.
It'll probably be that. It'll probably be social.
Like it leaves the tree in multiple stages.
Okay.
If VM fails, like there's a dry script like take the entire series, it will start the commit with the merge commit message with the cover letter. So it like does multiple things and you get confused because other type address. So yeah. Daniel was commenting like, oh, I thought this is going to just be one thing, and now it's everywhere.
I try to listen to the specific IP
You want me to give you an intro? All right. Oh, I need to download your slide.
Okay.
LPC. It takes a second. All right. Settle in. Okay, let's begin. The next talk is about the pair network namespace RTNL, breaking up our biggest lock. Take it away.
Thank you. Okay, let's get it started. Hi everyone, I'm Kunyuki, working for AWS, and today I'm going to talk about classic topic, that is RTNL. So this is the agenda. First, I will walk you through what is LT Netlink and what is LTNL, and then introduce some recent updates for LTNL. And finally, I will explain an issue that we are facing on and a possible solution that requires a large set of changes. So let's move on to the first section. LT Netlink is a kind of netlink family and stands for routing table netlink, and we can use it via a netlink socket created with protocol netlink root and communicate between various subsystems including network interfaces, IPv4, IPv6 addresses, routes, neighbor entries, blah, blah, blah. So most major network resources can be configured by LT Netlink. And in the netlink message, the green field and pink one, and then the message type and the LT gem family, that is the first byte of the message data, are used to determine which subsystem to communicate with. And also the orange field and the message flag is used to determine which function to invoke to process the LT Netlink message. So LT gem family is a protocol family like PF unspec and PFINet or something like that. And any message type consists of 4 types of message type: LTM new something, del something, get something, and set something. And NL message flags is this one: NLM F request, arc dump create. So for example, if you want to create a network interface, the LT gem family is PF unspec, and NL message type is LTM new link, and NLM F request and create flag are used. And if you want to dump IPv6 addresses, the protocol family is PFINet 6, and the LTM message type is LTM get address, and NLM F dump flag is used. And these messages are processed by message handlers registered by each subsystem that calls LTNL register or LTNL register module. And the function accepts 2 function pointers, do it and dump it. Dump it is called for dump request, and whose message type is LTM get something, and NL message flag has NLM F dump. And do it is called for other messages. The functions are stored in an array of struct LTNL link, that is LTNL message handlers, and indexed by protocol and a message type. So when we send a netlink, LT netlink message, the NL message type and LT gem family are used to fetch the corresponding LTNL link struct. And then the do it function stored in the LTNL link struct is called. And the notable thing here is the do it is called on the LTNL lock. This is so-called LTNL. So LTNL is a big kernel lock for the networking slow pass that is a global mutex, and it serialized all of the LT Netlink requests, but the situation has been improved since 4.14. The last argument of LTNL register, the flags, was added in 4.14 to control how each handler is called. The flag is also stored in the LTNL message handlers with the do it and the dump it functions. And the first flag added in 4.14 is LTNL flag do it unlocked. So you can guess from the name, if the do it is registered with this flag, the do it function will be called without LTNL. So by using this flag, we can push LTNL down to do it, or convert do it to use LCU. So if the do it is registered with the flag, in LT Netlink receive message, before taking LTNL, there is a similar code, but that is executed on the LCU. So this time LC read lock is acquired and LTNL link struct is fetched on the LCU. And if the struct has the flag do it unlocked, then the do it is stored in a local variable do it, and LC is released, and then do it is called. So since the flag was added in 4.14, few do it functions has been converted, and as of 6.11, we can run certain do it functions without LTNL. So the next section listens to updates for LTNL. So this year, 2 notable changes were merged to lower the LTNL pressure, and the both works were done by Elik from Google. And the first one is LTNL flag dump unlocked that is added in 6.9, and that is similar to do it unlocked. So if if dump it function is registered with this flag, the dump it will be called without LTNL. So we can use this flag to convert dump it to LCU. And as of 6.11, 15 functions has been converted to LCU. And another improvement is exit batch LTNL. This is also added in 6.9. So the exit batch LTNL is a new method of struct parnet operations. The method is called when network namespaces are destructed by a single thread work. The first argument is the list of dying network namespaces, and the second one is the important one. So to explain the second argument, let's see how network interface is removed. So when we remove network interfaces, we need to run these steps, 1, 2, 4. So first, acquire LTNL and queue network interfaces to a linked list, and pass the list to unregistered netdevice many, and then release LTNL. So here, unregistered netdevice many calls flush all backlogs and synchronize net, and both of the function have some latency. For example, flush all backlogs iterates all the CPU and checks the softnet data and check if there is SKB that is tied to a dying network interface. And then, if there is such a SKB, we need to flee the SKB. So it takes some time. And also, LTN unlock does not just release the sorry. So LTN unlock does not just release the mutex. It also waits until each network interface's left count to drop to 1. So this also adds some latency. And this network interface removal was common in exit batch method of some module like bonding, bridge, Geneve, IPIP, GLE, and more. And this is because when a module is unloaded, all network interfaces created by the module need to be also removed. And this method is basically called for alive network namespaces, but it's also used for network namespace dismantle. So then we call exit batch LTNL, exit batch of such module, and repeated acquire LTNL, release LTNL, and add latency by unregistered netdevice many. And this was improved by the exit batch LTNL. So exit batch LTNL factorize out LTNL and also unregistered netdevice many. And now each module just need to queue the dying network interfaces to the list, pass it to the exit batch LTNL. And then such network interfaces are removed in the batch. So this way, exit batch LTNL expedites NetNS dismantle by reducing LTNL lockdowns and removing network interfaces in a batch. Okay, the last section, NetNS LTNL. So currently there is 131 LT Netlink message handlers, and there is still 104 handlers are executed under LTNL, and 75 is do it, and 29 is dump it. So if you create some resources, it will be most likely serialized by LTNL. And taking a closer look at the converted dump it function since 6.9, now we can dump IP address, root, and IP routing table rule, and also neighbor entries. So most basic network resources can be now dumped without LTNL. So this is really nice. But if we look at the do it, the most of the message type or converted do it is LTM gets something. So there are only 5 LTM new or del something functions that actually creates or remove some resources. And in our case, we create 2,000 of network namespaces and a small number of network interfaces in each network namespace. So we issue so many LTM new something requests, and this is done concurrently for each network namespace, but most of them are serialized in kernel. So just setting up a single host takes 10 minutes or longer. So if we want to deploy a new host to production environment, then we need to wait at least 10 minutes. And this is a huge pain for us. So we want to more granular locking for LTNL. So that's the idea of, that's the background of PARNet and LTNL. Sorry. So the idea is very simple. So we want to replace the big LTNL with a small LTNL mutex to freeze a single netNS network namespace instead of freezing all of the network namespaces. But we need to know how big LTNL is. So it's serialized most lighter side of Netlink requests now, and also similar UAPI like ION control or CCFS are also serialized. But this is not the only code that are locked by LTNL. So I grab the LTNL lock. Anyone can guess the number. So how many LTNL scope in the Linux kernel? 10,000. 10,000. Okay. Okay. Stop that. There are 8,000. So, and 3,000 LTNL scope are under the net directly, and 500 are under the driver directly. And also there are 500 users of our such LTNL that guarantees the code is in the place the LTNL is held. And also LTN deliverance is a similar helper, and there is 600 users. And just scraping LTNL, there is 5,000. So 5,000 places are related to LTNL. So we need to replace over 800 of LTNL instances, but of course, it's impossible to replace all of them at once. So we need to gradually convert all of the LTNL scopes. And also, another question would be, how many netNS need to be frozen at the same time for each path? So for the first question, how to replace LTNL? So this is a plan to replace LTNL gradually. So first, for all LTNL scopes, we need to replace LTNL lock with LTNL net lock, and then replace LTNL helpers with PARNet and its corresponding alternatives. And then now I place LTNL lock inside the LTNL net lock, and then also added a config guard for the small LTNL mutex, not to slow down the each pass during the LTNL net conversion. And once the conversion complete, then we can remove all of the LTNL. Then we can remove LTNL lock in the LTNL net lock, and also we can remove the config guard. So the left code before conversion will look like the right one during conversion. So each corresponding helper accepts the netNS as the first argument. But there is no functional change unless someone enables the debug config. Okay, then let's think how to convert the do it function. So first, I added new flags, that is alias of the do it unlocked. So to indicate the do it is converted or under conversion. And we will use this flag to push Altiana down to do it. And most do it functions operate on a single network namespace. So we can convert it by adding a log for global data that is protected by LTNL or namespace by the resource, and moving message validation forward, and then add LTNL flag do it parnet flag and push down LTNL as LTN netlock, and then we can replace the LTNL helpers. So for example, LTM new address. This is the interface to manage IPv4 address on the network interfaces. So the IPv4 address is linked to a global hash table. So we need to namespace-wide the hash table. And IPv6.1 is already namespace-wide. So I mean, each network namespace has the hash table for IPv6 address, but IPv4 is not. So we need to namespace-wide it. And also, the hash table is used for garbage collection. So we need to namespace-wide the garbage collection too. And then we can place Altiana netlock and push Altiana down. And there is some do-its operate on multiple network namespace. That is LTM new link, the link, and set link. So then we need to freeze multiple network namespace. So we need to define clear locking order to avoid ABP deadlock. So recently we can define the locking order as a function by lock set conf function. And this time I implemented it as Altiana net comp logs. This can be used for used later for other helper functions. So the rule is the first initnet is locked, and then other network namespaces will be locked in the address async order. So this is because when destroying network namespaces in default device exit batch, we need to iterate dying network namespace and move some physical devices into initial network namespace. So the first rule would be useful in this case, and there's some other code lock in the same order. And then I implemented helper functions to freeze multiple network namespace easily. The LTNL nets stores multiple network namespace in an array, and also it has the number of network namespaces. And LTNL nets lock freezes nets from network namespaces from index 0 to length -1. And here's an example to explain how to use such helpers. So LTNL nets init initialize the struct, and then LTNL nets add accept the LTNL net struct and also network namespaces with its reference count bumped. And then LTNL netlock freezes the network namespaces from index 0 to the length 1, and unlock do the unlocks, and destroy calls putnet. And in the LTNL nets out, we sort network namespaces in the array so that LTNL nets lock can lock the network namespaces from index 0. Okay, so now the helper is ready, so we can think about how to convert LTM netlink, LTM new link. So there are 4 attributes that express the network namespace. So for example, if link netNSID is specified, the device is created in a network namespace that is the current network namespace or specified by PID, FD, or netNSID. And then new link is called for the current network namespace. So in this case, we need to freeze 2 network namespace. And if link netNSID is specified, then the device is created in the network namespace that is specified by link netns ID, and also new link is called for the same network namespace. And finally, the device is moved to another network namespace. So in this case, we also need to freeze 2 network namespaces. And there is some devices that create a peer device. So VS, VXCAN, and Netkit create another network interface, and that could be in yet another network namespace. So finally, we need to freeze 3 network namespaces. So for the first 2 network namespace that can be obtained from the LT Netlink message, we need to prefetch the network namespace before LT and netlock. So we need to move the message validation forward before LT and netlock. And for the peer network namespace, we also need to take the network namespace before LT and netlock, and also the network namespace can be fetched based on the device type. So we need a new ops method to fetch a peer network namespace. And also the ops is currently protected by LTNL, so we need to guarantee ops alive without LTNL. And in this case, this can be protected by SLCU as feedback from Netlink. And finally, we can release the SLCU. And also, when unloading the VS or when unloading a module, then we need to wait for the in-flight LTM new link to complete, and this can be done with synchronized SLCU. So to combat LTM new link, we can move message validation forward and then protect link ops with SLCU, and then finally add LTN flag do it parnet and push LTN down as LTN netlock. And LTN delink, this removes a network interface in either of the current network namespace or target netns ID. And what if the device has peer or child devices? For example, VS, VXCAN, Netkit, or MAC VLAN, IP VLAN. So does prefetching netns in LTN delink work? And the answer would be no. For example, MAC VLAN has this code, and if we remove a lower device, then the upper MAC VLAN device will be removed too. And the upper device could be in different network namespaces. And here we don't know how many network namespaces will be touched, and also the path is in the netdev notifier, so we can't add another LT netlock that could be result in a deadlock. So to resolve the issue, we need to do PAR-NetNS device on legislation, like queue network interfaces to a PAR-NetNS list, and then trigger PAR-NetNS on legislation work. So the work will look like this. It snapshot the dying network interfaces and do the on legislation. However, this change requires rework of LTNL unlock, and so this change must be done at the final stage of the conversion. I mean, this can be done only when LTNL unlock can be removed. So until then, we need to implement a glue code, like managing netns lists that has dying net device queued and collecting the device from the list in unregistered net device many notify. So when we convert LTN delink, we can queue dying network interfaces to PAR-NetNS list and splice the list in unregistered net device many notify, and remove kill list from ops delink and exit batch LTNL, then push LTN down as LTN netlock. But this change will reintroduce the latency that was removed by exit batch LTNL. So this option might be no-go, and we need to explore another solution to batching PAR-NetNS on legislation or something like another one. And last, LTM set link. This basically operates on the current network namespace, but it could move a network interface to another network namespace specified by PID, FD, or netns ID. And here the same question: what if the device has peer or child devices? the possible solution for that issue would be like this. Look up a network interface and the RCU, fetch all network namespace by yet another method, and release RCU and hold out in netlog, and then look up a network interface again. But another peer or child device could be added just before the second lookup. So then we need to look up again, and that would be really ugly solution. So we need to explore another option to avoid Altium netlog for peer child devices in the Altium setlink. So currently we have some challenges to convert Altium D-Link and setlink, but except for that, most of Altium users can be converted relatively easily because most of them uses just a single network namespace. So I'm planning to post this change upstream and proceed conversion under the config guard. And I hope I find a better solution for setlink and D-Link soon and complete the conversion hopefully next year. But yeah, that will require community help. So if you find Altium log in your code that you are working on, then please try to convert the Altium log to the Altium netlog. Yeah, that's all. Thank you for listening.
Can you go back to slide 46?
46, okay. This?
No, 46.
46, sorry.
Yeah, that part I don't really understand what's going on. So, isn't it adding a contention on initnet RT-Netlink?
Yes, exactly.
And then there's another question. Some CSFS entry just start to grab the RTNL with the RTNL trilock, and then eventually later are going to maybe call this function. So I'm wondering.
Okay.
For example, NetDevSim, I think, can create and delete net device from CSFS, which is kind of horrible.
Exactly.
So that's, yeah.
Okay. I need to think of solution.
Maybe we should first start from removing from NetDevSim the ability to create and delete net device from CSFS, because that's not, I don't understand why it's done this way.
That was Jiri wanted to do that because like he wanted to create the basically use the bus, like normal devices probe through the driver model, and that was the way to basically probe the NetDevSim through driver model. But we can do a asynchronous work or something like that. That should be fine, because NetDevs are supposed to pop up asynchronously anyway, so that might work. But NetDevSim is like, we can do whatever we want with it. I think we should focus on other things. Other questions? All right, thank you.
Thank you.
Some chocolates for you. Speaker gift for you. Thank you. Hello. I need to upload your slides. This, right?
Yeah, yeah.
So should I introduce your topic?
I can introduce it. No
Okay,
worries.
you can introduce it.
No worries. Can you just switch with arrows?
Yeah, just arrows or space.
Okay.
Or maybe not space. Don't touch space. Just
Okay,
arrows.
just arrows.
All right. Next is Jakub.
Yeah, hello everyone, welcome. I am Viaver Jakub, not the maintainer. I work at Cloudflare on kernel, networking, and BPF stuff, and today I want to chat about what makes the Panda set and the Linux network stack today. I have 5 war stories for you. Let's see if we can get through all of them, depending on questions along the way. I'll have a pause slot after each section for questions, but also feel free to interrupt me so we don't lose context. All right. Is it possible to have a proper loopback subnet for IPv6? So this needs no introduction. For IPv4, we have like 16 million local addresses. The first one is assigned directly to the loopback device, and the rest are present because if we have a special local route. But for IPv6, we get just just one local address, and that's due to no fault of the Linux network stack, of course. That's just what the specs mandate. But it's a problem for us, and it's not that we don't like Unix sockets. They're great for local networking. They're more secure. You know, it's harder to accidentally expose them to internet, and they are also as simple as it gets. There's no like routing code. You just shove packets from one socket to another. But we still need some local addresses, because some time ago we actually decoupled the public addresses from the addresses to which we bind our sockets by using socket lookup. And sometimes we have services which want to use the same local port, so we need more than one local address for that. Right, so we weren't naturally the first ones to think about that problem. There were some efforts in the past to make the situation better. But as far as we know, this didn't go anywhere. So we're stuck in the same situation. So what's the next best thing? It seems these are unique local addresses for IPv6. They're supposed to be used only within your private network. You are not supposed to root them. Yeah, there are a couple blocks there. Only one of them is actually designated for local use. So we're gonna see if we can use that unique local addresses just in a more narrow scope than the spec mandates. So there's this FD prefix there, /48. Within which we're supposed to choose a randomly generated prefix for a node. So that's what one of my colleagues came up with, and it's really easy to remember because it's just FD00 loopback. And we're gonna see if we can make it so it's locally assigned to our host and also can be only used within the communication on the host, not outside. Right, so following what IPv4 does, let's try to assign the first address from that subnet to the loopback interface. And if we try to do that, just naively, we'll notice that the scope is not what we want. But the IP tooling allows us to set it, so that's my fault there. Except it doesn't work. The scope is still global. And it's not that the tooling is broken, because if you capture Netlink, you'll see that the scope gets passed to the kernel as we set it. It's just that the kernel actually decides to ignore it and determine the scope by itself, because it follows another spec that says unless it's loopback or link local address, then it has global scope. Well, all right, so we can set the scope, but we somehow want to narrow down, scope it just to the host. So what do we do? So we can end up in a similar setup as by default in IPv4, where loopback addresses are treated as Martian. when they are coming from other devices. Well, I guess we can work around with a couple of firewall rules. All right, so we have one local address. What about the rest of a subnet? Well, we have any IP, fortunately, which allows us to assign a whole subnet to our host via a special local route. And works great because we can then communicate over loopback using these addresses, and the network stack is going to respond to pings, except you won't be able to bind to them, right? I can bind to the first address that I assign directly to loopback, but if you try to bind to any other address, you'll get address not available error. Why is that? Well, it's because bind actually checks if the address is directly assigned to to one of the network interfaces, and if it's not, we're just gonna fail there. So we can't make that routine happy, but maybe we can work around that. There's another check just before that with which we can short circuit the logic, and it will allow us to do that if we use either the IP non-local bind sysctl or the free bind socket flag. There's also IP transparent, but that's privileged, so we're gonna ignore that. So we have a tough choice here to make. We either use the pernet NS sysctl and risk it so that our applications, if you misconfigure the address, you won't get an error when binding. The address might not be assigned to an interface, or we make everyone else trying to use this fake IPv6 loopback set a socket option. So that's all right, but not great. Can we do better? Well, we can already set socket options from BPF today, but we can't set free bind. But maybe we could, allow that, and then we already have kind of an early bind hook for BPF, so we could check if we're binding to our loopback subnet and set it automatically for users, perhaps. That would give us a finer policy than what we have today. All right, any questions, comments to that? Okay, moving on then. How TS recent timestamp resolution can lead to port exhaustion. Okay, so here's a short experiment. I want to make an egress connection to a particular host, like 1,000 times in a row, open it, close it, and I want to always use the same local address for connecting outside, right? So in our first experiment, I'm gonna manually select the local address with bind sysctl, and if you do that, yeah, it will work, every time. But now, if we make a change here and we also connect to the same host, we wait a little in between, but this time we're gonna let the kernel find the free local port for us, but we're gonna tell the kernel that there is only one port to choose from, right? So if we try to do it this way, well, then that will mostly fail, right? We'll just succeed like a dozen times there. And if we take a look like when do we actually succeed, we'll notice that we succeed about once a second to reuse that local address. So what's happening there? Well, a quick refresher from TCP. Like when we're tearing down the connection and we're the ones actively closing it, then when everything has been already sent and received during tear down, so our fin has been hacked, right? And we have received a fin from a peer. Then we're gonna actually wait a little bit still, so just in case our peer has not, received our ACK to their fin, in case it retransmits their fin, so we can discard this old segment and it doesn't corrupt a new instance of the connection, right? And we wait for 2 maximum segment lifetimes, which under Linux the default is 60 seconds. So that's not what's happening here, clearly, because we were able to reuse our time wait socket after just 1 second, right? And that's because there's something called TCP extensions for high performance. which says that if you're using TCP timestamps, which your peer reflects, right, you can use that to detect stale segments in the new reincarnation of your connection, right? And it's something that has been implemented in Linux network stack for more than 2 decades now. And it actually was done for the very reason we wanted, so to prevent port exhaustion. Yeah, you need to actually enable it. By default, it only is allowed for loopback, but we consider ourselves technical experts, so we do that. But if you dig into the code, the function that actually decides if you're allowed to reuse a time-wait socket uses a 1 Hz clock. So even though we have millisecond timestamps, well, we will actually only be able to reuse it after 1 second. But you know, if I try to do a DNS query over TCP from one of our servers to Google, for instance, from send to the last tag, it takes me like 5 milliseconds. So waiting 1 second to then reuse that local address to make another connection, that seems very wasteful these days. Right, so we're wondering if it's something that we can improve. Like very naively, I just tried to switch that 1 second clock to 1 millisecond clock to kick off the discussion on that. Right, and we got some valuable feedback from our TCP maintainer there to reuse existing timestamping infrastructure, and also 1 millisecond, that's too aggressive, something to rethink. And I'll be circling back to these patches after the conference, so you can expect some updates. All right. Any comments? All right, moving on. This one will be short and fun. UDP segmentation offload does wonders for throughput, but can you always use it? What is UDP segmentation offload? Well, if you have a sequence of UDP datagrams that you would like to send out, you can actually pass all of them at once to the network stack. So they travel through the network stack together, and in this way you amortize the cost of executing all the code that we need to do. And you can leave it, offload it to your NIC firmware to actually chop them up into UDP, into IP datagrams, and also fill in the L4 checksum for you, because, well, that covers the payload. And you know, when you're serving traffic over QUIC these days, that's just a must-have feature from performance point of view. So that is something that we have been using happily in our patched Nginx, just passing large payloads, yeah, and datagrams will happily traveling over the network. But we noticed that from time to time we're getting an EIO error from the network stack, and when we dug in and to see when that was happening, well, that was actually happening when our egress device was a TON device. So what's going on there? Well, you see, to use the UDP segment API, your network device has to support certain features. One supported scenario is where your network device is able of both computing the L4 checksum and doing the UDP segmentation in hardware. Or alternatively, the network stack, if your device can't handle chopping up UDP into segments, will do that for you in software, but the device still has to compute the L4 checksum. Everything else outside of these sets, well, that just generates an EIO error. All right, but when we dug further into the GSO code, we noticed that actually the core GSO code that does the USO fallback, it can compute the checksums as well. I mean, there will be probably some performance penalty there, because as I was told, The data cache will be probably called by that time, but still, you know, as an application developer, why should I care through which network device my traffic egresses, right? So maybe instead of throwing an error, we can just handle that gracefully and do it all in software if our device does not offer anything, checksum computation or UDP segmentation. Right, so that's what we set out to do, and it's available, and it will be available in 6.11, right? Yeah, life is not that easy, and of course there were corner cases there. Well, first of all, what's that? Like, what if my device says, I offer UDP segmentation, but I can't compute the checksum for you. And you can misconfigure your device, virtual device like that. Well, that's obviously a nonsensical configuration, so we had to fix that up, and so it's not possible to do. And then there's another corner case, like your device can advertise that it can compute L4 checksum, but if there are IPv6 extension headers present, we're actually not going to use that capability. So then, well, we can't offload USO either, right? So we had to disable that as well. Thanks to Willem for patiently reviewing all my attempts at getting it right. Yeah, any questions there? Okay. All right, moving on. Why sourcing return traffic when using BBF socket lookup is tricky for UDP? So as I mentioned earlier, we don't bind our sockets to the public-facing addresses, which we use to actually source the traffic to the internet these days. And there are some caveats with that. So when the datagram comes in, we'll check if it's a local IP assigned to this host. If so, we're gonna pass it on to the socket lookup in L4 layer, and in there we're gonna have a BPF program running, which will actually find the socket which will receive this datagram, right? And that socket doesn't have to be bound to the same address as the destination address in the datagram. The application then can read the message, and it can recover the original destination address via an ancillary message. And that is needed so that, you know, when we source return traffic, then we can tell the network stack from which address we want to source back the reply, right? And on return, we're going to check, like, are we sourcing traffic from a local address? And if so, we're going to just send it back out to the internet. Right, but you see, our socket, it doesn't have to be actually bound to the same local port number as the destination port for the datagram. That is completely allowed. But in that scenario, if we try to send return traffic, well, we're going to generate a datagram that has a source port number which is not expected by our peer. So what can we do there? Well, we thought, well, maybe we can improve that and actually have another C message, or maybe a different kind of C message, where we are able to also specify a source port number in addition to the address. We'll still check if this is a local source address we're using, but we can't just allow you to source traffic from any port because, well, that might be used by another socket, right? So maybe we can do a reverse socket lookup to do some sanity checking there, and only if that socket lookup returns the same socket as you are using to send the datagram, we let it pass through. Any problems with that? Well, we don't have a lot of context, luckily, in the socket lookup, so almost everything is available, should be available on this reverse socket lookup. there is the ingress interface index, and it's not clear what to populate it with, so that's an open question. Right, so yeah, my friend Tiago is actually working on this, and we managed to get out an RFC to kick off the discussion. So if yeah, if you have any ideas there. Right, any feedback? Okay.
I want to ask the question is, can we implement something like the NAT in the BPF? Like we use the BPF format to maintain some status. So we can rewrite the POC, like the issues you are point out, because the POC is not the same, right? When you send back the packets. So can we implement something like the NAT in the BPF to do some transfer layer here?
Sorry, what's an NAT?
Because you are talking about the POC is not the same, right?
I didn't catch that.
Yeah, the POC is not the same as the service. Yeah, so maybe we can implement some transfer layer in the BPF.
Okay, yeah. Right. I got it now. Right. Yeah. I mean. Yeah, you could potentially rewrite the port in your net or in your there's an egress C group egress hook potentially. We haven't tried that.
Oh.
But yeah, maybe that's a way out.
Oh, okay, thank you.
Yeah, but of course that would come with some additional setup for your application, and you would have to have state in two places your configuration.
Okay.
But yeah, good idea. I haven't thought about that.
So this is a possible solution. Okay.
Potentially, yeah, I would say so.
Oh, okay, thank you.
There's one more.
I'm throwing Martin.
So, but I think at the point you need if from the slide, from the next slide.
Next one. This one or
the earlier one that you set the C message?
This one?
Yeah, maybe in your patch. I think you need in the patch you need to set a C message to tell which port or address you want to send from. Right? That is the information you need the user space to tell you.
Yeah.
And that's the information that the BPF program don't have at that point.
Yes. It would have to be somehow. That's a very good point. Yeah.
Yeah, but I think I asked in the patch, but I think I asked. I didn't know whether he replied or not. But does it have to run the BPF program to again, because the user space has already specified what port or address it need to send from, right?
Right, but you know it's just for so you don't start sourcing packets from a port that is serviced by some other service, right? I mean, I get what you mean with. In theory, you are able to bind a socket to any port, right, and do it anyway, because that's the workaround we've been using today. We just have a UDP socket for every port from which we need to source traffic, and that's allowed, right? So, yeah, maybe it's an overkill to do it on reverse. I don't know. That's why we wanted to have this discussion. Is the idea sound or yeah? Any other questions? Okay, I think we have time for one more. So let's see if we can make it through this one. All right, how can early DMAX get in the way of forwarding traffic? Right, so we have this setup in production where we have an application that uses a TON device, and it just injects packets that get routed out of a physical device to the internet. And on the same host, we also have another application that it just uses regular TCP sockets. It creates a TCP socket and sends, TCP segments through the whole network stack. And the important thing is that they both source traffic from the same address assigned to the physical device. So the challenge we have here is like how do we set it up so that there is no port clash when we are sourcing traffic between these two applications, and how can we make it so the application that uses regular TCP sockets, it can still use the kernel facilities for finding a local port, so it doesn't have to choose it manually and kind of cooperatively with the other app agree on which port is in use and which is free. Right, so we were thinking like, oh, is there a way for the application that uses tunnel to TUN device to inject traffic to reserve a local TCP port somehow? And it turns out that you can abuse TCP fast open for that. It works. I'm not proud of it, but it works. And it's probably the first use of TCP fast open for us. You're able to create connect a socket, reserve a local for tuple, but not initiate the three-way handshake. If you inspect it with SOCDIAC, it will show it's in a send state, but that's a lie. Actually, nothing has been sent out, but the local address is assigned, and that's what we've been looking for. All right, so that's so let's use that. Right, we first create this port holder dummy TCP socket. We know the port is now reserved, and we inject traffic through our TUN device. And that works, but on return, what we notice is that the return traffic, so our SYNAC in this case, it's not getting through. It's getting dropped by routing. So when we dug into that, what we found out is that when SYNAC comes in, very early on the ingress path, we have early DMAX, which is this optimization that checks if there is an established socket to which we can deliver the packet. And if so, it's going to assign that socket to a packet. And of course, it finds that placeholder TCP socket that we created. But when we pass this SKB to routing, because we have special routing policy that like overrides local delivery, we found out that like forward path is not happy with that. Like if you have a socket assigned to your SKB, then forward is just going to drop it on the floor. Right, so how can we work around that? Well, we can kind of hide our TCP flow from early DMAX because the pre-routing hook is earlier than early DMAX, and we can rewrite the destination there. That's one way we found out we can solve this. Or a nuclear option where is just disable early DMAX for TCP, right? Then we don't have a problem at all. And actually, my colleague ran an experiment in one of our data centers. How much do we hurt when we do that? And it seems it's like 0.5% of CPU time. So if we are able to recover that elsewhere, that's something we're considering actually doing. But ideally, we would like the sockets to be able to opt out of early DMAX, so they're not considered by early DMAX as candidate for packet delivery. That would solve it for us, and would be a finer control than what we have today. Yeah, thanks to my colleagues at work who actually worked on this. Right, any questions to that one?
The fast open trick, I don't understand why it's adding a route on because the early DMX need the incoming route to be stored in the socket. There is a socket field to hold the DST. But so if you just create a fast open socket without anything sent and received, the cache shouldn't be set. So I don't really understand why there is a problem.
I don't know either. I'll have to go and dig that out for you.
For me, early DMX only works when the first packet is received. Then we cache the DST once it has been
that's correct.
done here. So here, if you just create a dummy TCP socket, the cache shouldn't be set.
Yeah.
That's the thing I don't understand. But
right. Is it possible that the injected traffic created that?
Maybe.
I'll have to investigate. Sorry, I don't. No idea.
Any more questions?
All right. Yeah. If you have any more questions or would like to chat about this, you can reach me at this email address, or I hang out on the kernel mailing list. Thank you.
All right. Thank you. Is that a little gift for you? Thank you. Thank you.
You can open the PowerPoint, that's better.
Or we can try.
If that's possible, I uploaded both, but I don't know. If it's not possible, then...
I need to upload it to the system so we can see.
Yeah, the second one.
It doesn't show up in the selector thingy.
Right there, no? PowerPoint?
Oh, right. Underestimated this.
Let's see if it works.
Converted. Use your timer if you need it. Progress is being made. Yeah, okay. Alright, it's gonna pop up. So I'm into you and yeah. Start your timer. Oh, let me say, wait, because this is gonna take a minute.
Sorry.
That's good. All right, last talk before lunch is Joe is going to be talking to us about non-temporal rights.
All right, I'm going to get started. So, hi. This talk is called Experiments with Non-Temporal Rights and Application Architectures. So, before I get started, hi, my name is Joe. I work at a company called Fastly, and it's important for you to know that my opinions are my own. I am not an x86 expert, but I do know a little bit about x86. And since this is the networking track, and we're going to talk about networking eventually, before we can talk about networking, we need to talk a little bit about CPU caches. So the next couple slides are going to be, maybe for some people, really like sort of basic information about CPU caches. But I want to start from there and then build up from that to talk about non-temporal rights in the networking stack after. So this is sort of like your typical memory hierarchy diagram you'd find on the internet. I just downloaded this from some random website. And all this is really trying to explain is that there are different sizes of memory that have that are at different speeds, right? So like at the very bottom of the diagram, you have very large disks that are very slow, and at the top of the diagram, you have things like CPU registers that are very small. And just below CPU registers, you have your L1, L2, and L3 cache. And this is just to illustrate the idea that the CPU cache, the L1, L2, and L3 caches are very precious. They're very fast, but there's just not a lot of it to use. You need to be careful with how you use it. If you want to get a better understanding of the size of your caches on your system, you can run this command line tool on your Linux machine, lstopo, and you can have it output a PNG file, which will show you what your CPU cache is and your CPU layout actually looks like. And I find this particularly helpful because I like looking at graphics. This is an output of a graphic from an AMD Zen 2 system that I have access to. And you can see in this diagram on the bottom, there are 4 CPUs that are dual core, and you can see that each of those CPUs has an L1 data cache of 32K, an L2 cache of 512K, but all 8 of the cores here share a single 16 megabyte L3 cache. So this is the type of output you'd get from running lstopo, and this is really useful if you are trying to tune your application and trying to figure out like what sizes you want to use for different buffers and stuff. lstopo will help give you an idea of the size of the caches on your system. So lstopo is really dope. So there are 2 important properties of data access patterns to remember to maximize the benefit of CPU cache. And this might seem like really, really basic, but I think it's really important to start with this and then build from this to talk about non-temporal rights later. So the 2 important properties to remember are spatial locality and temporal locality. And I'm going to use a really common example that you've probably seen before if you took like a CS class in college or something. The standard example of this is just your like 2-dimensional array access in C, where you compare the access times of row major order versus column major order. And this is just like a really basic example, but I think this example really highlights like the 2 extremes actually really nicely. When you're accessing a 2-dimensional array in row major order, right, you're iterating through all the elements across a row, and so you're getting spatial locality because each memory access is ordered. And so like, the first access may be a cache miss, but the following accesses will presumably be cache hits, obviously depending on the size of what you're accessing and blah, blah, blah. And you're getting temporal locality because you're accessing those things very quickly, so there's a really good chance the data is still hot in the cache, versus column major order where you're doing the opposite, where you're working against the CPU cache. And the way this looks in code is just really simple, right? Like you just have your 2 for loops and you're iterating across a row, and then you have a column major order, you just flip them around, so now you're just accessing things along columns instead. And what this looks like graphically, again, I like pictures. What this looks like graphically, if you look at row major order, every color change you can just assume is a cache miss. So like in row major order, right, when you access the things in light blue, the first time you access it, it's a cache miss, and then the rest of those are cache hits. And then when you access the thing in green, it's a cache miss, and then the rest of the greens are cache hits, and so on. And in column major order, you're constantly cache missing. And so you can run lots of like really interesting memory benchmarks using an open source project called TinyMemBench that has lots of really interesting memory related benchmarks that use different instruction sequences and different sizes and access data differently to give you a really interesting perspective on how your system performs with different access patterns and different x86 instructions and so on. I ran just a really simple micro benchmark just to highlight this point about row major order versus column major order. You can see this is just on this AMD Zen 2 machine that I had. I pinned this sample program to a particular CPU. When I ran it in row major order, it completed in 46,000 milliseconds, and when I ran it in column major order, it completed in 94,000 milliseconds. So you can see that row major order is obviously a lot faster. And row major order is more than 2x faster because data accesses have spatial locality. You're accessing data that's near other data, right? So like your first access is a miss, and then you pull the data in, and then you're accessing things that are now in the cache. And you also have temporal locality because it's a tight loop, and so you're accessing things very quickly. The app is pinned to a CPU, so presumably the data is going to be in the L1 or L2 cache when you're accessing it, and so you get both of these 2 things. But what if we know that we don't need temporal locality? So if we know we don't need temporal locality, it'd be really nice to avoid the CPU cache evicting in-use data in exchange for data we know we won't touch again in the near future. I'm going to repeat that just because, like, the first time I thought about this, it confused me. The idea is that, like, you have a program and you're going to touch data right now, but you know you're not going to touch it again in the near future, and so you don't want to disturb the contents of the CPU cache. You don't want to evict data that you are using in your app in exchange for data that you know you're not going to use again for a while. And we'll talk about, like, situations where this might occur later. And if you're, touching data that you're not expecting to use again in the near future, well, when you do that, the CPU cache is thrashed unnecessarily. Useful data can be evicted from the cache in exchange for data where there is no locality benefit whatsoever. So it would be nice to avoid that. And using a set of instructions called non-temporal stores, you can actually write directly to RAM without disturbing the CPU cache. And on x86, there are a series of instructions you can use to do that. Here are some that you might see in the kernel or in other places or in Tiny Membench. Like, there are lots of places where these instructions pop up. And these things allow you to write data directly to RAM without disturbing the contents of the CPU cache. So that's cool. But what does that have to do with networking? Well, if you run ethtool and you grep the output of ethtool-k, you'll find this option called tx no cache copy, and the default is set to off. And I was really curious about what this option is and what it's used for and why it was introduced, and so I went sort of deep down this rabbit hole of tx no cache copy and its origins. And it turns out that ethtool allows you to enable no cache copies from user space on transmit. And I'm going to show you a diagram of what this means in both cases, when it's on or when it's off. So what does that mean to turn tx no cache copy on or off? So let's start with the default, tx no cache copy off. When tx no cache copy is off, what happens is you have your, sorry, the animation didn't work, sadly, but basically you have your data cache, which would all be green in the beginning. You have your user app. Your user app does a write to a network socket. That write does a copy into a kernel buffer. And then now that data that you're about to transmit on the network ends up in your CPU's cache. That's what the purple lines are at the top. Originally, those would all be green. But the data that you're about to transmit on the network disturbs the CPU cache, lands in the CPU cache, and then you do a transmit from the NIC. And you may not actually really want to do this because you may not actually want to disturb the data in the CPU cache in exchange for data that you're about to transmit on the network, right? Like, you're writing this data out to the network, you're not expecting to touch it again, so why disturb the data in the CPU cache? TX no cache copy on is exactly what you would use to avoid that from happening. So a diagram of TX no cache copy enabled, you have your user app, it does a write to a TCP socket, and it doesn't disturb the data that's in the CPU cache. So the data that's in the CPU cache stays there, you do this transmit to the network, and everything is good. So with TX no cache copy enabled, and assuming the kernel or the driver don't touch the data, the CPU cache is not disturbed. And this can lead to performance increases in certain situations. Important application data is kept in the cache, and there's a reduction in memory bandwidth consumption. I looked up when this was written and who the author was. The original author was Tom Herbert, and this was added to the kernel back in 2011. And in the commit message, there are some numbers which I added emphasis on myself so that to call them out more easily for you all to see. But you can see that in the commit message, Tom is explaining that the 95th percentile tail latency was reduced significantly by using TX no cache copy. And so the original author noted a 45% improvement in P95 times, which that's pretty cool. But this option only affects TCP. It's interface wide, so it affects every single connection on the interface. And it might be undesirable in some situations, like, I don't know, software KTLS, or if you're doing other operations that you might actually want data locality. This switch is just like an all or nothing. It's basically saying like everything on this NIC is not going to disturb the CPU cache, or everything on this transmitted on this NIC for TCP is going to disturb the CPU cache. It's either an on or an off, and that's all you get. And I think there are potentially other types of hardware, other kernel features, other application architectures, other protocols, other address families. All these things invite really interesting use cases that the existing TX no cache copy interface-wide TCP-only mechanism don't allow you to take advantage of. And I'm going to show you one of them right now with some really surprising performance numbers, one that we use ourselves. So here's an example of a common application architecture pattern you're probably familiar with. You have, in orange, that's your computer. And in red, you have your backend app. And in yellow is your reverse proxy. And they talk to each other over a Unix socket. And client requests come in. And the basic flow, what typically happens in this architecture setup, right, is like a client request comes in, the reverse proxy reads that request, it writes it to the Unix socket, the backend app reads that request. The backend app does some, I don't know, maybe makes like some queries to a database or something, generates a response, and then the backend app writes the response back to the Unix socket, the reverse proxy reads that response, and then writes it back out, and that's how you get your server response. That's like a fairly common application architecture with two things that talk to each other over a Unix socket. And by doing this, there's lots of buffers being read and written, and so a lot of CPU cache is being churned. Even for things like plain text HTTP, where the reverse proxy doesn't really do that much, like maybe it just throws a couple headers on, and that's it. And it seems kind of wasteful to be churning through CPU cache when you don't necessarily really need to if you're just moving a body, like some HTTP response body from a backend app through a reverse proxy. So I started to wonder, is there a way to do this with less data movement, thus less cache churn? And is there a way to do this for specific connections and for things that are more than just TCP? And the answer is, it is possible. What if you were to extend send message to allow the application to decide when a non-temporal write is necessary or not? So instead of doing it interface-wide, you just say on a specific send message for a particular socket that like this write should or should not be, should or should not have temporal locality. So I implemented that. I submitted an RFC to the mailing list. This was actually a while ago. I got super busy, so I didn't end up like trying to push this through to actually get this merged. This was probably like, I think I submit this, when was this? June of 2022, so a couple years ago. This adds a new flag called message NT copy to send message to allow you to do this, and it supports more than just TCP. It supports TCP, supports Unix sockets, supports UDP sockets, and so on. And the idea behind this all is that the user app knows like when it will or won't need temporal locality. You support more than just TCP, and you can preserve the CPU cache contents and common application architecture patterns. So I'm going to show you one specific use case with like really disproportionate benefit. So plain text HTTP1 benefits from this like just totally disproportionately, so it makes for a good demo. So imagine the same diagram you had before when we decide to redesign this thing to take better advantage of the CPU cache. Plain text HTTP1 request comes in to the reverse proxy. The reverse proxy reads that request, writes it to the Unix socket. The backend app reads that request, does its processing, generates the response. Right. The backend app though knows that the request is plain text HTTP1, and using the RFC that I posted to the mailing list, we can avoid dirtying the cache and we can save memory bandwidth by having the backend do a send message to the Unix file descriptor, telling it to do a non-temporal copy to not disrupt the CPU cache. And so, sorry, the animation didn't load. This was going to be like a step-by-step thing, but I'm just going to try to talk you through it. Basically, in this re-architecture, what ends up happening is the backend app does a non-temporal write to the Unix socket. The reverse proxy then uses splice to move that data out of the Unix socket into a pipe buffer, so keeping the data in the kernel but not touching it. And then the reverse proxy will use a non-temporal write to write out whatever headers it needs to write to the client. And then it'll use splice to actually take the response body and have that DMA'd via the NIC out to the client. And so you can re-architect your system to do this, to minimize the amount of cache churn and the amount of cache thrashing you're doing by copying data back and forth. And doing this has some really surprising results, or at least surprising to me. But there's a couple key things here, like the backend knows the request is plain text, the backend uses a non-temporal write to the Unix socket, and the reverse proxy, like I said, uses a non-temporal write for the headers and uses splice for the body. And so in this particular scenario, we avoid disrupting the cache because the NT write from the backend to the Unix socket doesn't disrupt the cache. The non-temporal write from the reverse proxy to the client for the headers doesn't disrupt the cache. And the splice of the pipe buffer to the client also doesn't disrupt the cache. And you save, not only do you not disrupt the cache, but you also save a lot of memory bandwidth by doing this. And so the CPU cache remains as undisturbed as possible. Hot application data stays resident. These are all good things. You might be asking, like, what about TLS? And I'm going to get to some benchmark numbers in a minute that are pretty crazy looking. But what about TLS? So I would argue for TLS, you could have something similar, like the backend app could still do a non-temporal write to the Unix socket, and then when the reverse proxy is actually ready to do TLS, it can just do a regular read, and then that read will populate the cache with the data, and then you can do the TLS, and then you can do the non-temporal write when you're transmitting to the client. That's one possible implementation of TLS. There's lots of other different ways you can do it depending on your hardware and what you care about and so on. And in the TLS case that I just showed, right, like the backend app preserves the CPU cache as much as it can. The reverse proxy wants the data in the cache, so that TLS will be fast. But you can still do a non-temporal write when you do the transmit. And there are lots of other cases where non-temporal flexibility, in my opinion, I think are really helpful. Like if you're using KTLS, which is like hardware offloaded, you might want non-temporal writes in certain situations with Quick. It really depends on like your application, the platform you're working on, what features you have, and so on. And I think like the whole point that I'm trying to make is that having a global switch that only affects TCP is better than nothing, I guess, but having more fine-grained control, in my opinion, makes it possible to build like much more interesting apps. So I'll give you some benchmark data when I tested this. I wrote so there's a micro benchmark that's floating around on the internet that you can use called Unix Thread, and it just measures the amount of data that two processes can transfer over a socket. I modified that to basically use. So what ends up happening is that you run this micro benchmark and it calls fork, and the parent process does a non-temporal write to the Unix socket, and then the child process does a splice from the Unix socket to a pipe buffer, and then from the pipe buffer to dev null. And there's lots of different command line flags you can use to benchmark different sizes and use like different things. And I posted the results of this actually in the RFC. So this is from the RFC. This is using just this AMD Zen 2 processor that I had available. I'm setting different buffer sizes, and you can test whatever buffer sizes make sense for you. From the RFC, just to give you like an example, this is really similar to the numbers that Tom posted originally in 2011. If you take this micro benchmark and you pin it to two CPUs on this Zen 2 system that do not share an L2 cache, using the message NT copy method results in a 43% increase in throughput. Which is really similar to what Tom posted. Tom posted like this huge increase, like I think it was like 45% or so for P95 times. Getting a sort of a similar like order of magnitude, a 43% increase in throughput, which is pretty surprising. And then if you try the same test, but you pin the parent and child process to CPUs that do share an L2 cache, you get at least with the numbers that the buffer sizes I was testing, I got a 33% increase in throughput. So that was all pretty interesting. Like, the numbers definitely seem really large and bizarre. And so it was not too surprising to me that I got this response to the mailing list when I posted this. I posted this, and then somebody was like, somebody named Alviro, I don't know who this person is, but they write a lot of kernel code, and they were just saying, like, you know, are you sure you're not testing like a KSAN kernel? And that, you know, and they also mentioned it in their response, which was really perplexing to me, was like, wouldn't it make sense to cover the memcopy side as well? And I wasn't really sure what they meant. I wasn't sure if they meant like memcopy in userland or not, or they meant memcopy like in the kernel or what they were talking about. But we'll come back to the memcopy bit in a moment, because I think that's actually really interesting. But the micro benchmarks show a really huge improvement, but who gives a shit about micro benchmarks? What about an HTTP workload? What does that look like? So an HTTP benchmark using a reverse proxy and backend architecture pattern, where the backend app just responds with like a response body with plain text HTTP1. Same setup that I was showing you before, right? There's just like the reverse proxy that runs, talks to the backend app over a Unix socket, and we try just benchmarking this with HTTP1. What do we get? This graph is probably kind of hard to see if you're in the back, so I'll explain it to you in words. But basically, the baseline throughput is about 170 gigabits using the normal copy mode. And then when I enabled the Unix, the NT copy into the Unix socket, 170 gigabits increased. The 170 gigabit throughput increased to 245 gigabits of throughput. And you'll also notice there's like a large dent in the CPU usage graph on the top. And if you look really closely, you'll see on the bottom that for baseline and TX no cache copy enabled are both there, and there's no difference when you turn on TX no cache copy in this case. And the reason for that is because, remember, we're using splice on the output path now. We're not doing a write on the output path. So enabling TX no cache copy when you're using splice on the output path doesn't do anything, and this test like verifies that that's actually what's happening. So yeah, TX no cache copy on doesn't help in this benchmark because the reverse proxy is already using splice and it's not touching the data on TX. So using message NT copy does help when writing into the Unix socket because it preserves the cache and it generates less memory bandwidth traffic. And just like to summarize, like in the HTTP1 benchmark that I was running, I went from 170 gigabits using a normal copy to 245 gigabits using a non-temporal copy. But that's on the hardware that I was using. That was on my AMD Zen 2 machine. Your hardware might be different. You might be using an Intel machine with DDIO, and that might affect the results because with DDIO, you can do DMA directly from the cache. So it really depends on your hardware platform, your architecture, what you're trying to do, and so on. And that, I think, just adds to the point that I'm trying to make, which is that maybe it's better for more fine-grained control over when copies should have temporal locality or not. Maybe an interface-wide switch is not the best way to go. I don't know. So what about DDIO? I just mentioned that. DDIO allows DMA directly from the cache, thus non-temporal writes may not be useful if buffers are sized properly. This is CPU and application specific, so users should be aware that DDIO will affect their results if they try to run these benchmarks. If your CPU has DDIO support, I strongly recommend reading this paper that I linked to in the slides. This paper is really, really interesting, and it talks about cases where DDIO can actually work against you if you have a high-speed NICs. And it's a really, really, really fascinating paper. I strongly, strongly encourage you to read it if you are interested in this. So if this is true in the kernel, right, that like controlling non-temporal writes and controlling temporal locality makes a measurable difference. What about memcopy and userland? And that's what I think Alviro was asking. I could be wrong, but that's what I assumed they were asking when they were posting this question on the mailing list. And the answer to the question about what about memcopy and userland is actually pretty simple, which is that glibc has had a tunable for memcopy and memmove for a really long time. So in glibc, if a copy is above a certain size threshold, glibc will use a non-temporal store instead of a regular store automatically. And it turns out actually in 2020, glibc was updated to change the threshold for AMD machines. For some reason, I don't know why, maybe like somebody at AMD can explain why, but for whatever reason, AMD machines seem to be particularly sensitive to this, and this is why somebody from AMD submitted this change to change the threshold on when a non-temporal copy would be used on the AMD Zen architecture. And stumbling on this is what sent me down the whole rabbit hole of like, well, what if we tried this in the kernel, and what if I tried this into the Unix socket, and so on and so forth, and that's how I got the crazy benchmark results I got. More recently, though, Noah Goldstein from Intel has been investigating non-temporal writes for memset also. This is again in userland. And Noah added this tunable for non-temporal memsets. So depending on the size of the memset, recent versions of glibc will automatically use a non-temporal store when doing memset of certain size thresholds for particular Intel CPUs. I saw this go by in the mailing list, and I emailed Noah, and he was like, well, I work for Intel, and like I ran these benchmarks. I don't have any AMD CPUs I can test. Do you? And I was like, oh, I do. So I tested this on some AMD CPUs, and we collaborated a bit, and then I submit this change for glibc that adds a tunable to glibc for AMD machines when you're doing memset, right? Like I was just talking about memcopy, this is memset, slightly different, right? But the same idea applies. And if you're really curious, Noah's been compiling this huge spreadsheet of memset performance data across lots of different CPUs, and you can see really clearly where the non-temporal threshold is for different Intel and AMD CPUs. He and I have been working together on this, where like I've been gathering data from different AMD CPUs I have access to. He's been gathering data from different Intel CPUs he has access to, and we're finding like the specific spot on where a memset might be better if it's non-temporal or not. So anyway, in conclusion, I think that TX no cache copy is useful for a very narrow set of applications. I think, in my opinion, that applications probably know when they do or don't need temporal locality better than an administrator just saying like globally for the entire NIC, like everything is non-temporal or not. glibc itself already has tunables for non-temporal writes for memcopy and memset, and the micro benchmarks that I showed you show improvements show a performance boost when using non-temporal copies in certain application architectures. And so maybe send message should be extended to allow user applications to decide if their writes should or should not have temporal locality to lots of different types of things, not just TCP sockets. And that's all I had to talk about today. I can take questions, but keep in mind that the more questions you ask, the less lunch you get to eat. So.
I have two questions. One, did I understand correctly that you measured the improvements even without a competing application that makes better use of the cache? So just looking at one application that bypasses the cache?
Yeah. So. Sorry, can you repeat the question? That there's one application that bypasses.
So the idea is to not trash the cache because other data might make better use of the cache or other applications, but you didn't talk about another application. You just run the benchmark. So there was no other application, and you still see an improvement.
Yeah. So there's other data that application uses that is not necessarily transmitting to the network, like internal data that the app needs, like for running its event loop or for keeping track of like connections that are coming in or whatever. So that data stays hot in the cache, but the transmits like to the network, you can avoid evicting data that you can imagine like the event loop in this app has a bunch of state that it needs to keep track of, and you can keep that hot in the cache if you don't evict it by doing a regular copy into the Unix socket. But in general, with our apps, we generally try to pin apps to CPUs so they have exclusive use of CPUs, so we can guarantee that like the cache will be hot with data that those applications actually need.
Okay, so I might see more throughput if I use the ETH tool command and run netperf or iperf or something. And
you might. I mean, it depends on the exact test that you're running. I mean, that's what I think Tom was showing in his original commit in 2011. Was just for regular TCP connections that I think he was running just like TCP RR or something back then. So presumably, if you reran the same test that he was running and you turn TX no cache copy on and off, you would reproduce the results that he got. It's up to you to decide whether or not that specific benchmark is like relevant for the type of application you're running or not.
Okay, thank you. And the other question is, have you considered the other data paths like sendfile or something like that?
Yeah, I've considered sendfile. There's a lot of reasons why sendfile is tricky for a variety of reasons, but one reason is, when you call sendfile, well, so first of all, the data might not be on disk, it could be in RAM, but also sendfile, you don't know when the receiver has actually, like, sendfile finishes and returns, but you don't know that the receiver has ACKed all the bytes, so you don't know if you can reuse the data on, like, if you can overwrite the data on disk or not. So there are complications involved with using sendfile, basically. It's not as simple, I think. But yeah, like, the short answer is yes. I've considered sendfile. Yes, I just think it's complicated.
Hello. So does the non-temporal flag travel with the SKB? Is it transferred to the SKB? So if you have any BPF on egress, like C group egress or maybe TC egress, they know not to pull in the SKB data by accident and thrash the cache?
Yeah, so I didn't make any modifications to any of that. So we don't really use like a lot of stuff on the egress path. So I mean, we have just like some basic like pacing and stuff like that. But as long as like you don't touch the actual payloads, it seems to be fine.
Okay. But in the current RFC, you have no way to determine that from BPF context.
That's right. Yeah.
Thanks.
Last question.
Do you think that it's feasible to implement for send MMSG the multiple messages at once?
Probably, yeah. I mean, I didn't try that, but I could imagine that's feasible. I don't know.
I'm just curious. Thanks.
Yeah. All right. Thank you. Wow.
All right. See you after lunch.
Wow, chocolate.
Thanks. Super interesting.
Yeah, thank you. Thanks. Glad you liked it. This just reminds me of what you said last night when I was giving you shit about not getting gelato. Oh. Yeah, but eating this is gonna make me fat. Yeah. Fair point. Sure.
I think that is not fine in that. I mean, we have a pretty young coming, so that my daughter was running this, so we would trash that.
Sure. Yeah. There are corner cases like that, but I guess you would know. I mean, like you would configure your app maybe to know that, to say like.
Yeah, that's the question how to do that. I mean, the app basically doesn't know what the administrator configures on the
Well, it depends on how you build the app, right? Like the app could take configuration at startup to tell it these types of connections you use non-temporal rights, these types of connections you don't. I mean, that's what we do. Like we know for certain types of connections we use it in other ways.
Careful, not just sound it with non-temporal rights if you don't know what's happening.
Yeah, sure, yeah. Yeah. Yeah, thanks.
Okay, yeah.
Hi. The presentation is already uploaded.
Yeah.
Copy down. Copy down.
Oh,
This one, right?
okay.
And then you can switch with the eyes. Right?
Thank you.
Well, you gotta wait a couple more minutes.
Oh.
3 more minutes, and then you can hit the start to keep track of time or whatever. Yeah.
Okay. Thank you. Okay, it's time, so let's start. I'm a geek from Denix, and I present challenges in reducing network virtualization overheads in software and hardware aspects. Okay, I talk about network virtualization as I define 2 use cases. So first one is KVM, so it's kind of obvious. So KVM creates virtual machines, and virtual machines may have some virtual network interfaces, so and require virtual network. And containers is also kind of somewhat containers kind of require some isolated networks too. So it's also kind of network virtualization. So, and there are various opportunities to improve network virtualization. And in this presentation, we present one of each for the software and hardware-based approaches. First, I discuss software network virtualization. So, there are two components of software network virtualization in Linux. The first one is the kernel top driver that creates virtual 2 or 3 interfaces for the user space. The other one is pre-hostnet, and it accelerates the interaction with the top driver for KVM. It implements the whole data path of the virtual interface in the kernel to reduce the number of context switches to the user space for KVM. The control path still needs to be implemented in the user space. It minimizes the complexity in the kernel and provides some flexibility. Let's discuss the received steering program in the software network virtualization context. Today, high-performance computers typically provide multiple hardware threads. So it is essential to distribute received packets to them to utilize those hardware threads. However, there is also a contradicting goal, and that is to keep data locality. If packets for one connection get distributed to different threads, the threads will need to exchange information about the packets, so that is quite inefficient. So the solution is to achieve these contradicting goals is called receive steering. Receive steering is to distribute packets according to the hash of something called flow. Flow is identified with packet information like IP addresses and TCP or UDP ports. This ensures packets for flow will be delivered to a particular thread. Unfortunately, receive steering causes another problem for virtualization. The idea of receive steering is to keep packets local to threads. However, in a naive implementation of virtualization, both the host and guest will perform receive steering independently, and that has data locality if they use different receive steering policies. And we cannot implicitly assume that the host and guest will use the same receive steering policy. For example, physical network interfaces often implement receive steering policy called receive side scaling. This is a very old one from Windows BSA era and uses Toplet's hash function. On the other hand, Linux also implements a software solution called receive packet steering. And today, it uses ziphash as a faster and more secure algorithm. It also enables an advanced feature called receive flow steering that tracks threads processing packets. So, for example, the host may use RSS if the host has RSS-capable hardware. However, the guest will not be aware of that and may employ ziphash-based RPS. And that in that case, it will result in inconsistent receive steering and harsh data locality. The top driver has a default mechanism to avoid such situation called AutoMQ. With AutoMQ, the top driver remembers the receive queue index chosen by the guest for flow. And when the driver transmits a packet from the reverse flow to the guest, it reuses the remembered index so that the thread handling the connection will receive it. This is quite elegant approach. It automatically does the right thing. No need of any kind of negotiation between the host and guest. But it also has some disadvantages. So first, this approach is stateful. So it can track only limited number of flows and does not work with new unknown connections. And also it doesn't work with connectionless protocols. Second, it ignores the direction of flow, so it reduces the hash entropy and causes more hash conflicts. So AutoMQ is quite an elegant approach, but it's not a shareable word. An alternative approach is to let the guest negotiate the use of RSS with BART.io. This ensures the host performs receive steering idea for the host as the guest. Unlike AutoMQ, RSS is stateless and provides configuration options to handle specific workloads for the guest. Disadvantage of RSS is that RSS cannot deal with guest thread migration. There are already 2 implementations of RSS, in QEMU and eBPF RSS. In QEMU, RSS was implemented as a reference for BART.io's RSS feature. It is not expected to bring performance improvement, it's just a reference. So, and it adds additional layer of receive steering between the chap driver and guest, so it doesn't have performance benefit. And it is also incompatible with pre-hostnet because in QEMU RSS requires user space database. So it's for like experimenting and understanding how RSS should work in BART.io's context. The second one, eBPF RSS, is as the name suggests, it uses eBPF and is intended for real usage. So eBPF sharing program is a mechanism implemented in top devices that allows user space to replace the AutoMQ and the default steering policy with custom steering policy. So it allows customizing the receive steering on host without duplicating work, so it can bring real performance benefit. It is also compatible with vHost because the receive steering work happens in the kernel. One downside of eBPF sharing program is that it requires privilege. It is not a practical problem considering that network virtualization often requires privileged operation for other purposes anyway. And in fact, there is a patch for revert to delegate the privileged operation to revert from QEMU. So using these approaches, we can use eBPF sharing program seamlessly. Now, I present yet another solution to enhance receive steering, that is hash reporting. Hash reporting is to pass hashes computed by the host to the guest through BART.io interface. So this can save duplicate hash calculations in the host and guest. And it also means that the host and guest will have consistent hash values by definition. However, it does not mean that it can obfuscate AutoMQ or RSS. Hash reporting is just to pass hash values, and it does not tell how to use these hash values. So it's still necessary to negotiate how to negotiate the usage of hash values to have consistent receive steering. Hash reporting is also, it's just passing hash values, so it lacks any kind of configuration. And finally, Windows requires to enable RSS and hash reporting at once, so RSS is mandatory for this particular platform. I have posted patches for Linux and QEMU to implement hash reporting for the chap driver and vHost. Next, I describe how I implemented hash reporting. For hash reporting, we need to pick up some hash values to report to the guest. For OpenMQ, the chat driver will use hashes computed by hardware if available, and fall back to the software computed hash values. The problem is eBPF steering program compatibility. eBPF steering program does not expose computed hash values to the kernel, so we can use this hash reporting mechanism with eBPF sharing program in the current form. And this eBPF sharing program mechanism relies on legacy context-derived interface. And each enters feature freeze, so we cannot extend it anymore. And the latest interface mechanism of eBPF is called kfuncs, and that is such nice one, but it is not UAPI. So in the context of virtualization, well, the other relevant APIs like KVM or pre-host are all UAPIs, so it's kind of misaligned. So I didn't choose that option. To make hash values computed for RSS available to the kernel, I'm also proposing to implement RSS in the kernel instead of using eBPF. So, and this RSS implementation gets activated by ion control, so it is intended to be a normal UAPI, just like other pre-host or KVM APIs. And this IO control will not require any privilege as bonus. On the other hand, this IO control is specific to RSS, so it does not intend to replace eBPF sharing mechanism. eBPF sharing program will be useful for evaluating new receive steering algorithms or implementing application-specific policy. I talked about OpenMQ, RSS, and hash reporting so far, but they are not the only methods to enhance receive steering. There are a few proposals for ButterIO that implements receive steering policy, so I've introduced some of them. Inner header flash is to support packet encapsulation such as Brown. And flow filter is more flexible mechanism than RSS, and it can be used to implement accelerated RSS, for example. So to track threads processing packets. RSS context is intended to be used in conjunction with flow filter and allows to have different RSS configurations according to flow filter. And from the kernel cost perspective, we have the eBPF sharing program mechanism. So technically, we can provide any kind of receive steering policy. However, just exposing eBPF has serious security implications. So if you want to expose this capability, you will need to employ some kind of program restriction or out-of-band privilege operation that is controlled well. Okay, and that was about receive steering in software network virtualization. Now I discuss hardware network virtualization. So software network virtualization includes overheads. Each has inherent overheads and requires complicated optimization as I have shown for receive steering. So natural way to solve this problem is to offload this virtualization work to hardware. This hardware-based approach is more appropriate if you're going to have design system that is dedicated for virtualization workloads, such servers. And there is a specification to add such offloading capability to PCI devices, and that is called SRIB. It creates something called virtual functions to assign resources of the PCI devices to guests. And the host can also perform necessary configurations such as packet switching and virtual functions before assigning virtual functions to guests. So it should solve this virtualization problem and allow to offload this network virtualization work. Yeah, at least that's the idea. However, unfortunately, there are also scenarios where SRIB hardware is not very good at. So that is the container in virtual machine scenario. Containers also often need network virtualization, isolated network. So container in virtual machine results in nested kind network in some sense. So and SRIB cannot deal with this nested situation and prevents VMs from offloading container virtual networks to the hardware. Our idea to tackle this challenge is to emulate SRIB. By emulating SRIB, we can add the way to for virtual machines to configure offloading. Here, emulation only means to add a software-defined control path for configuring network offloading. So the data path can be still offloaded with VDPA and will not be impacted with this emulation. We already have some patch series that implements SRIB emulation for KMU, so we evaluated performance improvement by offloading virtual network packet switching to the hardware when SRIB is in place. This SRIB emulation code, however, lacks the mechanism to configure packet switching, so it's not very useful in practice. But we can still have some numbers by letting the host configure packet switching on behalf of the guest. We measure throughput and latency between external host and container on VM. With this evaluation, we confirmed offloading Java's UDP transfer throughput. It also reduced UDP round trip latency to 2/3. So it's quite remarkable numbers. Now, then, I'll discuss about implementation and the current progress of implementation in QEMU, which is I'm my concern of. There was the first SRIB emulation code posted in 2014 for Internet Network Interface called IZB. And in 2019, Battery gained SRIB support. However, the HSR emulation work for QEMU stopped while after that. So I eventually took over the IGB patches and upstreamed it in 2023. And now I'm working on adding SRIB emulation for BAT.io. And the changes to add SRIB emulation to BAT.io is mostly ready. And yeah, and it's likely I hope it will run in the next version of QEMU. However, just adding SRB doesn't mean we will be immediately be benefited from that. So we need to use this SRB feature to add interfaces to configure some offloading. The latest Bufferbloat draft as a concept of device groups that it works as a foundation for such offloading interfaces. There are already a few proposals that employ device groups in the Bufferbloat mailing list. For example, there is an RFC patch list to add interfaces to inspect the statuses and setting MAC addresses of virtual functions. I had talked about packet switching before that, and there's no posted proposal for packet switching feature. So it is and there is some other there are some remaining open programs that can be implemented solved with device groups idea. I draw the conclusion. First, I discussed the receive sharing program as a network virtualization program. The top driver employs a mechanism called AutoMQ by default, and it is also possible to use RSS that is implemented in the user space or eBPF. Hash reporting is in progress of implementation, and patches for Linux and QEMU are on mailing list for review. There are a few proposals for the buffer specification to enhance receive steering, such as inner head flash, flow filter, and RSS context. So the buffer specification is even growing. Next, I discussed SRB and its problem with the container in BRIM scenario for hardware-based virtualization. Employing SRB emulation can involve configuring offloading in virtual machines for such as nested virtualization scenario. The latest buffer specification provides foundation to use SRB called device groups to add interface to configure offloading. So the remaining open program is to how to use this device group mechanism to actually implement useful offloading mechanism. Yes, so this is all, and well, yeah, actually, I'd like to thank you, Vashizu from NTT Open Source Software Center, for providing some diagrams and benchmark results. Okay, that's it. So, any questions?
Was that a question or you're just stretching?
Why are you saying that RSS hash is not available in eBPF program, since you have like XDP hints and you can request RSS hash from the hardware descriptor?
Well, first, and we are doing all of this RSS work in software instead of hardware. Yeah, certainly some hardware implements RSS, and that's why got this RSS in the spec. However, we cannot rely on the hardware to compute RSS hash values because the top devices may have the virtual machines may have different RSS configurations, so that may result in different results. So that makes impossible to just use hardware RSS, hardware computed RSS values. So we need to implement this in software in user space or eBPF. And when using eBPF, well, we do calculate the hash values. So in theory, we should be able to use these hash values. But the problem is that we don't have an interface for that. And we cannot extend the interface because it's in feature freeze. So that's why I opted to implement I/O control for RSS and use it for hash reporting.
Okay, makes sense. Thanks.
More questions? You have, yes.
So your extensions with the MAC address and the status programming kind of sound like it could be a special case of general, need to support provisioning of virtual machines. So isn't it like a good idea maybe to generalize it at some general provisioning interfaces?
Well, first of all, it's not my proposal. It's some proposal floating on the mailing list. And well, the idea is just to let the operating system using virtual device to configure this kind of settings. So if you are managing the host and have running some virtual machines on top of it and exposing virtual devices to virtual machines, and then you don't need to use this mechanism. You are controlling the host, and you can set MAC addresses of virtual devices with normal device configuration mechanism KML or libvirt has. So it's not relevant in that case. However, we are considering about the case that the guest that uses BART-IO needs to configure these BART-IO devices. So independently from what the host intended. So in that case, it makes sense to delegate this work to guest and provide configurability instead of kind of controlling everything from the host. So that's the idea of this device group things.
All right, thank you very much. We have a little gift for you. Thank you. Oh, you're already a presenter. Dust, if you can hear us, you can, I think, take over and change the presentation.
Yes, I can hear you clearly. Can you hear me? Oh, the network seems not very good. Can you hear me? I cannot share my camera. Hello, can you hear me? Hello, can you hear me? Any sound? No sound? Oh, shit.
Yeah, we still can't hear you, so give us a minute. Okay.
Can you hear me now? No sound? Sorry for that.
We can't hear you. Is speaking.
Oh, is it? Yeah.
Hello? Hello, can you hear me now? Hello, can you hear me now?
Yes, hang on a second. Keep talking. Check, check.
Okay. Is there any sound now?
Not yet. Keep going.
Okay, thank you very much. Okay, let me begin.
Just no,
I'm
don't
just
begin. Just do an audio test for us.
Okay, okay. So there is still no sound. Is that right?
Yeah, we're getting you in the headphones, but not in the room yet. But we're gonna get you in the room.
Okay,
soon,
okay,
so,
okay.
But I need you to keep talking
Okay.
so I can test it.
Okay, okay. Thank you very much. I'm really sorry I cannot be in Vienna in person, and my visa has some problems. And thank you for having me today. I hope I'm not the only one who is remote. And I hope the network goes very well, very fast. I don't know whether the sound is clearly enough because I see the pin RTT from here to the BBB is about 20 to 100 milliseconds.
Yeah, we got it's a problem with the soundboard. Any second, it's going to get solved.
Okay, okay. It's okay. Okay, looks like I'm the only one who is from the remote. Okay. Really sorry for waste your time.
Oh, you're fine.
Thank you. Let me check.
Okay. Keep talking for us. Any
Okay.
second.
Okay.
We're
okay,
getting
okay.
the
No problem.
remote signal, but we don't hear it in the room.
Okay.
Test 1 2. Test 1 2. From the laptop, the sound out of the audio interface coming through there.
Okay.
Is not going onto the speakers. Everything else works.
Do we have?
Okay.
Let me check the agenda and the PowerPoint. Okay.
If you could keep talking, that would be great.
Okay. Okay. I'll try my best. Looks like the PowerPoint. Oh, I switched myself as and okay. I'll try to see the PowerPoint goes very well. Okay, it's still not ready. Network is let me change. Let me try to switch with the slide. Okay.
Yeah, we're still working on it.
Okay. Okay. I'll wait. I'll try to see if the slide changes well.
Hey, say something.
Okay. Okay. Is that okay?
Yes. Thank you. You can start.
So it's okay. Thank you very much. Okay, let me change to the first slide. Okay, hello everyone. I'm Dust Lee from Alibaba Cloud. Sorry for waste your time at the beginning. It's very sorry I have not been in Vienna in person and have to give a talk remotely. My topic today is SMC ERM, which is a fast remote memory communication method based on SMC socket. Here is the agenda. Let's first talk about the problems we are facing with SMC now. What is SMC? Before I start, I'd like to ask how many of you have ever heard about SMC? SMCR is an effort to boost the performance of TCP applications in data center without any code change. It has three main characters. First, it provides the capability APIs, compatible APIs with the TCP socket. The second is it uses RDMA for data transmission at the low level. And the third, it's implemented in the kernel, which means it can work with static linked applications like Golang. There are three ways we can use SMCR. First, we can change the code explicitly from AF ANAT to AF SMC, or change the protocol to IP Proto SMC in the syscore, in the socket syscore. The second way is to use an ILD preload. We have a script called SMC run, which can run as a prefix of an application, and it will hook the socket syscore and set the AF-INET to AF-SMC. And we also have a third way, which is to use eBPF. With eBPF, we can replace an application from TCP to SMC dynamically. This is the same way as what MPTCP did now. This is the most flexible way because it can filter based on address, a port, and process name, etc. SMC has better performance for long-line TCP connections without any code change. We are trying to replace some applications like Redis and Kafka in the public cloud from TCP to SMC now. But for applications that need lots of bandwidth, SMC does not support zero copy now. So before we dive into the SMC ERM, let's see how SMC works. On the control path, SMC will first create a TCP connection with an experimental TCP option to see if both sides support SMC. If both sides support SMC, then we will go to the second step, which is the SMC handshake. And in this step, SMC will prepare all the resources that is needed to do RDMA communication, including allocate SMC buffers and RDMA resources. If any of those steps failed, then SMC will fall back to the TCP connection we established before. So the application should not be affected. Next, let's go to the data path. For one data transfer from the sender to the receiver, first the sender will try to do a memory copy from the application buffer to the SMC send buffer in the kernel. With the send messages core, then the data will be transferred by RDMA device using RDMA write from the sender buffer to the peers receiver buffer. Then the sender will then notify the receiver to update its receiver cursor. And then the application on the receiver side will call receive message to copy the data from the receiver's receive buffer to the application buffer. And finally, the receiver will notify the sender to update its send cursor. As you can see, for one data transfer, there are two CPU copies from the client side and server side, and one RDMA copy. And those two CPU memory copies limit the throughput of SMC. So since communication is all about moving memory, why not directly move the data from the send buffer to the receiver applications? This is the basic idea of SMC ERM, which is a direct memory access on top of SMC socket. We call it extended remote memory. So before we extend the API, we try to see if we can reuse the existing zero copy APIs. For example, we have send message, zero copy API, TCP with message, zero copy flag, or TCP zero copy receive on the set sock option, get sock option. We did some research on that, but we think it's better to extend the API for two reasons. First, for RDMA, the memory need to be pinned to the device, to the RDMA device. The second is for TCP, TX and RX zero copy is separated, but for SMC, we can directly move the memory from one side to the other. And one more thing for RDMA is actually RDMA it's very easy to support zero copy because for received data, RDMA directly go to the RCQP with no header, which means we already have data header split and flow director support for RDMA. And secondly, RDMA read-write can access any registered memory, both from the client side, from the local or the remote. So let's go to the design of SMC ERM. When we design SMC ERM, we have two goals in mind. First, we need very high performance. We hope to have a competitive performance over user space RDMA. And the second one is it should be easy to use compared to user space RDMA. So we need to simplify the APIs for user space applications. This is how it works. First, the user will register memory directly to the RDMA device. Then the ERM will synchronize the registered memory to the peer socket. And the third, the metadata is stored in the control message and can be transferred. And data can be transferred using send message and received using receive message. There are two sets of APIs we extended for SMC. The first is for the control path, and the second is for data path. For control path, we have a set of set sock option, especially to do the memory register and memory deregister. For the data path, we have extended the send message with control message and receive message. And for the control path, there are three main parts: the handshake, and the memory register and unregister, and the key exchange for the memory region management. For the data path, it's pretty simple. We can just do send and receive. So for the control path, first thing we need a handshake to tell each other if we support ERM or not. We add it in the SMC handshake process It's the CLC proposal in the SMC. Since we already have a handshake in SMC, it's pretty simple. It's pretty easy to support this. And for the ERM control path API, we have two main APIs for control paths, the reg memory region and the direct memory region. For reg MR, it takes a few parameters, including user memory address, and the most important, the access flag. If the access flag is set to remote read or write, then the memory region will be synchronized to the peer socket by ERM in the kernel. If everything goes well, then a memory ID is returned. The user space can then use this memory ID to do direct memory access on the remote side. For memory region management, we need to do two things. First, we need to register the memory locally. Second, we need to synchronize the memory region to the peer socket if it is marked as remote read or write. For memory registration, we have three routines as user. We have the same routine as the user space RDMA registration, and the memory region manager, in our current implementation, we implement it in the kernel space. The main benefit of managing it in the kernel space is that we can do safe checks, which is critical for SMC because different SMC sockets can share a same QP. This picture here shows the reg MR flow. The memory region management has two MR tables, one for local MR table and one for remote. First, the receiver side core set sock option with the reg MR and the remote read write side. And then in the kernel, the memory management will register the memory to the NIC. And since we have set the remote read write flag, we need to synchronize the memory region to the peer socket. And what we need is to synchronize the memory ID, address, IDMA key, and length. After the sender received the memory ID of the peer, it updated its remote memory region table, so it can then do read write using the memory ID. So let's go to the data path. First, we have a very simple API, which is send message, and as you can see, it only send a control message to, and it has no data in it. The most important part of this structure is the SMC ERM command copy. We have several very important fields, which is the flag, whether we want to notify the remote and the local memory ID and the remote memory ID and the offset of each memory. And if the remote completion flag is set, then after the send message, the peer will be notified and will receive a message that means it can know that some data has come to his memory. And if the remote completion flag is not set, then only a data transfer is triggered without bothering the receiver. And for receive message, it's even simpler. In our current implementation, we put the control message in the error queue, just like send message 0 copy did. And after, if the sender had the notification, remote notification set, then the receiver will receive a notification and an interrupt will be triggered, and then SK data ready will be called, and the application should then call receive message with the control message set, and then he can know the data is come, and he know where the data is and how much data have been received. I'll show you some of our preliminary test results. This is a test setup. We have a SPR CPU with 2 terabytes memory and a Manlox BlueField 3. This is the fastest NIC we can get now from the market with a PCIe 5.0, and the topology is pretty simple. We have 2 virtual machines run on the same host, and we have 2 virtual functions. Each one pass through the one VM, and the 2 virtual machines are running on the same NUMA node, and the CPU are on the same socket, so we don't have NUMA problems or cross-socket problems. And we run, since what we are doing is a 0 copy, so we run the throughput test. We compared the throughput with TCP SMC and ERM and user space RDMA, which is IB-RAT BW. The data is transferred from the sender to the receiver only, and the results show that both ERM and user space RDMA can saturate 200 gigabits with just 1 core. Our future work and standards. Now it's still a POC, and many code is hard-coded. The second thing we need to do is to finish the handshake support in the protocol. So we need to extend the SMC protocol to support handshake. And after that, we need to complete the IFC and try to send to the mail list. Some of the future works, including the BD port support. If we want extreme low latency, we need BD port support. And current SMC does not support that. And application can, but with ERN, application can do BD port in its memory, in user space without the kernel support. Actually, TCP BD port also has some problems in our I think. Especially it can do some work for others, which I mean, when you do PD pour, you can pour some other sockets packets, which is not belong to yourself. And one more thing is we may try to combine our URIN with our ERM socket. ERM is a synchronized API, so high performance, 0 copy. Maybe our URIN is asynchronized by nature, so I think our URIN may help us. Okay, that's all. Thank you. If anyone has any questions.
Thank you. Rishab, whenever you're ready, you can take over the presenter, and I think you can start whenever you're ready.
Great, thanks. So just a second.
Sorry, I need to give Chrome some settings. Oh, I'm sorry, I have to quit and reopen. Give me 1 second. I'm so sorry about this. Hi, can you give me presenter rights again? Okay. Can you see the slides? Just a second. I don't think I can hear you guys. Can you hear me? Sorry, I don't think I can hear you at all. I'm not sure. Should I just start the talk? I think someone in the chat saying they can hear me, but I can't hear anyone.
I can hear you.
Yeah, I can hear you now. Thank you. Thank you. You can't see my slides?
I'm remote. I'm not in.
Oh, sorry. It seems that the remote can see my slides, but the room can't. Okay, that works. Although there are probably a few too many, but okay, sure. I've uploaded it on the contributions page. Great. Okay. Thanks, Karthik. Okay, so I'll get started. Uh, okay, thanks for having me. Sorry about the snafu with the presentation. I'm Rishabh. I'm big disclaimer. I'm an academic researcher at Berkeley, and I work on building tools and techniques to help developers better understand the performance behavior of their code. And so, really happy to be presenting here, particularly because so some of the recent patches to the kernel were some of the motivating factors behind the work I'm presenting today. So, next slide, sorry. So, in a nutshell, the problem that this work is trying to solve is help developers answer frequently asked what if questions about the cache usage of their code, and particularly for unseen and untested workloads that it might face in production. And so simple example of these questions are, how does the cache usage of my network stack scale as a function of the number of connections? And what is my code's cache and hit or miss profile? Next slide. And what I want to emphasize is that we want to do this for developers, not only for their own code, but also for third-party code that they're not very intrinsically familiar with. So as a simple motivating example for the rest of the talk, consider a developer Alice who wants to build an in-memory key value store that needs to be fast. And so simple two-component key value store with a hash table that Alice knows and understands, that's her code, and a network stack that she's going to use off the shelf. And because in such systems, throughput is often bottlenecked by the number of LLC misses, Alice needs to answer questions such as what workloads lead to consistent cache misses and how much of the cache does each of the two components use. So for instance, how many cache lines does the hash table touch per key value pair, and how many cache lines does the network stack touch per connection? Next slide. Now, the problem is that existing tools to answer these questions are insufficient. And so today, when we're trying to answer these questions, we rely on profilers like perf and the hardware counters that they come with. And the problem is that these tools are very good at providing insights into the concrete, specific test cases that we give them, but they don't have any predictive capability. And so you cannot use them to draw conclusions across workloads. And so, for example, if I want to understand how many cache lines does my network stack touch per connection, I can give perf, I profile my workload, I get a bunch of hex numbers, and then I have to manually sit and understand which part of the memory those hex numbers came from, which I can maybe do for my code, but becomes sort of an order of magnitude harder for code that I didn't write. And so at the end of the day, developers are often forced to manually reverse engineer their answers to key questions, which is not only painstaking, but also error prone, particularly for third-party code. And no, sorry, can you stay back? And this observation was really the patch that I mentioned on the slide here was really motivating this work, because if the fast path of the Linux TCP stack, which is probably some of the most heavily exercised code in the world, can have a bloated cache footprint, then it's very likely that lots of pieces of code all around the world are suffering from such bloated cache footprints. So what's the key idea? So we realized that the big challenge is that there is a lack of abstraction for cache use. And what do I mean by abstraction here? If you think about it, Alice needs visibility into how the code processes an abstract workload, so an abstract connection, not a specific packet with a specific 5-tuple in the TCP header. And the problem is that the only way she can obtain this information today is directly from the implementation itself. So she has to either read it, which becomes painstaking after a point, or then profile it, which gives you incomplete answers. And so the question we're really asking is, can there exist some kind of abstract or symbolic representation that can help developers like Alice efficiently reason about cache usage? So in answer to this question, we come up with this abstract representation that we call memory distillates. And I'll start with this 10,000 feet view, and then I'll get into the details. And so at a very high level, this memory distillate is a representation that is going to retain all the information relevant to how the code accesses memory and is going to discard everything else. And so given the same inputs as the code, what the distillate will do is produce an identical trace of memory accesses, but will not, for instance, produce the right outputs or the right timing behavior because it is not timing equivalent or functionally equivalent. And so we use this idea of, next slide, sorry. And so we use this idea of memory distillates to build a tool we call CFAR, or Cache Footprint Analyzer. And basically, CFAR has this two-step workflow, which allows developers like Alice to answer their questions about cache usage. So in the first step, called distillation, we use a bunch of program analysis techniques to transform the code into the memory distillate. And the second step, we basically turn this distillate into some sort of database that you can query to answer specific questions about cache usage. And the key idea here is that because the distillate contains all information relevant to how the code accesses memory, you can answer diverse questions about cache usage. And I'll give you an example of this later in the talk, where I can show you how we not only answer performance questions, but you can also answer security-related questions. So in the rest of the talk, I will go into the details of the distillate and CFAR, but if there's one sort of key takeaway I want you to leave with at the end of this talk, it is that, sorry, next slide. It is that this abstraction of a memory distillate gives you a simple yet precise foundation for reasoning about cache usage. Okay, so I'll now jump into the details. Next slide, please. Here is an overview of CFAR. It's very similar to the diagram I just showed you. You have the program source on the left. You have the two phases of distillation and projection, and the distillate in the middle. And then you have the answers to different questions that developers have. And so I'm going to dive into the details, starting with the distillate. You probably have to skip 2 slides. Yeah. Okay. So to give you an example of a distillate, I'm going to use a very simple create system call from a research OS. And this create system call is responsible for creating a new file. And so as you can see, it takes a bunch of arguments, and it's going to sort of validate the arguments. And if they're valid, it's going to add a new file. And now this is a very, very simple piece of code, but the key point is, next slide here. The key point is that it has an input-dependent access pattern, just like a sort of a more complex piece of code like the Linux curve. So as you can see here, based on the process ID and the file descriptor, it's going to access a bunch of kernel state, sort of indexing into the arrays based on the inputs. And so what does the distillate for this piece of code look like? Next slide. So the distillate is what you see on the right. Don't try to read the whole thing at once. I'll sort of walk you through it. So first and foremost, the distillate, and this is for the data cache, of the program is another program. And this program is going to take in the same inputs as the original program. So for instance, here you see the same inputs as the syscall, and is going to maintain the same state. So the same process table and the file table. Next slide, please. Now, the key difference is in what the distillate returns. So instead of computing the correct semantic or functional outputs, what it's going to do is return an ordered sequence of data memory accesses in which each element is a tuple. And the tuple consists of a type and an address. Next slide. The type can be one of 3 things. It can be read, write, or read, modify, write. And the address is a symbolic expression in terms of the input I and the state S. And next slide. And the reason we chose this symbolic representation is because it allows the distillate to very precisely replicate the memory access sequence of the program, irrespective of the concrete values of the input and state, or or factors such as how the address space is randomized. And it turns out you can do this not only for the data cache, but also for the instruction cache. So next slide. So here on this slide, you see the instruction cache distillate for the same program. And once again, it's another program that's going to take input the same inputs as the syscall, and it's going to return an ordered sequence of instruction memory accesses. Next slide, which are expressed as a function of as offsets with respect to the memory address of the first instruction. And once again, the key idea here is that this symbolic representation allows us to precisely produce the same instruction sequence executed by P, irrespective of factors such as where the code is loaded. And so that was sort of the distillate at a very high level and the symbolic representation of a program. You can think of it as a program transformation such that the new program will only produce an identical sequence of memory accesses and nothing else. And so that brings me to a couple of key limitations I want to emphasize is that this distillate is going to discard all timing information related to memory accesses. So you cannot, for instance, reason about memory latencies. And this also, in particular, affects prefetch operations because you cannot reason about their timeliness. And another thing, another limitation in these is that it does not provide details about speculative memory accesses because these are, for instance, hidden by the hardware, precisely extract them without modeling your hardware in some kind of weird way. So that was at a high level the distillate and the symbolic representation. I'll now quickly walk you through the process of extracting this distillate or the process of distillation. So distillation in CFAR is a 4-step process. And as I told you before, it is backed by a bunch of program analysis techniques. So the first step is the path enumeration step, where we basically analyze the source code to enumerate different parts of the program. And there is no magic here. We basically have 3 types of analysis that provide that occupy different points in this trade-off between completeness, scalability, and human effort. So one sort of analysis backend we have is automated symbolic execution. For those unfamiliar with it, you can think of it as something very similar to what the eBPF verifier does for programs, where it takes in a piece of code, try to automatically explore all parts of the program and just until exhaustively. And this is fully automatic and it's in theory complete, but in practice, it doesn't really scale to complex code. The other option you can use with CFAR is sort of a more guided symbolic execution, where you manually add constraints on the input and the state so that the program analysis only goes down the paths you care about. This actually works quite well, even for code like the Linux kernel, because very often with cache behavior, we care about the fast path code, which is very often the most simple code. So if you constrain symbolic execution to go down the fast path, it can actually fully explore the fast path. And the last sort of backend that we're building, and this is still work in progress, is a concolic execution based backend. And what this basically does is it gives you the same information that symbolic execution gives you, but only for a set of paths that you can cover in your tests. So the idea here would be you take a set of tests and you can run them through. And what the program analysis will do there is only explore those paths, but will give you the symbolic expressions for all memory accesses along that path. This is still work in progress, and we should be done in a few weeks. So at the end of this sort of path enumeration step, which is really the big heavy lifting in CFAR, you end up with a set of path constraints for each path, which is a set of constraints on the input and the state for them to exercise this path, and a set of expressions for the symbolic addresses. And what we also extract is a set of concrete inputs, one for each path. So a concrete input that will exercise that path. And the reason we do this is it'll become clear in step 2. Sorry, next slide. Is because in step 2, what we do is we replay the program binary. And the reason we do this is just a matter of convenience, actually, because it is much easier for us to analyze the source code. But when looking at the source code, you don't have all the information about memory accesses. So simple examples are you don't see register pressure. Let's say you're analyzing something like LLVMIR, you don't have register pressure. And so you want to get the sort of precise sequence of memory accesses, you need to replay and sort of taking stuff like compiler optimizations, you need to replay the program binary. So what we do in this step is we take the concrete input that we got in step 1 and we replay it with the binary to get an execution trace from the actual binary. And what we use here is pin. So we run the input through pin, we run the input to the program through pin, and we extract a very precise detailed log of all the hexadecimal addresses it touches. The next step in step 3 is basically putting together the results of step 1 and 2. So we basically in this step, we combine the information extracted from the source with the information extracted while replaying the binary to have finally the precise information for each path. And then we also use the path constraints extracted for each path to build the entire execution tree. So that is all the paths that the input can go through in the program. And the last step is really just a cosmetic step where we take this execution tree and we translate this into a Python program. And it's really not that fancy here because we limit ourselves to binary trees. So we have a very simple if, else, and so on in our Python program. And so that was distillation in CFA. I'll now very quickly walk you through how projection works. So as I've told you before, in the projection step, developers are going to write a bunch of programs that operate on this distillate to get answers to their questions. Next slide. So what exactly is a projector? So projectors in CFAR are user-defined functions that are going to compute different cache usage properties. So for instance, all of them are going to take as input a Python list, which contains the list of symbolic memory accesses, and are going to answer questions about specific questions about cache usage. So very simple examples you see on the slide here. For example, length of the list is going to give you the number of memory accesses, and the second expression, where you take each address, integer divided by 64, and compute a set of unique addresses, is going to return the number of unique cache lines touched. So this is sort of the trivial examples. The more sort of involved projectors that CFAR comes with are stuff like how a p-scale, which tells you how cache usage scales as a function of the workload. This is, for instance, one of the first questions that Alice wanted to know. P-hit and miss, which is a cache model to study specifically the hit and miss profile. And finally, as I promised you before, you can not only analyze performance properties, but also security properties, because once you have full information about all your memory accesses, you can very quickly identify memory accesses that depend on a secret in the data cache distillate, and memory accesses that depend on branches in the instruction cache distillate. Next slide. One thing I want to emphasize here is that projectors are very, very easy to write. And so, for example, the first and third projector are both less than 100 lines of Python code, and the cache model is sort of more or less, it's much larger, but it's basically taken almost as is from Gem 5. And the reason for this is because projectors directly operate on a list of memory accesses, and they really don't care about how the program in question actually produced that list. And so they allow people who are unfamiliar with a piece of code to very quickly and easily understand the cache usage properties of that piece of code without having to understand the piece of code itself. So as a simple example, at very high level, let me tell you how the p-scale projector works. So what is p-scale going to do? Given a list of addresses and a symbol of interest, a symbol is just an input, it's going to compute the number of cache lines touched that will change if the value of the symbol changes. And so it's a very concrete instance. Given a function in the TCP stack, let's say the transmits function or the receive function, and let's say a particular symbol here, let's say it's a socket, it's going to compute the number of cache lines that will change if the socket changes. So for example, the connection changes, right? And so as a simple example here, if you have three memory accesses, one to a constant, one to x plus 16, and one to x plus 72, assuming x here is 64 byte line, it's if x changes, you can have you can access a set of two new cache lines, and so it should return two. So how does it do this? It's very straightforward. What it's going to do is it's first going to use the Z3 Python API to compute the list of addresses that will change if x changes. Then it's just going to compute it's going to ask Z3 to give you concrete values for which the change will take place. Run these concrete values through the distillate, and then just compute the difference in the concrete cache lines touched. And once again, you can do this and analyze any piece of code because you don't care about how that piece of code actually gave you the Python list. That part has already been taken care of in distillation. So yeah, I just want to finish with a couple of limitations about projectors. So one thing is the current prototype only analyzes each path in isolation. So as I told you before, it's going to take as input only one list. Now it's feasible, it's very easy, it should be rather easy for projectors to be able to analyze more than one list at a time, but we currently do not support this yet. This was sort of a philosophical decision because the moment you have to analyze more than one list at a time, you have to take into account the branches. And so then your projector starts becoming dependent on the program itself. And this nice separation doesn't hold. But it's something that we will add if we see a use case. And the second, and this is a key limitation, is that all of the projectors we have right now assume that the program is not preempted during the execution. So for instance, if I want to compute the hit and miss profile, I will assume that this is the only piece of code that ran for a while, just because there is no way for a projector to analyze what happens if an arbitrary program can run in the middle, because there is no way to compute the state of the cache at the end of that program running. Okay, so that was sort of how CFAR works. Let me sort of quickly give you a few highlights of our evaluation, just show you what you can do with it. So we've analyzed a bunch of programs. We've analyzed the fast path of the transport layer, so just the TCP layer, of the ingress and egress from 6.5 and 6.8. And the reason we chose these two versions is because they are the stable versions before and after the patch I told you about. And we also sort of replicate the analysis on a couple of much simpler TCP stacks, which is one kernel bypass stack in academia, and the LWIP stack, which is a TCP stack for embedded systems. We also did a bunch of other programs, a research kernel, a bunch of open source hash table implementations. And as I talked to you about later, we also did a bunch of OpenSSL algorithms with our cryptographic projection. And the questions that we are interested in is, are the distillates extracted accurate and are they useful? So can you do cool things with them? So to answer the question about accuracy, we manually wrote a bunch of test cases that covered approximately half of the paths through each program. And for each test case, we measured the number and the addresses of all the executed instructions and the data memory accesses. And we compared these numbers to the values predicted by the distillate. And in each case, we observed zero error. And to some extent, this should not be surprising, because CFAR, at least when it comes to the distillate, is not modeling anything. It is analyzing the program, replaying the binary, and extracting the information through PIN. So there is no modeling here, and so you have a completely precise substrate. And this also tells us that the distillate will hold irrespective of the concrete values of the input and state and how the address space is randomized. So that was the accuracy. Now I want to show you a few examples of how you can actually use CFAR. So the first question we try to answer with CFAR is the question I talked about earlier, which is the question Alice asked and the question that the patch was trying to answer, which is we analyzed the fast path of 4 TCP stacks, so the 4 ones I told you about, and we really wanted to know how the working set would scale. So we told CFAR, and this is a combination of the first two projectors, the scale and the hit and miss, which is predict the number of connections at which each of those 4 stacks will suffer consistent LLC misses. By consistent LLC misses, which is each incoming packet will start to thrash the cache. And so, next slide, please. So here is what CFAR predicted. So you have the 4 stacks, and you have a number in terms of number of connections. And this is not a comparison between the 4 stacks. It is just 4 different numbers that CFAR came up with. And to validate this prediction, what we did is we actually ran just the transport layer. So we wrote a simple shim, and we measured the latency of just this transport layer. And can you turn the slide? And when we measured the latency, we noticed that for each of the 4 stacks, there was an increase in latency at roughly the point predicted by CFAR. And when we actually looked at the root cause, this root cause was due to LLC misses. And so the point I'm trying to make is that now with CFAR, you can analyze the cache usage of a piece of code without having to understand the piece of code. And I mean, among the many things, it will immediately show you that the 6.8 is much more cache efficient. At least the fast path is much more cache efficient, and because it's going to fill the cache only at a much larger number of connections. So we replicated what the patch did for other TCP stacks, in particular the kernel bypass stack. And so here is a very simple 5-line projector, which is trying to identify how many cache lines within the PCB, which is the equivalent of the socket buffer in the kernel, the socket in the kernel bypass stack. And so basically you take the PCB and you try to compute how many accesses depend only on the PCB and how many cache lines they are away from the base of the PCB. And when we did this, next slide, please, we noticed that this is what CFAR returned. So the top vector is for the send path, and the bottom vector is for the receive fast path. We noticed that there was sort of this one errant access to a 5th cache line that was not accessed anywhere. And we did this without understanding the stack at all, right? And when we actually went and dug deep, it became very clear, because what the stack had done, and this is academic code, I understand, is that a bunch of the timer information was upfront. And because this is not used in the fast path, it was you were pushing one access to the 5th cache line. And so we went and fixed this, and we reorganized the struct for cache efficiency. Go to the next slide. And the results were immediately noticeable, right? So once again, we did the same experiment, and we noticed that at this point, for the fixed kernel bypass stack, you start the latency starts rising only at a much larger number of connections. Lastly, I want to finish with showing you CFAR's flexibility and show you that you can do more than just performance with it. So we use CFAR to inspect 7 algorithms through OpenSSL 3.0. Most of them are the commonly used ones, so AES, SHA, MD5, RSA, and so on and so forth. And here, in addition to reproducing a known cache leakage vulnerability in RSA, we also found a new constant time violation in AES, which had been latent in OpenSSL 1.1. And this has been acknowledged by the maintainers and in the final stages of being merged. And I just want to very quickly show you what the output will look like to show you how quickly and sort of intuitive it is. So this is based on the instruction cache distillate. And so here is the specific function in OpenSSL. The projection for the number of cache lines, the number of instructions. And the key thing here is that the padding length of the buffer needs to be a secret, because if it's not a secret, you are vulnerable to padding oracle attacks. And so very quickly here, next slide, you'll see here on this slide that this is not the case, right? The number of instructions are a very clear function of this padding length. So we went and fixed this, and we verified the results with the projector. And you can sort of very intuitively and immediately see that the projection will immediately tell you that the number of instructions is now independent of the input. And so you are sort of constant time. To summarize, today I told you about CFAR. The key idea behind CFAR is this abstraction of a memory distillate, which captures in this symbolic representation all the details relevant to how the code accesses memory and discards everything else. And what CFAR does is this turns this distillate into the substrate that can be projected into answers to diverse questions about cache usage. So you can find more details about the project at this link. Thank you for your time, and happy to take questions.
Can you talk some more about the findings that you had from the Linux kernel? Because you mentioned earlier on the networking stack, right? So I would be curious, like, what you found and what you changed, or if you're planning to.
So we didn't find anything new. I'll be honest here. This work, we analyzed the Linux kernel after this patch. So basically, I'll tell you what this patch is. This patch says that the key portions of the TCP sock struct and many other struct, but I'll focus on the TCP sock, were being accessed or were all over the place. And so the fast path was accessing 50% more cache lines than it needed to. And so basically there was this elaborate measurement, and it said, okay, all of these particular fields are being accessed in the fast path, and so we need to move them up, and so on and so forth. And we didn't find anything new. The study was fine. The organization was fine. It's just that you can now do this automatically. When we went and we tried to do this automatically for the new kernel bypass stack, that's where we found the new result.
Okay, and do you have the tool available for developers to try out? Like, let's say if I want to look into other areas of the kernel, for example.
Absolutely. So the thing is, because the Concoli execution is still work in progress, we will release it in a few days. Oh, sorry about the delay. I mean, I can send you the details about the symbolic execution stuff, but that requires a little too much understanding of the tool for most users. That's been our experience so far. So we thought we'll make it public once we do the Concoli execution stuff.
Sounds good.
Hi, can you hear me?
Yes.
Yeah, I think the main difficulty we had with TCP was actually the fact that we had variables or fields used both on receive and transmit path. So you said earlier that your tool was only capable of studying one path. So that's going to be a bit of a limitation, I think.
So I should rephrase. You can do one path at a time, but you can analyze. Sorry, you can analyze each path independently. Let me tell you what you can't do. So what you can't do is say, let's say one thread is executing path A at one point in time, one thread is executing path B at one point in time, and they're interleaving in a weird way. That it cannot do currently. But it can say, for instance, someone executing path A is done, then someone's executing path B is done. It can do that. So it just assumes that the different paths are independent. It cannot analyze all possible interleavings of paths.
Thanks.
But the
So just to build on that, sorry, can I just finish? Sorry. If you look at the distillate, right, because the distillate is a program that takes inputs and computes these symbolic accesses as a function of these inputs, distillates are composable in that you can take the distillate of a function, and when it calls a new function, you can just plug in the distillate of the new function because they're just programs. And so, which is why you can stack up one path after the other. Sorry, I interrupted someone.
No, I was going to ask you, basically, if you have two distillates and they get the same inputs, you can, in theory, say how much they will do fault sharing or not, right? Because if you assume that the input
exactly,
right?
Yes. Yes. Yes.
I just looked up the link on your slides, and it seems that the paper and code is actually not on the page. Is there a timeline where you plan to publish it?
So the paper is public. The paper is already public. The code, I mean, we're in discussions with a few people, and we're expecting end of this month. I mean, I wanted to have it ready by today. I'm really sorry, but we're expecting by the end of the month for sure. So I mean, apologize for this, but please shoot me an email, and then I'll get back to you at the end of the month with the code.
Thank you very much.
Paper is. I'll add the paper to this website 2 minutes after the talk.
Me again, I wanted to say that we couldn't do a complete job of reorganizing TCP fields because of this CCP, which forces to have common fields with TCP and DCCP in INET structure instead of TCP. So when we get rid of DCCP, TCP will be much faster.
Any more questions? All right. Thank you very much.
Thank you.
But it's, I'm uploading in the breaks. Yeah, I think you were out, but the first VC presenter was a bit of a pain. They had to patch them through. Took them like 10 minutes. Okay, but I think it's fixed now. Do you want to take over or just present from the PDF? Present from the PDF. Do you want your chocolates or? You get 10 chocolates. So yeah, maybe for kids. Yeah, I'm just basically not giving them to the remote people. So it works out, right? Yeah. have CI and then you can run. Oh, yeah.
Half an hour, maybe less than that. We'll see if there are discussions or not. We'll see.
No hard break at the end, right? So. Hello, David. We might get a song from Dave while we.
There's something happening here. What it is exactly clear. There's a man with a manifesto there. I'm telling you, you got to beware. Stop, baby, log off now. Get outside, get on down. AI hear every tweet. They know you are what you eat. Your Kindle logs every page. I turn the fine, turn to days of rage. Oh, stop it, baby, log off now. Get outside and get on down. Signal knows who you call, and they say they don't hear nothing at all. But Zoom is a bit more fast. Yeah, we spy, but only on the low class. So stop, baby, install Galen, get your code on your own machine. Paranoia, it strikes deep into your arms, it will creep. And sometimes I think I made a new friend, and she turns out to be an LLM. Oh, stop, baby, log off now. Get outside and get on down. Just stop. Hey there, ChatGPT. Can you rewrite this song for me?
a two-level upload system. I also uploaded it here. No, or maybe I didn't. It's I thought I uploaded this already. This is a Chromebook. And where's demo thing? Oh, here. Where I got. And we want to start. But it will pop up.
Why can we not have the screen bigger? I mean,
no, I think we're supposed to see the remote people to be friendly.
but you've done it too.
Hmm?
You've done it with Netlink.
Yeah. I mean, it's already almost the end of the day.
Yeah.
All right. Whenever you're ready, I guess we can. I will try to have the people inside.
Hello. Yes, so welcome to this presentation. So it will be about the NetDev CI. I'm Mathieu Bart. I'm co-maintaining MPTCP, but I'm not going to talk about that today, so you can stay. It will not be technical really, so it's fine. We're on the afternoon, a bit tired, so probably a good time to have this talk. Just a quick note is that on the slide it's written that I'm affiliated to NGI0. It's just that I got some funding, but I will see in the coming months what I will do next. Anyway, here so I'm going to talk about NEPA, which is a NetDev CI, and NEPA stands for NetDev Infrastructure for Patch Automation. So here the plan today is to describe what it is, why it's important to have it, some stuff that needs to be known, how we can extend it, like to cover more code, also how we can replicate that in other subsystems, and maybe having some discussion about what is missing. So the first part. So what does NEPA do? So in very short, it tests stuff. So I guess I can switch to the next part of my presentation. Now, a bit of history first. So before NEPA, patch were hopefully tested somewhere. They were tested somewhere. The thing is that it was tested on on company side, so private test. Of course, they were doing some build tests, statics tests, analytics tests, functional tests, and other kind of tests. But there was no really a global view on what was going on there. There were also some CI that were validating different trees, and they were publishing the result. So there was Intel's KBot, Sysbot from Google, LKFT from Line Arrow, and others. The problem with that is that you have a late feedback, and you don't really know when you will get a feedback, in fact. So the situation changed in 2020, because Jacob brought NEPA to life, really good. Starting point, so here we started with some static analytic test. Yeah, some basic patch check, also some build tests with different tool chains, and that was and still executed by patch.
the results are publicly available, and that's really a big change because you can see that something is going on. It's not behind a company VPN that you can access the result. In 2023, that's the first change, big change, is that the functional tests are appearing. So there are some new tests that appear, proxy checks and documentation building, but the important point here is KUnit is coming. And KUnit, so simple test, but anyway, for that you need to have, to start the kernel. So in this case you need a VM, but that's the first big change for NIPA. The results are still reported back on Patchwork, so that's great. But the main change here that is important for this talk here is that a month later, the functional tests are definitively here. What it means is that we have K-self tests because there are a lot of K-self tests in the network subsystem. And for the moment, and it's still the case now, you have some VM that are running these tests, but that's a big change. Also, to complement that, there are also some web pages to present the result. And again, still important, the results are publicly available. You can access the logs and everything. So at the end, what is NIPA? We could say that it's just a bunch of script, but it's a bit more than that. Because you need to track the patches that are sent on NetDev. You also need some machine that build the test, that build the kernel, and some others that run the test. And you also need to have a web service where you can present the results. But what it is not. So NIPA is not a service to validate non-locally tested patches. So kids today, what they usually like to do is that they do some modification, they then send it, just check the CI after, and oh, it doesn't work. What happened when it doesn't work? I'd fix the first problem, I wait, I send my stuff, and then I come back later. We don't want that on NetDev because to do that, to achieve that, you need to send the patches somehow. So if you start doing that, that will increase the traffic, and we really don't want that. There are already enough patches there. The other thing is that it's not a general testing. It's not for a general testing purpose. Of course, it's focused on the networking part, and we don't want to host new tests over there. There are already other frameworks that are available. You can store the test there. Continue to do that. So why is it needed? Well, it might be a bit obvious, but the main purpose is to help the maintainers and the reviewers. It helped to get quick automated feedback. That it also helped to reduce the feedback loop, increase the trust a bit on the patches. One very important point is that it helped to reduce issues that are seen after merging, because that's something that's really time-consuming for maintainers, that you have something, you spend quite a bit of time in the reviews, and then that's only later that someone else come and say, oh, in my test suite, in fact, this is now broken because of what you did. You could have said that before. That's the whole point of this NIPA here. But when this happens, you, as a maintainer, you need to track what's going on because you want the fix. You also need to ping the right people trying to have something being fixed. If it's not quick enough, you might want to revert, but when it's revert, you need to re-add it later, and yeah, that's time-consuming, and that's something we want to avoid. Another point also is that it's also a bit there to have more control, because here at least we can see how the tests are being executed. We can have an integration with Patchwork, because that's what is being used by the maintainers. And that's it for that part. Now regarding the functional test, what's the current status? So roughly we have a bit more than 750 tests, but that's not counting the sub-tests. So there are really a lot of tests being run. It's just here the number of the group of tests that we have. Among those, only 8 are being ignored. And most of them are ignored because they're a bit unstable when we run them in an unstable, in a debug environment. Maybe for that point, it's not even a big deal that they are unstable, because when we run these tests with a kernel, with a debug kernel config, the main purpose is to see if some new tools can help to detect issues like mem leaks and others. So maybe we don't really care about the end result. Also, to have all the results, it takes approximately 2 hours. That's not too bad. A few VMs are running in parallel. That's really needed to get the result quickly. But one very important point is that it's not covering all cases. So again, don't use just this CI to say, I don't really need to do more tests, I just send them, and okay, if the CI says it's okay, that means that everything is perfect. I don't think that it works like that. So a bit more details now about how it works. As I said before, it needs to monitor the new patches that are sent on patchwork. Then when there are new patches, they are added to a build queue. In the build queue, there are some, of course, build and other small tests that are being executed. Then the results are sent on patchwork. And this takes something like 1 hour, but can take a bit more, of course, depending on the size of the queue and what you are sending. Then we have another step, which is, we could call it the periodic test period every 3 hours. So what's happening during these 3 hours? So first we start by creating a new branch. And this new branch, it's important, is on top of netnext that is merged with net if it's possible. So of course, sometimes there are some conflicts, so we will only take netnext in this case, and then it might happen that some patches that are on top of net will not work, but that should be exception for the moment. Of course, we only take the patches that are in review where it can at least pass the build test. Why do we do that? Because the tests already take a long time. Some of them need to be retried, but also to cope with a future use, which is the hardware test, where these tests can take longer. The functional tests that are run in parallel, so there are different kind of tests with KUnit, K-self-test, BPF self-test, and others. They are run for most of them with and without the debug kernel config. And yes, multiple VM, as I already said. After that, of course, the results need to be published somewhere, but they are mainly published for the maintainers and reviewers. That's an important point, because sometimes the failures are not really problematic, because like, I guess you all know a check patch, and sometimes it tries to help, but it also gives you false positives. And we don't want people that just send and try to fix small thing that doesn't really need to be fixed. So it's more to not tempt them to really try to publish a lot of version. It's better to wait for a review and send all the fixes step by step after the review. At the end, the results are visible on patchwork, and there is also the web UI. We can have a look at that. So if you look at the patch on patchwork, you should see at the end of the check that there is the contest one. If you click on the link, you will be redirected to something that I'm not sure you can read, but basically you have all the tests that are being run, when they have been run. You can also see, of course, the result, the time. And what is important, you also have some links to get access to the logs. And you can also see what is called the matrix. The matrix is helpful to see where what test was unstable. So sometimes if you see that the test is unstable, you might try to understand why is it unstable. So maybe it's not really your fault, but also what we would prefer to is that maybe you will see that and you will see, oh, maybe I should try to help and fix the tests that are unstable, which would be really great. There is also a status page, but that's really for maintainers and reviewers, more to see what was going on, when the next results are expected. So let's not take a too long look at that. But a good reminder here is that it's really oriented for maintainers and reviewers. Of course, the developers can check, they're welcome to check, more to trying to help and trying to improve the global situation. If you send something on the mailing list, that can also help you to prepare the eventual future version, but again, test locally first before posting a new version, and probably wait for the reviews before doing that. Great. So if you still know some issues, you might want to reproduce that locally, because that's what we ask. For the static analytic issues, that should be clear enough, I think. Like if you had a build issue with a specific toolchain, well, you need to install this toolchain and try to reproduce the issue and fix it. For the functional tests, it's a bit more complex, so that's why there is a wiki page on the NIPAS website. So the link is clickable, but not on the screen, unfortunately. But it will describe that you can use a tool that is called VirtMe NG. It will help you to build the kernel and run the test in a VM, if of course you can reproduce that in a VM. Then you can reproduce them manually. We explain how to do that. You will also see that some tools are needed, so you might need to install some very common tools like IP Route 2, but you might need to install a development version sometimes. So that's why maybe it would be helpful that there is something like a container having all the requirements, and maybe the container would be used by the CI to do the validation. So that's something in discussion and might come later. Yeah, so if you want to help and try to extend the code coverage, or if you want to introduce a new feature and you want to be accepted, you might need to add new tests. So there are different ways to add new tests, or at least for the networking subsystem. There is, for example, KUnit. It's a lightweight unit testing framework. So you give some specific input to a function, and then you check that the expected output is there. There is also K-self-test, so some small tests to exercise individual kernel code paths. I will come back to that just after. Or you can also try to deploy a new remote. So you might need that if you have a special infrastructure, like if you want to do some tests requiring hardware, or if you have complex or external dependency, like if you want to do some validation with BPF, you might need that. Regarding K-self-test, quick notes about that. It's really not complicated if you never looked at them. It's just a simple program in user space, and all it has to do is to return a code. So 0, for example, for pass, but now the code to say that this test is skip or fail or orders. There are some helpers in C, Bash, Python for the moment, more can come later. These helpers, for example, they can help to generate an output that is following the tap format, and that's useful if you want to have sub-test support, which is really great because sometimes you might put a lot of tests in your K-self-test, and maybe one will fail, but you don't want all of them being marked as failed. You really want to point out which one was failing. In the helpers, you can also find some tools like if you want to create some network namespaces, for example, there are stuff that really help you to do that, so you don't have to start from scratch all the time. Just use what is already available. An important point is the last one, is that according to the documentation, all the K-self-tests, they should run on any kernel versions. Let's come back to that, because in the documentation it says running tests from mainlines offers the best coverage. So yes, sometimes tests are added later. That's not really nice. You should add the test at the same time as you add the new feature, but that's not always possible. But they also say another point is that to regression test a bug, we should be able to run that test on an older kernel. And that's what some CI are doing, in fact. When they test a stable kernel version, they install the kernel's self-test from the latest stable version, and they run them on an old kernel. That can be tricky, but you really want to support that, because if you don't support that, you can have self-tests with a lot of subtests, like we had one with MPTCP, like it takes half an hour to run, but we added a new case for a new feature, which of course failed on all kernels. And what happened at that time is that the whole self-test, so the whole half an hour was run for nothing, because it will always say that it failed. So you cannot even check if there were regression with the other subtests, because at that time there was no support for it. That has been improved, but that's the kind of situation you want to avoid. But is it really a solution? Because, okay, that's in the documentation, but maybe it's not really feasible with networking test. When it was presented, it was more like, okay, you introduce a new syscall. Well, that's easy to check if it's supported or not. You just try to call the new syscall. If the kernel doesn't support it, you have an error. Okay, you skip the test. Easy. But that's not always possible. Like, you have a new feature, and it's using the socket API. And maybe you cannot do that. I take a random example with MPTCP, because I like that. In v5.6, that's when we introduced MPTCP. And we did that step by step, so there was only one path available at that time. Really useful for MPTCP, but that's just that we needed to do that. But then if you have a test that checks that when you create a connection in with some condition, you want to check that multiple paths are being created. If you do that on the 5.6 kernel, of course it doesn't work. But how do you check that your kernel support this feature or not? Because that's still the same API. It's still you create the connection, you send some data, and you expect to have multiple paths. There are some workarounds, and that's what we try to do. So you can check maybe if some counters are available. You can fall back to some kernel symbols if they are there. That's a bit ugly. Or you can have it even uglier. You can check the kernel versions, and then we have some complaints from Red Hat people who say that, oh, but we backported your nice feature, but the test doesn't work. It's skipped. Yeah, so try to avoid that. But my conclusion here is that maybe it doesn't work, and maybe we need to have some discussion with the people who are running the test that way to say that maybe do an exception for the network subtest. And maybe we can do that because the networking test in K-self-test, they are the most important one, I think. Also, if you count BPF, they are in the same case. We might want to do that. Okay, so another extension that is possible is what I explained before, is the new remote. So if you have some hardware specific that you need to test, like a NIC, or if you have an external test suite that it's a bit difficult to integrate in the kernel, that might be a solution, and you might want to then publish the result on Patchwork. So the main use case for that is if you want to validate some drivers with real NIC, which is in fact a new requirement from 6.12, so the new ones coming, and that's a requirement for the supported driver. So there is an announcement about that if you're curious, or if you're a vendor. But I will be quick about that. It's just that if you need to implement that, there are some helpers to help. Of course, you will need to set up a remote runner, but then from there you will have some helper that will help you to connect to different machines or to connect to different interfaces, like via different network namespaces. But what I really want to discuss here is the reason why we want to have that. It's because we want to improve the feature delivery and the user and vendor participation. So a bit more details about that. What can happen is that what would be the ideal solution is that the requirement and specification could be defined as test. They can reflect use cases, and the end goal is to have them hosted in the K-self-test in the kernel, so we can run them when it's ready. By doing that, we might also increase the compatibility between vendors, can also share efforts, and of course we can avoid regressions, because if someone touches a driver, because they have to touch many drivers, you also want to make sure that it doesn't have any regression in the other ones, that they cannot be easily maybe tested by someone because it doesn't have access to the hardware. To help for that, you can also use NetDev sims for prototyping. Of course, the test doesn't need to be sent up front. You might want to either send them with the implementation or enable them when the implementation is ready. But the idea here is to make the upstream first development model more feasible. Good. The last part of my presentation is to explain how we can have that in other subsystems. Like, this works well for network subsystem, but if you are part of a subsystem of networking, for example, you might want to have that kind of stuff on your side too. So if people send patches on another mailing list, you might want to have the same kind of test before you send the pull request to the NetDev mailing list. So if we look at the global picture here, the workflow that you expect is that you have some patches that are shared on the mailing list and are also visible on Patchwork. You want to have the patches in Git or applied somewhere. You then want to build kernels and launch some tests, and you want to have the results somewhere. So we can look at what is possible and what can help to have that set up on your side. For the first part, there is a service called Patchu, developed by Red Hat. The main goal of this tool is really to monitor a mailing list and apply the patches. It looks like that. I'm not sure it's visible, but we can see in this gray line in the middle that Patchu apply the patches on GitHub, on a GitHub repository, with a special tag. With Patchu, there are also some nice tools, like you can see a difference between the V1 and the V2, for example, that has been sent, so that's also something that can be useful for other reasons. But now, okay, we have all patches that are applied on Git. We can have a CI building them. The expected result is to have something like that. So you have some build that have been run with different configuration, some different tests also with different kernel config, and you want to have the result at the end. Just an example here. For that, you have some requirements. You will need a service or some dedicated server if you have some dependencies, like hardware dependencies. Then you want to run the test, but to run the test, you need to set up the environment. Then you need to build a kernel. You need to run a VM or run the kernel somewhere. If you have a VM, you want KVM support, because otherwise you will see that your test doesn't pass because it's too slow, especially with a debug kernel config. Then you will realize that, yeah, but I'm spending quite a bit of time building, so you might want some cache there, or Git cache. And then you want to catch the errors, because like if you run with a debug kernel config, sometimes it's just that you have a warning in dmesc, but your test can pass, so you also want to catch that. Sometimes it's a bit more complex, like you have kmang leak, so you need to force a scan, and then you need to check the result elsewhere. but there are some stuff that can help here. Like if I take an example again with MPTCP here for the environment, we use a Docker container. So anybody can run this command with a few options that are not visible here because it's too long. But it will download the containers with all the required tools, and then there is a script there that will launch the test and give the result at the end. You can also do many other stuff with that, but that's the main purpose. So if you have a VM, something that can help is to use virtmeng. That's what it's packaged in the Docker containers. So it can be used to build and run the VM. But as I said before, you also want to have KVM support. And for that, many CI that are public, like that are open for open source project, they don't support KVM. So when we started to look at that for MPTCP in maybe 2020, there were not so many solutions that were available. One of them was Cirrus CI, so we started to use them. Was working well, and then they decided to add some time limit. Was not really nice for us. We could have hosted some runner somewhere or something like that, but that's something that is difficult when you are collaborating between companies, because who will set them up? Sometimes it's difficult to have someone like to ask for money to do that. So what was done at the end is that the smallest company that was participating to this project, so where I was working, we had to do something. But yeah, we were hesitating to pay for that, or I mean to have to maintain that service. So we tried to look at the solution that were available. So that's why we started with Cirrus. Then we were stuck because there was the limit. And to avoid the limit, we started to use GitHub Action. But that was without the KVM support. So we tried to have a runner. I tried to have a runner at home, but the one who owes me, I only have a 20 meg downstream, 20 megabyte per second line, which is really slow. I didn't want to clone the repository every day, multiple times a day. But that was good because at the end, they changed the runner at GitHub, and you can have KVM support, except that it's a bit hidden. So it's opt-in if you want to have it, but that's possible. Small thing, you also want Ccache. Just to speed up a bit the thing there. You don't want to have the build taking long and long. You also want to catch error, as I said before, and maybe for that there are some shared resources that can be used, because at the end that's always the same keywords that you need to try to find in the logs. So there are some solutions here. Once you have the build, you want to publish the results. There are different things that can be done here. But on, I guess, any service, you want to publish the logs. That's certainly easy. Publish some more artifact, like debug stuff. Also certainly easy to do. You might also want to show the last result. And with kself-test and many tests that are in the kernel, they use a tap parser or different version of it, but there are different tap parsers there for this format. And you can also convert it to other formats. So that's something that should be easy to do, but still need to be done. And last point is that you also want to check regressions, because sometimes tests are unstable. You want to see when it was unstable last. And for that, there are nothing on GitHub, or nothing that I found. It was nice. So we ended up doing a homemade solution, copied from NIPA, in fact. And that looks like that. It's just that you want to see when the tests were run. It's just that the failure was at the end. I had to cut, so that's why it looks all green. But that's the idea. It wasn't stable at that point. It was just something wrong at that time that has been fixed, so that's fine. But there are still quite a lot of different things that you need to assemble there. So if you're interested by doing that, maybe easiest is to contact me. you can also look at what we are doing for MPTP. There is also the container, and see what we can do with it, and copy some of the part for your side. But there is kind of a trend that is coming here, where, or at least in the DRM side, they would like to have something where all the subsystems can easily have their tests being executed somewhere. They are talking about GitLab and that kind of thing, so that's because they are using the free desktop infrastructure there. But they are open to discussion. So there is maybe something coming. I will try to participate to these discussions. But if you are interested to have some tests being run in other subsystems, don't hesitate to contact me and join the discussion, because there will be hopefully something easier in the future. And that's the very last part of my presentation. Just some discussion if we have time. Just to see, maybe to discuss what is missing in NIPA, if you have some ideas, or missing elsewhere, CI related, don't hesitate to interrupt me. Yeah.
Okay, so I have a question. Does the bot infrastructure do bisecting if it finds a regression? Can it point to a specific commit now?
Done by who? Sorry.
Did it,
the regression that are done by?
If the infrastructure finds a regression, can it point to a specific commit? Can it do bisect?
Not with this infrastructure, no.
So not yet. Okay. So maybe that's one suggestion.
Yeah, but for example, for MPTP, because it's really easy to reproduce the test locally, like with the command that I put at some point there, that's also very easy to do the bisect locally, because you just need to run the command there after when you do the bisect, and it will run all the tests, and we do the report. But that's not something that can be done on NIPA or with the NIPA infrastructure. But if there is a container, for example, that is there, that's also something that would help to do that kind of thing. But I think the goal is really not to have NIPA doing the bisect for you. No. But that's something, yeah. I don't know, maybe there will be more resources later.
Okay, thanks. Another question is whether, because regression can be, for example, if throughput is lower than it was in the previous build, so it has to, the infrastructure has to remember some information from previous. Does it currently, is it capable of that now?
No, and if I'm not mistaken, we are trying to avoid having to track that, because
so you want to make it stateless?
Yes.
Okay.
But that's something important, and that's, yeah.
We can store the data, but we don't want to be responsible for like tracking it ourselves, right? Because it's very prone to false positives.
And last question, you mentioned that so does this NetDev bot infrastructure only use virtual machines, or so no real hardware testing?
Not yet, but
okay.
That's coming.
And are you? Would it be possible to send some boards for testing, so to your farm?
So do you mean to?
Or to provide some boards?
Some boards. Sorry, I didn't get it. Yeah.
We don't have a lab right now. These are just machines in AWS. We are trying to get the vendors to participate a little bit more, so we can have someone who actually has a lab, and we can send all the hardware there, but nothing materialized
yet. In my experience, performance testing is like completely different game than functional testing, so I would suggest to separate it. And also for performance tests, usually in my experience, it's very hard to compare old results with the new ones, because it's not it's probably not going to be 100% stable because something will change. For example, just the switch in the test infrastructure will burn down, so you will change it for some other switch, and suddenly the results will be different and it will have no relation to the code changes whatsoever. So if you want to do performance tests, you have to have the ability to basically run the old version, a new one, like every time, so you can compare it on the exactly same setup. Otherwise, the old results will be, nonsense after some time.
Yeah, it makes sense, but that's also the reason why it's not there yet. Not in this plan for the near future.
Yeah, I'm trying to say that it might not be the best goal for the near future because there is lots of work before that.
Thank you.
Would be really nice to add some, I don't know, PyHole div to warn about like introducing new big holes and paddings, because people love to do that, really, sometimes. And also regarding the previous presentation about CFAR, I think this could play well. CFAR could just say, hey, your patch increases cache line usage here and there.
Yeah. Yeah, but I think that kind of test can be easily added by anybody. I think Sabrina is looking at some stuff with the UAPI. That's something that can, you don't need to have access to the machine to add them, so anybody can add that kind of test. But yeah, definitively we would like to have that kind of test there.
For what you mentioned, that tests should be running on all kernels, I feel that is pretty straightforward. If you want to test a new capability, that capability should come with some sort of probe. A Netlink command, test for a sysfs file, something. How else is a user going to know that the capability exists?
Yes and no. In our case with MPTCP, not everything is exposed. Because, of course, we didn't have MPTCP with all the features from the start. So at some point, a feature was not present, but it's something that is managed by the kernel, not triggered by the user somehow. And you still want to validate it, but there is no interface for the user to know that.
And that's missing, I would say. If it's a new capability that exists in the kernel, there should be some query to see that it exists.
In that way, maybe. But I don't know which interface we would use then. Because, for MPTCP, we are limited to the socket API. And I don't think that we would add up front, get sockup stuff, to say, is it available for everything that can be possible? That's hard to put in place. I understand that something can be put in place, but that's really hard. And at the end, the user might not care about that. It's just that we are validating the implementation. And that's it, yeah. There are some very small things, there are some retransmission that can be done on some very specific packet. If it's not there, okay, it doesn't work as good, but it works. If it's there, that's better. But does the user need to know about that? I don't know.
Yeah, but then it's questionable whether you need to add a test.
Yeah.
And it might not be only a new feature, and maybe that's also more the question, if I did something wrong here. I just recently, last week, added a test that on older kernels will crash the kernel. Because there was a bug in the kernel, and I added a self-test, and it will crash the kernel if you have not applied the patch that comes with it. Does this count as run on old kernels? Because it will crash the kernel? I mean, it runs, but it crashes then in the end.
Yeah, but for me, the idea would be that you have a fix, you attach a test with it, and both the fix and the test are backported, and that's the backport that is being validated.
Okay, so it's the expectation, it runs on a properly backported system, not on you take any kernel version from somewhere, some random kernel, and it just runs. It's just that you on the stable kernels or on the backport, old stable, you expect it to run. Okay. Okay.
Because it's time, but I didn't.
Hello, I'm from Sysbot team, and the question is like, the coverage artifacts downloadable here?
No.
No way.
I think the reason is that we are a bit ashamed of the current code coverage. No, it's not possible for the moment.
Okay, any plans to add them?
Is there a big impact?
I'd like to direct further towards the areas not covered by tests.
Yeah, but I mean, if we run the test with the code coverage, is there a big impact for, like for the test itself? Like, if we introduce that, could we have more tests that are unstable because it takes more resources or something like that? Because I think that that's the main point. If we add new features that help, of course, I know it's helpful here, and that would be really great to have it, but if it impacts the test and make them unstable because it takes a slightly longer time to do something.
I don't have the answer.
Okay. Yeah. Also something about the test coverage is that it's also very difficult to have a big test coverage for the error path. That's where Sysbot is really helpful, because it can find many crazy ways to find error paths. And when you design a self-test from user space, sometimes it's hard to, like, you need to inject some fault somewhere. And from user space, that's not always easy to do that. So
All right. Thank you. Next talk by Daniel.
Shall we start? Okay, cool. Hey, thanks for coming. I'm Martinas. This is Daniel. There's Anton. So we all work on Cilium, which back in the day used to be just a BPF-based container networking plugin for Kubernetes. But since then, it evolved into standalone load balancer, egress gateway, service mesh product, and so on. And the reason I'm mentioning Cilium is that all the performance work, VideoGuard performance work, was triggered by its usage. And yes, so some historical context. So in 2019, at Linux Plumbers in Lisbon, we presented our load balancer for Cilium, BPF-based one for east-west, north-south traffic, L4 traffic. And basically, after that presentation, we started looking into implementing more advanced use cases for the load balancer. And one was adding encryption. So on the slide, you can see the very typical north-south packet path, like node 1 gets a request which needs to be load balanced. The BPF program, either at the XDP layer or TC layer, does the decision, picks the load balancer application, and then forwards the packet to the destination node. And the problem is that that packet is being forwarded in the clear text, and some users might want to encrypt it, like depending on the underlying network, which they might not trust. And back then we had, in Cilium, we had the IPsec integration, but unfortunately it was relying on the host networking stack to do the encryption, so on the IP transformation framework in the kernel. So in order to encrypt this packet from the BPF program, you have to pass it to the stack, then IP transformation policies will pick the packet, do the encryption, and then we need to recircle packet back to the BPF program. So we cannot just do the BPF redirect to encrypt the packet. And also, the integration relies a lot on the TC index and SKB mark, and both are very scarce resources in Cilium because we tend to encode our state there. And also, we didn't have any like key rotation back then, so we started looking into alternatives, and one of them was VidaGuard. And back then we had some experience with VidaGuard because we were running in the CI to test Cilium's L2 to L3 and L3 to L2 NetDev redirection. And basically we started to look into that integration, and yeah, it turned to be fairly simple compared to the IPsec, and mainly because with the VidaGuard you have a dedicated network device to which you can just redirect the packet, and that network device will do the encryption, and you can attach the BPF programs to ingress and egress. And we decided, yeah, to add it to Cilium, and the integration turned to be very like simple, like that simple. So each Cilium agent generates public-private keys. Public keys are being exchanged between different nodes managed by Cilium, and then Cilium creates the VidaGuard network device, sets it by using the generated public key with the private key, and also adds basically the list of endpoints, which are the container IPs, and that's it. So the packet path for the container-to-container traffic is that the VIF device, from the VIF device to which we attach the BPF program, we can redirect to F0 network device, and on that network device we have a BPF program, and that program can decide whether a packet needs to be encrypted, and then we pass to the VidaGuard device, it encrypts, sets the SKB mark, again forwards to the if0. In if0 we check whether the mark is being set, because otherwise if we pass it back to the VidaGuard device we'll end up in a loop. And then we pass to the remote node, the packet is encrypted, and it's very similar on the receiving side. And basically back then the VidaGuard in the kernel, it was fairly new citizen. It was upstreamed in 5.6 kernel, and in Cilium we supported 4.9 kernel. So we added the user space integration, but we never considered it being very serious because yeah, it's running in the user space, so it might have a very bad performance compared to the in-kernel implementation, and also yeah, like stuff like Cilium control plane restarting might cause some packet interruptions. And yeah, basically the performance thing was the main thing, and then yeah, we said like, okay, just experimental code, but then some blog post appeared. So passing to Daniel.
Yeah, so in April last year actually, there was a blog post from Tailscale folks. They were using WireGuard Go, and they basically showcased how they improved the performance of it. So this got us quite interested. So basically what they were doing, they were leveraging UDP GSO and GRO. The whole thing goes through a TON device. And yeah, the implementation is basically in Go. And they managed to improve the performance in their blog post, which they described, from around 8 gigabit per second to 13. And in comparison from what they saw, like from the kernel, it was around 11. So they basically managed to overtake, which got us interested to look a bit deeper into it, whether whether there's low-hanging fruit initially to potentially improve something on the kernel side as well. So yeah, we only started recently looking into this. So basically we did a benchmark back-to-back 100 gigabit ConnectX 6 NICs from Linux, couple of tunings for future reference here, And yeah, so basically that's what we got, like bare metal back to back in the host namespace with the standard MTU of 1500. Without any encryption, we're around 46 gigabit per second. With the WireGuard Go driver, we managed to get 8 gigabit, and the kernel just like 5.7, which is not really great. We also looked into this in terms of higher, like increasing the MTU. So using an 8K MTU, we basically managed to get like as a baseline 72 gigabit per second, and the native driver in the kernel actually looks better here. So we actually got to 20 gigabit. In comparison, for the WireGuard Go, it was around 15 gigabit per second. Yeah, in terms of the transaction per second, what we found was that the native driver has a higher TPS than the WireGuard Go, like on smaller MTUs, and very similar also on the larger one. So the question is, yeah, is there something we can do better? So looking into the WireGuard code, basically, you know, how it does, like in terms of GRO, GSO. This are probably like obvious candidates to look into first. The GSO, it's basically, there's nothing registered from the driver point of view. So basically, once the packet arrive on the physical NIC, it will try to GRO aggregate, but there's no callback or something like this. So the packets will go up the stack individually. And once they hit the WireGuard UDP socket, WireGuard then decrypts, and then it will try to aggregate through NAPI GRO receive, and then it will go up as a batch. In terms of GSO, the kernel stack basically will send a big packet down, and once it hits the WireGuard device, the WireGuard will basically do the software segmentation, so that it will create individual packets, and then after it did that, it will encrypt them. And one of the reasons why is because you cannot just duplicate the headers, because in the protocol there's a counter or nonce for replay protection. So yeah, that's why there's the reason to call the SKB GSO segment first. So yeah, in terms of potentially low-hanging fruit, we looked at the Stefan's ESP offload, which is basically the idea is to register a GRO callback from the UDP socket, and we looked at the XFRM code in terms of how it would do the GRO aggregation, and what it basically does is it steals the packet from the GRO engine and decrypts them, and then aggregates them, and then pushes them up as a batch. So that's on the GRO side. On the GSO side, we try to add the big TCP like flag to enable it, to see whether this helps in some way. In terms of the implementation, which is probably a little bit hard to see here, but yeah, we are basically registering a GRO handler, and when we see data packets, we are pushing them right into the queue that WireGuard has for the decryption, and then stealing it from the GRO engine, which is basically done through the return code with E in progress, which tells the GRO engine that it's consumed. And then once it's decrypted, as I mentioned earlier, there's the NAPI GRO aggregation, and it will push it up the stack. One thing for discussion, in the ESP offload, it's basically done through a kconfig, and it actually turns out that seems to be enabled by default in distributions, at least in Ubuntu. I double-checked whether it would be useful for the WireGuard at least to have it as a device attribute, because it changes the behavior for the stack, because, for example, if you would run TCP dump, that might not be visible on the physical device anymore, because the GRO happens earlier. Or through a sysctl, I'm not sure. Like, probably more useful as an attribute in the device, and or kconfig, whether we should do something similar, or yeah. If anyone has opinions, I'm happy to hear. Okay. So looking at the netperf TCP stream for the 1500 MTU, the combination together gives a small improvement, 15%. And yeah, it's still less than what the WireGuard Go implementation has in the user space, but probably worth it to you know, submit. In the case of the 8K MTU, what we saw is that the L2 based GRO actually gives, you know, also like slightly better performance improvement. The big TCP enabled as a second step, it's slightly worse. But yeah, overall, like there are some things to get out of. In terms of the transaction per second, yeah, it's helps a little bit. So yeah, this was basically for the single flow. Then the next question was, what about multiple parallel flows, right? Because as Martinez mentioned earlier, like Cilium creates a single WireGuard device, and then all the east-west traffic from the pods, they get pushed through that device. So it was question is, how does it perform here? And yeah, it turns out not great. Because there's no RSS scaling. Like if you look at the packets on the wire, the source and destination ports, they are like basically the ports that you configure on the WireGuard device when you create it. So they all look the same. So all basically hit one CPU and doesn't scale very well. So we are basically stuck around like 25 gigabit per second for just like 4 or 5 streams. It doesn't get better, it rather gets worse. So the question was if there's anything that we could do to improve, at least maybe based on without changing anything. So the idea was, okay, can we create multiple devices and then have them under a bond, for example, and the multiple devices, they would have same config, just different listen ports, so that you can actually distribute the traffic across different CPUs on the receiver. But it turns out, yeah, like for the bond, it's not possible because it expects an L2 device where I got is L3. There's like one trivia, there's a missing set MAC address, but even if you implement like a dummy one, so there's definitely more work needed to support something like that. So like out of the box, yeah, didn't get it to work. Generally, it would be nice because you just have a single device. So like from a BPF point of view, you don't need to, it would just be like a drop-in replacement. But yeah, it's currently not possible, at least without extending bond one way or another. Yeah, the other idea was to have multiple WireGuard devices and then like load balance through multiple next hops. So from a routing point of view, that works to configure, but then the problem is WireGuard itself. So it turns out that somehow there's a bug inside the WireGuard driver that we still need to fix, because the allowed IPs, for example, if you have all of them the same across different devices, they get overwritten. Basically, suddenly it will be visible on one device, but on all the other devices, they will basically replaced with none, so that it will drop all the incoming traffic. So that's something that still needs to be done. So yeah, what about different listen ports and different key pairs? I mean, it will end up in the same situation, so that was not possible. So just to see whether the idea would bring something, basically what we did is like to completely, configure all different IPs so that there's no conflict across, among the different devices. So yeah, looking into the performance of that, like for the parallel streams, yeah, it gives quite a bit. So like 70% better throughput in total when it's load balanced across the different CPUs. So that's definitely something worth following up. Similar, there's improvement for the transactions per second for the TCP/RR based workload. So yeah. Some of the other findings that we had while testing, what you can see here is a flame graph, and actually in the WireGuard basically calls SKB copy and write data on shortly before the decryption, because it will do the decryption in line, and it will then call PSKB expand head, and internally it will clear the pages. And it turns out that this is actually something I missed earlier, like while doing the benchmarking. That's something that seems to be enabled by default on all the distros. And yeah, thanks to Eric for the hint. So basically that's like a kernel hardening setting, which initializes all the allocations by default in the kernel. So like this is even, slightly more or like as expensive as the decryption itself. So like the promise that's like for synthetic workloads as high as 7% is I would say not quite accurate. But I didn't manage to remeasure before I got here, but it's something to look into, and maybe like also to have something to opt out if we know that we are overwriting this data anyway. So yeah, I think like as a next step, what would be really useful is to potentially have a new mode in WireGuard where we can say that we want to hash the source port with the actual tuple from the inner packet, and use that as a source port instead of like the listener port. So this would basically expose the hash, but on the other hand, you would be able to make use of RSS, and I don't think it would be a big issue to expose that. That would assume that you would only have like a potentially like a single device on each node. So very similar to what the way that VXLAN would do it. But it would probably have to be a new mode, so that because it would not be backwards compatible with the current one, with the current implementation. Then another thing that would be useful to experiment with. So there's this multi-core crypto operation where you basically, this is very visible when doing the NetPerf performance benchmark. So when you do a TCP stream and pin the sender and receiver to a single CPU, you can see on the that basically all CPUs get busy, right? So that's a scheme that was implemented in the driver to distribute the decryption among different CPUs. But it would be interesting to experiment whether, like I would presume like all the caching and everything, it might be more beneficial to just stick with a single CPU. Might also simplify the implementation potentially. And once we have the RSS, yeah, that should hopefully improve the performance even further. Some other things. What can be done here, and I think there hasn't been too much work in that area yet, is also the cache length groups for the receive and transmit, and for scaling among lots of flows, there's actually an atomic counter which is shared across different CPUs, which is currently on the per peer queue internally that the WireGuard has. So that seems to be also a point of contention. Yeah. So those are like some of the next steps we will try to experiment with to improve the performance of the driver. And yeah, that's pretty much it. Are there any questions, comments, feedback, other ideas?
I have a question. So for the GSO, you're saying you're breaking up the packets? It's not doing GSO under the view?
Yeah, it's basically segmenting inside the driver. So like the big packet comes to the WireGuard, and then it's doing that.
So the nonces are part of the payload, right? And it's UDP segmentation. So as long as you maintain the right format inside the payload, you can do the same thing as Quick is doing. The packets, the packets are the same size, right? So
yeah.
So you can just like inject in between the frames the space for the headers, do the crypto, and ship them as one.
Okay. Yeah, we'll take a look if that's possible.
Questions? I saw someone was raising their hand.
I suggest to take a look at VirtualNet in QEMU because we already have a BPF classifier for RSS. And actually, Akihiko, who is here now on the conference, is working to push some kernel patches to have the hash reporting for kind of general network devices. So I think it will help what you're doing. So probably a good idea to cooperate. We also have not GRO, but rather RSC, which is kind of Windows-specific code inside of QEMU that aggregates the packets, so it also might be useful.
Okay, yeah, thanks for the pointer.
Just wanted to understand how did you compare the KTLS instead of using the WireGuard here?
No, we didn't look at KTLS.
On that?
What?
Any thoughts on that?
Sorry.
Any thoughts on that? Like, why not KTLS instead of WireGuard?
I mean, like for the KTLS, you would have to have, like opt-in support for the specific applications. But we basically just wanted, this to be transparent and for all the pod traffic that goes east to west. So yeah, I think that's like apple and oranges. I would say like to yeah.
I happen to know of someone who's trying to do the same thing with KTLS.
Okay.
But on the what I wanted to say was the crypto fan out thing that you were talking about. I believe it's there to optimize for single flow throughput, right?
Yeah.
And obviously you're multiplexing a lot of traffic across of different flows across a single device, and then you're probably right. It would make a lot more sense to just inside WireGuard just treat each lower level flow or upper level flow individually and not do the fan out. But then that is going to regress single flow throughput, which people want. So I suspect it may have to be like a different deployment mode or something and require quite a bit of surgery to get rid of. But that could also be an option of just having two different modes. Right.
Actually, just before the break, I was talking with Stefan. You mentioned that the WireGuard actually took this as an inspiration from XFRM, but later on you got rid of it, right? So maybe you can comment about it.
Yeah, so that fan out was good as long as crypto was much more expensive than pinning packets to CPUs. But with that change, we have ASNI, and crypto is rather cheap. And now, so pinning the packets to different CPUs eats up the benefit we get from multi-core here. So that's why we invented something new in IPsec. So what we're now doing is we are pinning the crypto context to each CPU, and so we can just send the packets through independently in the data plane.
And the encryption decryption happens on the local CPU, right?
Right.
Yeah. Okay.
Just a thought here. Have you considered abusing IPv6 flow label for fan out?
Yeah, I've heard the suggestion as well. The problem is, like, unfortunately in the real world, like, the users we are dealing with, they are all on IPv4, which is very sad, but that's the reality.
Understandable.
But yeah, that would be another option. I agree.
So I was playing with other IPsec implementations, and I didn't get results as good as yours. I was testing with in a VM, so host to host. So have you tried to test on VMs?
No.
Okay. Another question is, I got the impression that you are doing encryption on the CPU. Have you tried or considered offloading it to the NIC?
I don't think there are offloads available, at least not to my knowledge.
Okay.
For WireGuard, yeah.
For WireGuard, okay.
Yeah.
There is actually a WireGuard offload available for FPGAs, and it's open source on GitHub. But that's very hardware specific and not Linux kernel specific.
You need to go by FPGA, yes.
Exactly.
Have you, I mean, certainly not an easy task, but have you considered doing the actual crypto triggered from BPF directly? I mean, since we have now the crypto API in BPF?
I mean, I haven't. I mean, but it would.
WireGuard is not using the crypto API. Not at all. Even okay.
Yeah.
Okay.
But I mean, the other idea was also to make it useful and faster, like by default outside of BPF, right? I mean, like.
Second.
But I mean, like the rationale to improve it and look further into that, like into improving the drivers to make it useful also without having to use BPF, right? So
yeah.
Basically, yeah.
Thanks.
Thank you, Daniel.
Yeah, thanks.
All right, last but not least, Dave is going to talk about Bufferbloat. Take it away.
All right, can you all hear me? Can you all hear me, guys? I am getting nothing back from you guys. Remote can hear me. I can no longer hear any of you, which is cool, I guess. I guess I get to talk in perfect silence. Anyway, hi, I'm Dave Tott. I've been doing the Bufferbloat thing for almost 15 years now. And back in 2012, we solved the problem. And watching the deployment go by very slowly has been very difficult. That's what I'm going to talk about today. I'll try to speak up. My microphone is there. Is this good? This better? All right. So the executive summary of where we stand today after 15 years of effort is that most ISPs still have Bufferbloat, but there's a lot of positive things happening in the quality of experience world and in Wi-Fi and on Starlink. I'm coming to you live via Starlink today. I'm hoping that I come through okay, aside from me not talking loud enough. Smart queue management has become the default for smart users to go manage buffer-bloated networks. Uh-oh. What? What's wrong, Jacob? I can't get any closer to the microphone than this. Can I shout? Oh, okay. You guys have a different tool. So I can play music while you do that, or I can just recite poetry or whatever you want me to do. Okay. Shall I keep testing? Testing, 1, 2, 3. Testing, testing, testing. Watching the chat go by. Well, I can increase my volume too. Cake is in partly a backronym. We were picking on a different algorithm called Pi, and it just stuck. So we gave it a backronym called Common Applications Remain Enhanced, and that's how it ended up. All right, back to my topic here. I'm hoping that everybody in this room knows what Bufferbloat is. Those of you that do know, raise your hands. Cheer me up. Those of you that are paying attention, raise your hands. So I still have to explain it to those of you who don't have it up. Basically, we have a funnel that connects everything to everything else. And at 100 gigabits, this funnel's egress is really, really tiny to come out at 100 megabits. And algorithms to manage this properly turn out to be really complicated and difficult. So aside from that, there's been wonderful presentations, and everyone that had their hand up that knows what Bufferbloat is, go bug them. Okay. So we're good on volume. All right, thanks. So today I'm going to talk about the state of the bloat in the two countries for which I have data for. I'm going to talk a little bit about the kernel. I want to apologize. In the past few years, I haven't been able to pay much attention to kernel development. I'm mostly hanging 10 versions behind in the embedded versions of the world. I'm also going to talk about bloat of the cloud on Ethernet, 5G, and Wi-Fi, and Starlink, and 2 new Bufferbloat.net projects starting up this quarter. So this is the Measuring Broadband America report put together by the FCC. And it illustrates the scope of the problem in building the metaverse, having reliable gaming, being able to multiplex Zoom while doing big uploads and downloads. And at the 95th percentile, we see a latency inflation under load of several hundred percent. And at the 99th percentile, it's even worse, and you don't even want to talk about the maximum. And this is after 10 years of trying to deploy fixes. We still see latency variations, like just to give you an idea, looking at the fiber. Fiber's great, right? So the goes from 7 milliseconds to 120. And while most of our protocols have been designed to handle this kind of stuff, we still have jitter and things freezing and stuff like that unless we actually focused on trying to reduce peak latencies across the internet. Another country that did a report recently, they've been doing one quarterly. This demonstrates all the different technologies and speeds available. The idle latency is the first bar. So to pick on fiber, 300 megabit fiber, the baseline latency is 10 milliseconds. And the peak latency on this particular test with the levels of additional statistical ledger domain is 42 milliseconds while you're actually using the link. And with the techniques that we've developed through the Linux and the Bufferbloat project, we have the ability to keep those latencies relatively flat under load, but they really haven't deployed. It turns out that if you recalculate these against the actual speeds, it turns out that almost all these devices have 1,000 packets of buffer, which is 10 times too much or more. And they don't have any smart algorithms like F2CODL to actually manage the systems. So the technology is done for most of us in the Linux world. It just has to deploy. And expressing to the public that bandwidth isn't everything has been a large portion of what I've been up to for the last few years. And if ever any of you have a feeling, want to take a pot shot at your local regulator to explain that latency and bandwidth are two entirely separate things, please join us. We had a lot of fun with this one. Over here, I have now managed to explain to the Republican side of the FCC that what Bufferbloat is and what latency is. I had a chance to play with Ajit Pai, backing him up while he sang a couple songs, and then I explained to him that all the headaches, most of the headaches he took from Bufferbloat from the network neutrality controversies were actually generated by Bufferbloat, and he gets it now. Not seeing a whole lot of clue on the other side of the FCC so far. So over the years, we've developed a lot of really great tools for measuring latency under load. The premier one is Tokyo Jorgensen's. He's in the audience. Wave. Their Flint suite. He just landed version 2.2. That has 120 tests that can plot over time all the differences in network behaviors you can possibly see, and I really wish more people used it. Bob McMahon is the author of iPerf, and iPerf is used pretty heavily in this community, but it seems like none of you have looked at the progress that's been made in measuring additional statistics in the latest versions of iPerf. So please check that out. There's a new tool called Crusader. It's written in Rust, which is the first tool we've had that tests the right things for latency and load on everything, including Windows. There's a new one I'm going to talk about, just landed yesterday from Dave Seddon, called XTCP2, which allows you to monitor existing applications and containers to see what the round trip times and throughput actually are. There's a new one called Network Quality from Apple, which is written in Go. It has all kinds of other stuff. I have a tool I've not had time to work on called Where is the Bufferbloat? And if anybody wants to help me on that. And over the last few years, every single major speed test site has added metrics to measure latency under load. This one on the right here is a copy of what Netflix is doing. They sit there and they measure what the responsiveness is, which is measured in this case in milliseconds. So at a given download thing, they have a worst case of 480 milliseconds on the download, a half a second of additional latency, which tends to interfere with interactive traffic. So Dave Seddon's XTCP landed yesterday, and basically it allows you to dump TCP diagnostic information, not just round trip times, to the cloud and be able to analyze what the heck is going on behind your containers. Now, in watching kernel development in the last quarter and knowing I was going to come to this, I was really happy to see VirtIO BQL. VirtIO Net got BQL, and they saw significant advantages while running TCP stream against TCP/RR. I think it's possible to do better than that. But one of my concerns going forward with the BQL subsystem is you end up with one queue per core. And as you add cores, you have a static latency living below FQCODL where it cannot be managed. Now, I just did this math real quickly. If I've got this wrong, if I'm off by an order of magnitude, but it looks like it's over 8 milliseconds of data can get stuck in the kernel at 10 gigabits with 64 cores and 64 queues. If I got that wrong, forgive me. The other one that bothers me in dealing with the cloud is all the additional stuff living in hypervisors and VMs and containers and in the proxies themselves and in sendbus. And anytime that the CPU is able to outrun data that's going to the wire. Similarly, NAPI was a really great idea when it first came up. And we had this magic number of 64 in there before we start cleaning out the queues. And again, multiply that by the number of cores and your latency has a worst case bound that goes higher. And overall, we have this gut feeling in this community that, oh, milliseconds is enough. And I know I'm an extremist, but going for 100 microseconds or a microsecond for anything involving the difference between processing time and TCP time is there. Remember that a packet at 10 gigabits is only a few nanoseconds long, and yet it takes milliseconds to process one. So if we can keep thinking about reducing latencies, it would be great inside the kernel. So I just enjoyed the Cilium presentation. There was a bug that went by, a few months ago, back in April, that talked about their bandwidth manager. And the initial implementation of that had over 2 seconds of latency. I want to apologize to that crowd for losing my temper. But if more of you could review the bug and the progress of the bug, you'll have a much more intuitive understanding of why Bufferbloat exists and how we can possibly fix it. Their method is different from most others, and I don't know if it'll be widely adopted in the container community or not. My biggest problem is that I thought that once we got FQCODL and BQL and all the embedded hardware in the world, that magically Bufferbloat would vanish from the edge. And it turns out that kernels do not get upgraded very rapidly. It's almost running 10 years behind Linux kernel development. And been at this for 10 years now, and I was looking at these global statistics saying that have we actually made a difference? And For smart users, we really have, but for the typical Joe average, probably not. And people are just used to it. So a couple years ago, someone came up with the idea of creating middle boxes that can run things like Cake and FQCoddle. A company called Preseam pioneered this model in about 2017. Another company called Bequan adopted FQCoddle as their secret sauce to do interception and management of latency at layers 3 through 7. Paracom adopted DPDK and Cake, and LibreQOS, which I'm now a part of, started in 2021, which used all the latest and greatest stuff that I was so annoyed it wasn't deploying yet. But together we've got less than about 3% of the entire ISP market and a bunch of other players like Sandvine not paying attention. So a brief plug, LibreQOS is open source. We have over 175 ISPs around the world, particularly stuff in Africa has been very exciting, as well as in Australia, New Zealand, South America, other places where the bandwidth is low and the latency is high. We've made a big difference for the quality of their video conferencing, etc. I want to thank NLNet for funding most of the development effort so far. In addition to the shaping stuff, we learned that getting cool network monitoring tools in normal users' hands was useful. And I'm hoping that those of you that had the time to go install LibreQOS and play with it will get a really good kick at the level of detail we're able to extract from almost any kind of network. So, for example, I'd love to see someone fiddling with WireGuard there. This is a SAN key at the bottom here, which shows a very complicated ISP network, over nine layers deep, over several hundred towers. And this particular plot shows stuff being green. It wasn't green when this guy started optimizing his networks using LibreQOS. The other cool plot in this one, and there's dozens more, there's things like mice and elephants and things like that. This is what Amazon Prime video streaming actually looks like in terms of its buffering across the system. And I'm kind of puzzled always as to why it is so random looking. It should be much flatter than that. But maybe that could be problems in the cloud. We don't know. I don't really want to make this an ad for LibreQOS, except open source, go install it, check it out, and tell your ISP about it. Because when you do this, when you actually manage the latency at the ISP first, you're able of getting a millisecond or 5 of additional latency on everything that you do, which is so much better than the worldwide reports I showed you earlier. And then there's 5G. It's wonderful we're seeing higher and higher 5G speeds, but this is actually a good number. It's only a quarter second of latency under load. There's lots of other problems in 5G. I don't know how to fix it. Toki's link over here is over 200 milliseconds when you use it. Ideally, you want to be below 20 milliseconds. Another piece of how 5G operates is how bursty it is. And it turns out that they have a native reorder buffer that will put in another 200 milliseconds of latency just because packets must be delivered in order across the multiple channels. Anybody here working on 5G? Making it better? Implementing anything? I see Toki looking around. Toki, are you nodding no? No one's working on 5G? Look, guys, we use this stuff every day. And it runs Linux on top, usually. It would be awesome if we could make some progress on fixing the bloat in 5G. On the other hand, Starlink is looking really awesome. I'm coming to you live over Starlink, and I'm hoping this is pretty good. In a matter of months, Starlink managed to improve their median latencies by over 60%, and they've been at it for about a year now, and across their entire network, they've really optimized for interactive traffic. If you look at, I have some plots showing how badly it works for TCP, but it turns out not to matter as much if you want to have a good video conference. A little packet loss is just fine. Who knew? If I could get more ISPs and more people to look at the kind of parameters they use to optimize their networks, the internet would get a lot better, a lot faster. And most recently, last week was a really marvelous week. They conducted a 40-minute video conference from space. That was almost entirely uninterrupted. They were only talking to one satellite. And over there is an OpenWRT box bolted to the sides of the spacecraft. So all of you have worked on Linux and on Bufferbloat and on so many other things. Be aware that your code is flying in space now and was used to make a really wonderful, wonderful video conference last week. Now, I still pay attention to a lot of the research. There's thousands upon thousands of articles about doing congestion control better. And this year alone, there was 4 that went by that looked really interesting. DEQ-AQM annoyed me because it claimed it did better than Cobalt, which is Cake's congestion control algorithm, and I haven't had time to look at it. I think that slow start is the biggest source of jitter and latency the internet has, and search posted that seems to improve slow start somewhat. Also, the really exciting one, and the thing I would love someone to verify, is the ETSCCC, which uses microbursts to detect bandwidth availability pre-congestion. It's a really simple and elegant idea, and the paper was excellent, and I disbelieve it. I want to believe it. It'd be really cool if someone looked into that. And fairly recently, a very good version of CODL 4P4 landed. So if any of you are using Tofino switches, you might be able to control your latency a little better. Kind of an active part of the Bufferbloat project has been Make Wi-Fi Fast 2. This was originally run by Toki there, who managed to improve Wi-Fi's latency by by a factor of 50 or more. And that's now the default driver set for most of OpenWRT and all of Linux. I am a huge fan now. This is a MT79 board. It's 4 in order A53 cores. It's pushing over a gigabit beautifully with consistent latency and a lot better than the vendor drivers. Because uptake in the world is taking so long, I would love it if more people here, or at least one person here, was going to the 802.11 meetings at the IEEE, because I would like to make sure that these kind of modifications we've made to how the stack works make it into the next version of the standard. So if any of you are going to 802.11, get back to me. The biggest new project I got going is I finally got some funding from NLNet and Comcast Research to go fix a bunch of minor bugs in FQCODL and Cake across a bunch of other operating systems, including Linux. And we're going to try to take a look at real traffic and real workloads from the LibreQOS perspective to see what more we can learn and modify. And the biggest problem that I think that Cake has is it really needs to be multi-core. And that turns out to be a really thorny problem that I would love to attract some people to work on. And that's it. The thing that I'm really happy about is watching LibreQOS take off and helping tens of thousands of people per week, new people per week, have a bloated internet. So if you have any questions. And by the way, I don't hear anything in my headphones.
Any questions? Questions? All right. Thank you, Dave, if you hear us.
Thank you for having me. Keep fixing the bloat. There's something happening here. What it is exactly clear. There's a man with a manifesto there. I'm telling you, you've got to beware. Saying stop, baby, log off now, get outside and get on down. The NSA, KGB, I'll care too much about what you say and what you see. Zoom is a bit more fast. Oh yeah, we spy, but only on the lower class. Oh, stop, baby, start dealing, run your code and your own machine. The AI is here every week, and they know you are what you read. Have a great conference, everybody. I wish I was there.
Oh. I guess you guys didn't take any notes here. So I'm not saving them.